Hi, lesson. Our focus will be on helping you understand the fundamentals of IP Multicast. And we'll cover most of the technology in a CCNA, CCNP level course. So in lesson 1, we'll cover IP Multicast fundamentals. We'll talk about multicast addressing, as well as just general technologies and techniques. In lesson 2, we'll focus on layer 2 and IP Multicast, focusing specifically on Internet Group Management Protocol, IGMP, and how it's utilized in an IP Multicast network. Lesson 3 focuses on Protocol Independent Multicast and the various flavors of PIM that are available to us. We'll talk about Dense Mode Multicast, Sparse Mode Multicast, Bidirectional PIM, as well as source-specific multicast. In lesson 4, we'll focus on rendezvous point engineering and placement. We'll discuss topics including Anycast RP, Auto RP, Static RPs, as well as BSR. We'll also discuss rendezvous point redundancy and introduce technologies like MSDP to the conversation. In lesson 5, we'll talk about multicast controls that are available to us. We'll talk about controls that are available at layer 2 for Internet Group Management Protocol, as well as layer 3. Additionally, we'll focus on administrative scoping and how having a proper plan for your multicast deployment will lead to your success. In lesson 6, we'll focus specifically on source-specific multicast, SSM. We'll start with a discussion of IGMP version 3, and then follow up with a discussion of how SSM's state and RP requirements are unique in a IP domain. Our last lesson, IPv6 and Multicast, will focus on the capabilities that IPv6 has inherent to it for IP Multicast. We'll also compare and contrast how IPv6 and Multicast are similar between version 4 and version 6. So come on, let's get started. Okay, so we'll begin with lesson 1, Introduction to IP Multicast, and we'll start with a Multicast overview. So to really start talking about multicast, we need to first off understand what multicast is. And this is a question that a lot of customers ask. What is multicast? How does it compare? Who uses it? So certainly the benefit of multicast is it allows the network to be able to take a single packet and multiply it, to replicate it out to many different receivers or hosts on the network. And you'll see as we go through the lesson that this has a very good compounding effect on the network, and it becomes very, very efficient for delivery of the same datagram, the same packet, to multiple different receivers. And one of the neat things about multicast is that it crosses subnet boundaries. So take what you know about unicast routing and layer 2 adjacencies and things like that, and kind of set them aside, if you will, for a little bit, because multicast behaves differently than unicast. And we'll go through those details as we go through the day. We do utilize the Class D network addresses, so if you go back to your kind of CCNA intro to IP networking fundamentals, you always deal with Class A, Class B, Class C, and then there's like Class D and E. D is, they just lump into multicast. That's what we're going to focus on today. And then Class E is experimental, right? So we're going to dig into part of the less explored parts of the IP family. And truly, from my experience, multicast can be very, very simple, or it can be unbelievably complex. And ultimately, it depends on your use case as to how deep in the weeds you get with multicast. So certainly, we'll try to make it simple and easy for everyone to understand through this lesson. Certainly, from also experience, you need to have careful planning. Before I became a vendor, I worked for a large global financial company. And one of the projects that I was involved in was a global IP multicast rollout across the entire world, right? So this was a big, big deal. We had to come up with an addressing scheme, some logic behind it, rules and kind of principles to put in place to make sure that the multicast environment did what we wanted it to do, scaled to meet our needs, but also protected the rest of the infrastructure to make sure that there wasn't going to be a problem if things went awry in the multicast space. So definitely lots and lots of careful planning, and especially as you get larger, you'll see when we talk about state that becomes even more important of a concept. So to kind of compare and contrast, if we look at the top diagram, this is a unicast environment. We have a single source on the left-hand side. that is sending data out to 3 different receivers. And because it's unicast, we have 3 copies of that same data being propagated out across the network. The source is responsible for sending those 3 packets. Compare and contrast to the multicast environment where I have the same single source sending to the same 3 receivers, but utilizing multicast, the source only has to send 1 packet, and the network is responsible for replicating that packet out to the interested parties, to the receivers. All right, this is its foundation, what multicast does for us to optimize traffic on the network. So another common question is, who uses multicast? So it sounds like a cool technology. Why doesn't everybody use it everywhere all the time? Great question. Certainly, being here in New York, there's obviously a lot of focus on multicast, especially in the financial sector, right? And there's some significant benefits to multicast for financial applications, being able to disseminate the same information, say a stock price, to multiple different receivers at the same time, so that you don't have network latency and replication delays to interfere with potentially a trade or something else that's could be a matter of a lot of dollars, right? So financial industry is probably one of the heaviest users of multicast anywhere in the world. Certainly video makes a lot of sense. Think about this from a live broadcast standpoint. I don't want to have to send out 1 million copies of the same packet if I'm a large TV broadcaster. I want to send out 1 copy and have it replicated to the interested parties. That's what multicast does, right? So it makes that a reality for those broadcasters. Certainly voice, and specifically music on hold or a call center application. Thank you for calling Cisco. Your hold time will be X number of minutes. Your call is important to us. That type of thing is all done via multicast. It's the same message being repeated to multiple different receivers. And again, I don't want to have to repeat that message again and again and again from a datagram standpoint on the wire. I want to send it once and have it be disseminated to everybody. So multicast. Certainly some of the system administrative tools, imaging and software distribution, these were some of my first exposures to IP multicast. Long ago, there was an application called Ghost. I don't even know if it still exists. But it was a common desktop imaging application. I was able to stamp out the same image to 50 desktops very, very quickly using multicast at its foundation, right? So that was a very common one. It's still in use today. Clustering applications leverage multicast, and there are more probably than you thought, right? Most people, when they think of multicast, their first thing that comes to mind is that's a financial trading application. I'm in healthcare. I'll never need it. When the reality is, if I'm a healthcare provider and I'm doing music on hold, that's a great use case for multicast for me. Or from a system administrative standpoint, I want to stamp out multiple copies of my desktop images or my server images. Multicast can again be utilized to achieve that kind of goal. So there's a lot of use cases for multicast. So if we shift gears and focus on multicast addressing and dig into the Class D addressing that we mentioned earlier, we'll see that we start off with what is lovingly referred to as the Dead Sea Scrolls of multicast. I don't know how many of you are familiar with a gentleman named Bo Williams. He is kind of considered to be one of the godfathers of multicast, if you will. And certainly this is a document that he had quite a bit of input into and still continues to have input into multicast from a technological development perspective. But it's all defined in RFC 1112. So if you're interested in some light bedtime reading that will definitely, probably put you to sleep, the RFCs are always a great place to go. You'll see as we go through the rest of the lessons that we'll refer frequently to these different RFCs, but this is the fundamental RFC for multicast, right? This is kind of the starting point for everything from a documentation perspective. We mentioned earlier that we are utilizing Group D addressing, so that's the 224.00/4 range, so it goes all the way up to 239, so it's inclusive of all that, and you'll see that we'll break that down into smaller blocks as we go through the discussion. And this is the Class D range, again, back to Class A, B, C, D. This is the D range that usually most people just kind of know that that's the D range, it's multicast, it's different. Well, we're going to try to demystify the different today, right? The high order bits, for those of you who are interested from a Wireshark standpoint or getting down into the detail on the wire, are all ones, right? So, 11, 10. When we look at the address ranges, they're broken down into different groups for different purposes, and we'll talk about these. Certainly link local addressing is 224 across the board, right? 224.0.0 are the link local addresses. We can also break those down into global address ranges, 224.0 through 1 through 238. Those are, in general, the broader bucket of IP multicast addressing that we can utilize. And then we have a group called the administratively scoped address range, 239. These are really kind of designed to be the RFC 1918 address space, if you will, for IP multicast, right? These are reserved for private company usage in the intent. And then depending on how structured you are, certainly you can always reserve the top 256 addresses for scoped address ranges across the board. So you'll see this as we go through in one of the next RFCs that we'll talk about, is providing a kind of a reference guideline structure for how to utilize multicast addressing in your enterprise. So let's focus on the link local addresses. These are very special, and we'll see these not only for IPv4, but they also come into play for IPv6 as well, closer to the end of the lesson, when we start talking about what these things do. These are designed specifically to have a TTL of 1, which means that they have a time to live of 1. It means they only go 1 hop, right? And then they expire. Because it's layer 3, we have TTL as a field. It's not a layer 2 that doesn't have TTL that just loops endlessly and causes a headache and heartache for everybody. These are all layer 3 packets, and they're designed to be things for protocols, right? Things that are very, very link specific. So OSPF, EIGRP, PIM. We'll talk about PIM in quite a bit of detail later in the lesson. And then also an example here for IGMP version 3. So there are some very specific use cases for link local. The good thing about link local is that they don't leave the next box. Right? They don't go from one box to the next and then beyond that, it's just to the adjacent boxes. That's the idea of link local, to contain that distribution, and that's all done through that TTL of 1. When we look at the global address range, these are assigned by IANA, the Internet Number Assignment Numbers Authority, right? These are the people who are running out of IPv4 addresses that are in the news recently. So certainly when we look at how they break this down, they control the 224.0 through 238 address space. And these can be allocated to different companies. Now, in all fairness, this was really kind of part of the RFCs prior to multicast being widely deployed. This was kind of the mindset of everybody's going to want to do multicast everywhere all the time, and we need to have some sort of control for it. The reality is, when you look at the global internet traffic, it's not that much multicast. Multicast still kind of remains an inside the enterprise or SP network, but not necessarily multi-domain across boundaries. So you don't see a lot of customers jumping up and down saying, I got to have a multicast address range so I can be globally routed on the M-bone. Certainly there are organizations who do that, but in general, your average enterprise or customer doesn't have that requirement. But they are controlled by IANA. You can request them if you want to, and they will be uniquely assigned to you, much like an IPv4, IPv6 range is assigned to you today. So that's globally unique on the internet, and you could have your own globally unique multicast range. So sometimes, though, they will assign the global addresses to very specific technologies and protocols, much like TCP port numbers or UDP port numbers that are well known across the board. Some examples are a technology called AutoRP, which we'll discuss a little bit later today as well, with regards to rendezvous point engineering. So we'll see that in lesson 4. Certainly, IANA has to kind of fend for themselves and protect the address space as best they can. People are always looking for additional addresses, and they need to keep that in mind as they allocate them out to users and customers. But I would imagine most of this kind of requests and requirements have probably died down a bit, just because people are either shifting to IPv6 or multicast not being widely deployed across the global internet. Certainly, when we look at the administratively scoped address range, this is the 239/8. So go back to your IP addressing days of old, right? How many addresses are in a /8? 16 million. So pretty fair chunk of address space. And we're able to see that this is really designed to be that RFC 1918 address space. So if you're used to the 10.0/8 network or the 172.16 blocks and the 192.168 blocks, similar approach, but for a multicast addressing allocation. So And then we look at RFC 2365 defining kind of the best practices for administratively scoped zones. And this is truly one of the driest reads I've ever had. It's just an addressing allocation scheme, right? It talks about how you can go through and break down a 239 subnet into different types of scopes. And this is important when you look at it from a global IP multicast rollout perspective. Certainly you want to have that structure, that organizational approach to be able to design it to meet your requirements, but it's, as I mentioned, it's not that exciting of a read. But the idea is that you want to break it down into different scopes to define the breadth of a particular multicast range. So for example, 239.192/14 being kind of the largest allocation, and that defines a globally reachable address inside of your network. So maybe that's the CEO's corporate, address the troops type of feed. That needs to go to everybody. Whereas if I maybe want to break it down into further scopes and maybe have a local scope, 239.255/16, and define that as being maybe a building-wide or campus-wide scope. So it never leaves the building or never leaves the campus, right? So providing an addressing scheme to localize traffic to different parts of your network, global, local, whatever makes sense for you. We have some customers who utilize these to be able to define different bandwidth requirements, right? So maybe if I want to send a 1 meg video stream, it's in this address space, but a 128 kilobit stream is in a different address space. That makes it very, very easy, and we'll see this in one of the future lessons. We talk about multicast controls, how we can start to control this flow of traffic so that it's not being sent out across the entire network. Certainly having a logical addressing scheme makes a lot of sense to be able to provide that foundation to write your ACLs and control lists so that you can understand where the traffic goes. So definitely 2365 is a good place to start. So if we shift gears to talk about multicast distribution trees and state, these are some very important concepts. And really, if I draw an alignment to mathematics, which is not a strong point for me at all, this is the kind of stuff that my teacher would have said in 8th grade, this is important because it's the foundation for everything else. So keep that in mind as you go through, right? This is the foundation that we'll use for the rest of the conversations and the live lessons to be able to talk about how multicast works and how it gets packets from point A to point B. So we start off with distribution trees, and really the idea with the distribution tree is that it is a path through the network to distribute multicast traffic, right? That's how traffic is replicated across the environment and how the packets flow. And if you look at one of my coworkers, Denise Fishburne, is a fantastic resource. She did a Cisco live session about being a network detective, how to troubleshoot a problem. And ultimately, that's the kind of detail that you'll need to know with regards to distribution trees is to troubleshoot a problem, right? I need to know what kind of tree I'm using to be able to figure out what's happening if things don't work the way you want them to, right? So to draw that kind of parallel there, when we look at the types of trees, we've got a shortest path tree and a shared tree. These are two considerations that we need to keep in mind. Certainly there are pros and cons to each, as in everything, right? It's always the classic networking answer. Somebody asks you a question, what's the answer? It depends. And truly it does, right? It's not being flipped. Sometimes it is being flipped, but certainly in the majority of the time, it truly does depend. It depends on the requirements, it depends on the application, it depends on the protocol. We'll discuss both of these. Shortest path is definitely the fastest tree, but one of the downsides to having the shortest path tree and this fast converging tree is that you are propagating state throughout the network. And we'll talk about state coming up as to why that's important to understand and what the impact of having a lot of state in my network is. Is it okay to have a lot of state? And then equally important, how much is a lot? Is 100 a lot? Is 15,000 a lot? Is a million a lot? And again, the answer, not to be flip, is it depends, right? So see how this is like a self-propagating thing? It's a career path. It's an adventure for sure. So certainly the shared is the most efficient way, but certainly could also be some suboptimal pathing through the network as well. So again, that's back to it depends. What are my requirements? Do I need to have a fast converging network, or do I need to have maybe a slower converging network? Again, you get to choose your own adventure. And then also equally important, what is state, right? State is information that the network devices must track for a multicast. And when we talk about the state, we'll see as we go through some of the CLI examples, it's things like S comma G, star comma G, and the amount of data that's being required for the network to understand where to send multicast traffic in the environment. And ultimately, how much state is too much state is very, very dependent on your platforms, right? Because it does impact your CPU load of memory. If I have an older Cisco 2501 software-based router, right? Hopefully some of you might remember the 2501s. They were definitely the workhorse of the early 2000s. Maybe you don't have them in your network anymore. Maybe they're in a lab somewhere. But certainly they were very limited in the amount of CPU and amount of memory that they could handle. Compare and contrast that to some of the higher end routers now that can handle terabits of routing. The amount of state is going to be very dependent on, that they can handle is dependent on the platform, right? Certainly a newer router can handle more than an older router. It's important to know the details. And certainly more state usually equals slower convergence, right? And for customers who look at convergence as being a very high consideration, a very high importance factor, that might be key to understand. So let's talk about the multicast distribution trees. And we'll start with the shortest path tree, also known as the source distribution tree. So when we look at it, we've got our source up here on the upper left-hand side that we'll be sending to the bottom two receivers. And when I look at the shortest path tree, there's a couple different ways I can get there across the network. Right? I could go from A, B to D, or I could just go A to C to E to get to both of those receivers. So the most optimal route, the shortest path, we're not very creative in the networking world, so we try to use words that make sense most of the time. But certainly the shortest path tree is from the source through router A, down to router C, and over to router E, and now both of my receivers have received the data, right? If I look at it from a shared distribution tree standpoint, if I've got a rendezvous point, we'll see the importance of rendezvous points coming up on a little bit later, but bear with me that we haven't defined our RPs yet, rendezvous points. Our rendezvous point is in D. So what does our path look like when we build out this topology? Our shared tree is from D to C to E, right? That's a pretty easy to visualize illustration. And if I've got sources over back at the upper left-hand side, their path doesn't go from A to C the way it did in the previous slide with the shortest path tree. It goes over to the rendezvous point and then to flow south to C and E. So you can see that that's kind of a good illustration of the differences between a shared tree versus a shortest path tree. The shared tree, I'm going to go to the rendezvous point and then from the rendezvous point down, right? So that might be suboptimal routing in my network. You know, if I look at it from a standpoint of what's the link between A and B, what if that's a slow circuit, right? A T1 or something even slower. That could be a performance implication on my multicast topology. So something to be aware of that we need to keep in mind as we're designing our protocols and choosing a technology for our multicast deployment. In the case of source 2 entering the mix, again, the path is through the rendezvous point, but in this case, that's also the shortest path tree, right? There is no connection from the router F on the far right-hand side southbound to C and E other than the path through D. So that makes sense. When we talk about multicast forwarding, this is where most people kind of get mixed up with regards to multicast because they're trying to draw allegories to what they know from a unicast perspective, and really the recommendation I give customers is that you kind of need to set your understanding of unicast off to the side because multicast works in reverse of unicast. So it's not the way you typically think about how traffic flows across your network. And certainly when I compare and contrast the two, certainly unicast is concerned about where the packet's going, right? How do I get to the destination? Whereas with multicast, that's not the case. How do I get to the source, right? Where did it come from? So I'm building a reverse path tree back to the source. How do I get there? Usually that's not the case in the unicast, right? I don't care how I got there, or maybe I do, but not as much. So with that, I have to worry about reverse path forwarding, the RPF. And we'll talk about RPF quite a bit as well throughout the day with regards to reverse path forwarding checks. These are checks that are done by the network to make sure that we're not looping traffic across the environment, right? Or having traffic take an invalid path back. This is a bit of a sanity check, if you will, in the multicast environment. Certainly, to perform the RPF check, I do compare it to the unicast table. So if I look at some kind of general troubleshooting guidelines for multicast, you have to have a solid unicast underlying network to be able to be successful with multicast. And multicast doesn't just run on its own, right? It relies on the underlying IP unicast network to transport datagrams, but you have to have a solid underlying network to be able to be successful with multicast. So when I look at the RPF check itself, what we'll do is we'll check against the source address in the packet and make sure that we didn't come in off of an invalid interface. And the rule is that if the datagram arrived on an interface specified in the routing table for the source address, then the RPF check succeeds, right? If it says, oh, hey, that's right, that's how you would get through to the source, then the packet goes through. Otherwise, our RPF check fails and we drop. And we'll see that there are counters in the software to be able to show us RPF drops. So that's important to know as well for troubleshooting, right? Did I pass RPF? Am I coming in on the wrong interface? Am I trying to go the wrong way across the network? That's why it dropped. Maybe that's where I've missed a configuration. So definitely food for thought and something to keep in mind as you look at troubleshooting and operationalizing your multicast network. So here's an example to illustrate RPF checking. We've got our source over on the left-hand side of 10.100.100.51, and we can see that the multicast traffic is really going across every single link in the network, but our RPF check fails on these routers in the middle. And the reason for that is because the best way to get to our source is through the bottom router here, right? This bottom router, as opposed to coming in through there. So RPF check takes place. It says that's not the right way to go. We'll drop it, as opposed to the two hops the other way. So certainly, in summary for lesson one, if we look at what multicast is designed to do, its number one role is to reduce traffic on the network, being able to take a single packet and replicate it across the network as opposed to having dozens, hundreds, thousands, millions of the same copy being sent from the receiver and routed across the topology. It does use Class D addressing, and there are tons of RFCs, and you'll see as we continue to go through the day, we'll layer more and more RFCs than the two we mentioned earlier into the mix for us. Certainly, distribution keys are key to understanding multicast traffic flow. If you don't understand which distribution tree you're using, shared or shortest path tree, you're going to have a hard time with multicast, right? So, and this will hopefully become much clearer as we get into some of the other lessons on things like PIM, Protocol Independent Multicast. Definitely our RPF check helps to prevent loops and floods, which is always a good thing. I'm sure everybody's suffered through a bridging loop where a spanning tree has failed to keep the network topology loop free. RPF does pretty much the same thing or similar function for multicast. So but it's not as despised as spanning tree. So most people hate spanning tree. People don't hate RPF as much as they do spanning tree. Definitely state as being a very large consideration to how you design and build out your multicast topology. Definitely key. And that's it. When we look at multicast addressing at layer 2, it's important to understand that there are some key considerations for mapping it into an Ethernet domain. And this is primarily an Ethernet problem. If you look at some of the super old slides on multicast, back some of the ones that Bo and some of the other earlier multicast people developed, you'll see that there's references to how it works into a token ring or FDDI environment. We're going to at least upgrade this technology into the 21st century, and token ring and FDDI are no longer predominantly deployed to the technology. But the idea with mapping multicast into an Ethernet frame is that we have a bit of address overlap, right? We start mapping the bits from a multicast frame into an Ethernet frame, and we have to start to lose some of the bits as we compress it to fit into the address space. So if we look at it from a standpoint of the high order bits we mentioned earlier, 11, 10, we've got 5 bits that are lost from the 32-bit address of an IPv4 packet. We only have 28 bits that are available to us out of the 32 to be able to use. So we have to start compressing and losing some of those, which means that we end up with some overlap. So here's a reference to FDII as well, but certainly the idea is that we want to illustrate that you end up with a 32-to-1 oversubscription of multicast into Ethernet frames, right? So something to keep in mind as a multicast network planner is you have to understand that this overlap exists when you start laying out your addressing schemes. Otherwise, you could end up with a situation where you assign the same multicast source address to different sources, but they end up mapping into the same thing at an Ethernet layer 2 domain, right? So then you could have conflicting information depending on the type of content it is. It could be overlapping video, or it could be video jumbled in with other data streams. So you want to keep that in mind because it might be troublesome for the receiver to sort that out, right? It might not know what to do if it starts to receive a market data feed and a video feed at the same time. So you have to keep that into account. And here's just kind of a secret decoder ring, if you will, to help you understand that these are all overlapping addresses. So it's not sequential, which would be really, really easy. It has to be hard. So the pattern is up here on the screen with regards to the overlapping addresses that can be encountered. So you have to keep that in account as you plan for your multicast addressing scheme as you deploy multicast in your network. So one of the fundamental things that we need to understand is, if I'm a receiver, how do I tell the network that I'm interested in receiving this data? Do I just randomly send out a message and say, hey, send me some multicast data because I want to see what's out there? No, I actually signal intelligently through my application. My video player, if you will, says, hey, I want to watch this particular stream that I happen to know lives on this particular address. And to do that, I do host to router signaling, and I utilize IGMP to this, right? So it's how the hosts tell the routers that they want to join that particular group. I want to receive that video stream. I want to receive that market data feed. I want to receive that music on hold stream. That's how they tell it. And then also, equally, the routers will solicit group membership from directly connected hosts. And this is a layer 2 technology. So keep this in mind as we talk through IGMP. We're focusing on layer 2 technology. This isn't up into the layer 3 domain yet, right? We're trying to figure out about hosts that are on the same VLAN, the same IP subnet across our network. What we mentioned earlier, RFC 1112 is the Dead Sea Scrolls of multicast. That's where IGMP version 1 is defined. RFC 2236 defines IGMP version 2. And as you can imagine, there were quite a bit of improvements made from version 1 to version 2. In general, most applications don't use version 1. They're all backwards compatible. If you have maybe a really old device that only supports IGMP version 1, you can run at that flavor. But in general, the most predominant form of IGMP that's out there today is version 2. And almost anything and everything supports IGMP version 2 that has any kind of multicast support. Building upon IGMP version 2, RFC 3376 is where we find IGMP version 3. And we'll talk about IGMP version 3 later in this lesson, and then also how that plays into a technology called source-specific multicast. And we'll get into details on source-specific multicast a little bit later today. We've got a whole lesson dedicated just to SSM because it's a little unique in how it works. So when we start talking about IGMP snooping and understanding how network devices understand who on the wire, who in the VLAN is interested in receiving multicast frames, IGMP snooping comes into play. And certainly it's a feature that's enabled on almost every switch, and in general it's enabled by default. Because what you don't want to have happen is have multicast on your network and not have IGMP snooping to be able to be intelligent about who I send multicast traffic to. if I look at how a network works, if I'm connected to a hub, hubs send the same packet to everybody. They are truly a broadcast domain, and whatever data comes in on one port, it gets sent to everybody else. A switch, on the other hand, is an intelligent device, and most of us have switches in our network. It's 2015. Hopefully we're getting rid of hubs in our environment, but certainly from a fundamental standpoint of how a switch works, a switch will learn the MAC addresses of the devices that are connected to it and only send traffic destined to that MAC address that needs to go out that particular port or group of ports. With the exception of being broadcast and, a little asterisk, if you look at most of the release notes, multicast, right? Multicast kind of breaks that one-to-one mapping of technology or of flows, and it can have one-to-many. So now if I'm a switch in a layer 2 domain, how do I figure out who all gets a copy of a particular packet? Well, IGMP helps me, but I also can utilize a feature called IGMP snooping, where I can figure out, hey, this particular port has a device that's interested in this particular multicast stream. Only send that stream to that guy and not send it out to everybody else like I would if I were connected to a hub. It's an efficiency mechanism, right? So this is fundamentally something that happens by default in your switch, and in most cases, it's enabled by default, right? So when you get back to your offices and start looking at some gear, you start doing show IP IGMP commands, you'll see that, oh my gosh, this stuff is on here, and I didn't even know it, right? It's protecting the network. It was also providing an efficiency mechanism inside the switch itself. Because what we don't want to have happen is having the MAC address table overrun as multicast traffic is received on the network. And this is something that's always a challenge for a switch. If you start thinking about switches today are capable of switching hundreds of gigabits, 40 gig interfaces, 10 gig interfaces are predominant in data centers, right? That's a lot of data. If all that has to go to the CPU, the switch will roll over and die. So having this IGMP snooping table allows them to be able to intelligently learn that particular MAC address lives on ports 0, 1, and 2, and it's in that traffic to those subset of ports, right? So the switches will snoop the traffic. They're passively listening, right? They're kind of eavesdropping on the conversation. They're listening out for IGMP joins and reports to see who wants to have the multicast traffic sent to them. It builds the table, right? And only the interested receivers actually get the traffic. So this isn't sent to everybody and their brother on the switch. That doesn't scale. That doesn't provide the benefits that the switch brings to the table. What if I'm a receiver that doesn't care about multicast traffic? Do I want to receive it? No. I only want to receive the traffic that I'm truly interested in. And it definitely helps control multicast traffic in layer 2 domains. So again, this is a layer 2 technology in your switches at a VLAN level and not higher up in a layer 3 domain. And as I mentioned, it is on by default on most switches, so you don't have to configure it. It's there for you because it's kind of what I would consider a goodness and light feature, right? Anything that's all goodness and light should be turned on by default. This is a default because it's important and it's an important optimization. So if we shift our focus and look at IGMP version 2 in this particular lesson, we'll see that RFC 2236 is where we find the specification for IGMP version 2. And one of the things that IGMP version 2 brings to the table is the concept of membership queries, right? I want to see who is participating in a particular group, right? So I can send a query to 224.0.0.1 with TTL1, and then it will send that out to all of the ports and say, hey, who's interested in this particular traffic, right? So I can start to become more intelligent about who is interested in receiving traffic, and the receivers will see that report and respond back to it, right? They'll report this membership reporting saying that this host or a subset of hosts are interested in receiving the traffic. This is on by default, right? This happens out of the box, if you will, with the IP stack in your operating system. So it's not something you have to manage and configure inside of the box. And then we've got some optimizations to restrict to one report per group per LAN. And then, as I mentioned earlier, it is all backwards compatible with IGMP version 1. So you don't have to worry about having a very specific configuration just for IGMP version 2 if you do happen to have older devices or older hosts that only speak IGMP version 1. So let's take a look at how this works in action, right? So in this case, we've got a network on the right-hand side. We've got an IGMP version 2 report that's being sent to 239.1.1.1 immediately upon joining. And then the router will send periodic queries to the receiver saying, hey, are you still interested in receiving the traffic? And then one member per group will report back that, yes, there is somebody on the subnet that's still interested in receiving the traffic. Now, if I'm the last person on the subnet, then we'll see what happens in some of the upcoming slides. But the idea is that as long as one person on a subnet is responding back that they are interested in receiving that particular traffic, the router will continue to send it to that particular group, right? And then based on its snooping table, we'll determine which ports to actually send it out to. And all the other members will suppress the reports. They elect who sends those reports amongst themselves. So in this case, we've got 3 hosts connected to a single IP subnet with a router. 10.100.1.1 is our router, and then we've got our host 10, 11, 12. So in this case, 10 is joining the group. He sends a report to 224.1.1.1 immediately. We've got our query election. So all the routers that are on a subnet will elect a querier, which is an important role, right? He's the one who's responsible for asking the host, are you interested in receiving this particular stream anymore? If the answer is yes, we continue to send it. If not, we remove it. But you don't want to have a subnet with 2 or more routers on it where all the routers are constantly barraging the host with, are you still interested in this traffic? What about you? Are you? So let's elect a query. Let's be intelligent about how we ask these hosts who's interested in the traffic. That's the role of the querier. So initially, all of them will, but the router with the lowest IP address is the one who has elected the querier. So that's kind of the secret decoder ring as to who wins. So depending on how you do your addressing scheme, most customers typically on an IP subnet will have 2 routers for redundancy, right? You'll utilize HSRP. So maybe .1 is the virtual address, .2 and .3 are the physical addresses that are assigned to the VLAN. In this case, the router with the lowest IP address would be the querier, which is .2, right? So typically that's what we see. Depending on what I kind of refer to as a customer's religion on IP addressing, we see customers typically will have .1 as the default gateway, and then in the spectrum, customers will have .254, right? Most customers typically use /24s because it's easy math, and address space is relatively abundant, assuming not talking about registered address space, but private address space. So then if it's .254, that's typically the virtual IP. .252 and .253 are typically the physicals on it for the SVIs for the interfaces. So .252 would be the lowest address in that case. So, but ultimately it depends on your addressing scheme as to what's out there. But .1 and .254 are probably the most commonly deployed default gateways out there, utilizing either GLBP, HSRP, and all the other fun acronyms, VRRP, that we love to have in our networking lexicon. But the querier is the one with the lowest IP address. And then the others are non-queriers. Now, certainly if the querier fails, right, if we see that, hey, this guy's not sending out reports anymore, maybe he's dead. Maybe I should take over, right? If I'm a non-querier, I'll start the election process all over again and resume roles, right? And this is all defined in RFCs. So again, if you're looking for some bedtime stories, these are always a fan favorite.
Is that based upon a particular timeout? In other words,
correct. Yes.
It in 30 seconds or?
Yes. So the question is that based on a particular timeout? Yes, and that timeout is typically platform specific. So is with most things, the devil is always in the details. You'll want to understand what the default values are for your particular platform and your particular release of code, because sometimes those timers will change. Although in all fairness, having worked in the BU where we were some of the ones responsible for making those decisions, we did our best to try to make the defaults a sane value, but then also something that didn't need to change unless there was something catastrophically wrong, right? Because we don't want to have defaults change when you upgrade versions of code, because then your network behavior changes. So, but definitely you want to check the docs for that particular platform. So iOS could be different from NXOS, could be different from iOS XE. So you have to be cognizant of those differences as you design and build your network. So we talk about maintaining a group from an IGMP version 2 standpoint. The router will send the query out, right? So in this case, this router is the active querier. And then one member per group will report back that, hey, yeah, we're still interested in the traffic. Keep on sending it, right? So, and all the others will suppress the report because they see the report from the one who responded. It's multicast. So it gets sent to everybody, right? So they all saw it and said, oh, great. Bob's already taken care of it. We don't need to respond. Now, if Bob goes away, then we'll elect another one. And equally, what if I'm the last person, right? I'm Elvis. I'm leaving the building. I'm the last guy in the group, and it's time to roll. Host 2 leaves the group, sends a leave message, and all the devices will send joins and leaves as they either subscribe to a stream or stop a stream or join a group. When I leave, I'll send a signal a leave message. The router will send a query. Is anybody still interested in the group? Well, nobody else is, right? Elvis left the building. They're gone. And in this case, we've still got one guy, so the group remains active. But what happens when that guy leaves the group? He leaves. The router sends a group-specific query yet again. Is anybody still interested? Nope. No reports received. The group times out. The router stops sending the traffic to that particular device. Now, something that's important to keep in mind, we talked earlier about switches and IGMP snooping and kind of what they do from an optimization standpoint. That was a layer 2. This is talking about a router at layer 3. So the assumption is in this topology really is that we're connected to a hub. So that's why we're relying on IGMP to time out. Certainly from a snooping standpoint, we would see the leaves and stop sending the traffic that way as well. So depending on the type of device you're on, you need to understand these behaviors because it becomes very important when something's not working, and you need to troubleshoot it. You need to know what's normal. How's it work? And it's very dependent on if it's a router or if it's a switch. IGMP itself is the fundamental and stays there, but yes?
IGMP snooping, does that have the automatic timeout if no device sends a report?
So the question is, does IGMP snooping have timeouts as well? In general, IGMP snooping is just a kind of a passive behavior. So it just builds the table. And then eventually it can time out. If it sees that receiver is no longer receiving the traffic, it's either send a query or a leave message, it will prune itself out of the table.
For example, if the device has not sent a leave message but just got cut off the network, I guess IGMP would detect that.
Yeah, so the follow-on question is if the device leaves the network but doesn't send an IGMP leave. Maybe the network cable got cut or the device was powered off or didn't exit cleanly. Would the router stop sending the traffic? And yeah, it would. The switch would, right? So that table would either time out or depending on the type of failure, it would see that as soon as that link went down, that MAC address is no longer available and would flush it from all of its tables, both the CAM table as well as IGMP snooping table. So, and that's a great example of the it depends process didn't work, right? Well, it depends on how it died. Did the process just hang? Maybe the server blue screened, right? And the link is still up, but it's not receiving traffic anymore. That's where the timeout would kick in. Whereas if it were a hard link down, the server lost power. Once the link goes down, that MAC address is no longer associated with that port because that port just went down. I know it's not there, right? So the link went down. So there's a lot of intelligence built into our networking platforms that help the network converge under different failure scenarios. So yeah, depends on the scenario though. Okay, so let's dig into some CLI. Okay, so as we start looking at the command line output from IGMP version 2, what we'll do is we'll start by looking at some iOS devices. So we've constructed a sample topology here that consists of devices running iOS XE at the top, the edge devices. We also have devices that are running iOS in the middle, the core devices. And then we have some devices down at the bottom that are running NXOS, as labeled as data center aggregation 1 and 2. Connected to all these devices, we have Linux servers that are able to inject multicast traffic into the network. So to kind of give ourselves a bit of an orientation where we're going to focus on this particular CLI output are the Core 1 and the Core 2 devices that are in the center of the screen highlighted in the blue box. And we'll start off by taking a look at some IGMP data on the first box.
So we will begin by connecting to Core 01, which is the router in the middle of our topology diagram on the left-hand side. And let's take a quick look at some of the existing IGMP configuration. And this is all done by default, just out of the box. IGMP is an important aspect of multicast, and certainly it's beneficial to have it enabled so that the switches and infrastructure can determine where and who is interested in receiving multicast traffic. And most platforms have it on by default from a configuration standpoint. So if we do a show IP IGMP interface, what we'll see is that all of the interfaces on this platform already have IGMP enabled by default, and we'll pick on gig 03, for example. And we can see that it's enabled by default. We haven't enabled any configuration to turn this on. It's already there. And then it defaults to version 2. Now, version 2 is backwards compatible with version 3, but as we'll discuss later in the lessons, distinctly different from IGMP version 3, which is primarily used for source-specific multicast configurations. So let's do a show IP IGMP groups, and we'll see what groups our network already knows about in this environment. So we can see that by default, the auto RP group is enabled, and it's enabled on loopback 0, and that it's there. We also see we're learning some multicast sources from Gigabit Ethernet 0/6, which is a port that we have a server connected onto that's sourcing multicast traffic. Specifically, it's sourcing it on these groups, 239.1.1.1.10 and 2.1. So we can see from the output here that we have some IGMP configuration or some IGMP traffic already happening in the network. And if we do a show IP IGMP interface gig 0/6, we can see that it is all version 2 and some statistics on IGMP activity, 3 joins, 0 leaves, which indicates that all 3 of these sources have started to transmit. They've joined the IGMP group, but they haven't left yet, which is part of the IGMP signaling process like we discussed in the lecture. So we can also do a show IP mroute, and we'll see that we've got star comma G state for some of these sources, right? 239.1.2.1, for example, that it's coming in. But these are more PIM entries than they are IGMP entries. But certainly, out of the box, it's not difficult to configure IGMP because it's already enabled by default, and that's definitely a good thing for scaling multicast designs. So with this, we've done a basic configuration and show and tell of IGMP and Cisco iOS devices.
Okay, so now we'll shift our focus to the routers at the top of the diagram, the iOS XE devices that are the edge of our network. And we'll take a look at some IGMP commands on these devices.
So to begin, we'll connect to our iOS XE router, Edge 01, in the upper left-hand corner of our network topology. And much like a traditional iOS platform, we can see that IGMP is enabled by default. Because of its value in a multicast domain and the requirement for a host to be able to signal to the network to join groups, we want to have all of our networking devices or routers and switches participate in IGMP out of the box so that they can intelligently handle multicast traffic if it's requested and seen on the network. So if we do a show IP IGMP interfaces, what we'll see is that all of our various Ethernet interfaces are enabled for IGMP, and specifically, let's look at Gigabit Ethernet 3. We'll see that it's enabled configured for IGMP version 2. That's the default. Version 2 is certainly backwards compatible with version 1, but it's also uniquely different from IGMP version 3, which is used for source-specific multicast. We'll discuss more detail on source-specific multicast in future recordings. So we don't have to configure anything really to enable IGMP version 2 on an iOS XE device, which is a nice capability. But if we do a show IP IGMP groups, what we'll see is that there is already some multicast traffic in this environment. We'll see that we've got a sender connected to Gigabit Ethernet 4 who has joined the group 239.100.100.100 and has been up for a little over an hour, and that's part of the IGMP state of the network. So this is all part of the memory and CPU, the information that the router has to use its CPU memory to compute and calculate for in the event of a convergence event. So if we do a show IP IGMP group detail, we can see some additional details on it. In this case, nothing terribly exciting except for some of the local flags, or the flags, which I wanted to call out. And that we can see, for example, loopback 0 has joined 224.0.140. That's the auto RP group. And it's also a loopback and a user configured one. So it's there out of the box because auto RP is enabled by default on an iOS XE device. But you can see that the other multicast source isn't listed as a local interface. It's dynamically learned, right? It's something that was learned via IGMP itself. So, and right now we can see that the source list is empty. Nobody else has joined the group. So, a little bit of detail of what you can see inside of an iOS XE device. So, with that, you have configured, or at least done a show and tell on IGMP version 2 in a Cisco IOS XE device.
So now if we take a look at NXOS, we'll look at the switches down here at the bottom, right? Data Center AG 1 and Data Center AG 2, and take a look at those from an IGMP perspective.
So to begin, we'll connect to our router Data Center AG 01 in the lower left-hand corner of our network topology. And much like iOS and iOS XE, IGMP is enabled by default on the switch. And that's definitely something that we want to have enabled because of IGMP's important role in building a multicast topology. Without it, we have no way to be able to determine which hosts are joining the various groups. So having on by default is definitely a key component for having a successful multicast deployment. So if we look at our show IP IGMP interface, we can see some output. And what I wanted to focus on is that this output looks a little different than what we saw within iOS or iOS XE. The formatting is a little bit different, and we see some additional details. So a lot more information on our timers and our version. We can see that this is version 2, and we can see our various group timeouts, the query values, and other details about IGMP, which makes it very helpful when you're troubleshooting to understand what the defaults are and what timers are in place and things of that nature, instead of having to look them up. Also, because this is a NXOS platform, there's some detail down here for virtual port channel, VPC. Now, this configuration doesn't support VPC, and VPC in and of itself is outside of the scope of the multicast live lesson, but it's important to know that virtual port channel does have some considerations that we'll discuss throughout the rest of the videos that impact how you deploy and design your NXOS domain. So you want to keep that in mind, that if working with NXOS and using virtual port channel, you'll want to be aware of the different considerations that we'll call out as we go through the rest of the lessons. So if we do a quick show IP IGMP groups, the same format that we used for a iOS or iOS XE device, we can see that we are already seeing traffic from a dynamically learned group. So our output is distinctly different here as well. The flags that we were looking at earlier in iOS XE that are part of the detail command are now there by default inside of NXOS. So there's a good enhancement to only have to do the one command instead of having to go deeper into the detail command. But we can see that this is a 225.100.100, that it was a dynamically learned source on Ethernet 2/3, and the uptime and how long until it would expire if it doesn't receive any additional traffic, and who the reporter was. So this is all part of that multicast state that we mentioned that's important from a design aspect to understand how much state your network has, and that will help drive some of your decision-making criteria for which protocol independent multicast topologies to use and things like that we'll go into detail on as well. So But you can see from a simple output command here that IGMP is enabled by default. We do have a source sending on that particular group, and that it's enabled by default for version 2 on an XOS. So with that, you've now taken a look at and seen some configuration for IGMP version 2 on Cisco and XOS devices.
So let's take a look at IGMP version 3 and how it relates to the multicast network. As we mentioned earlier, it is covered under RFC 3376. And what we've done in IGMP version 3 is we've added some additional capabilities to add intelligence to IGMP so that now we can start to include and exclude source lists. So now my clients can be very, very specific about, I want to see traffic from this particular source, but only this particular source as opposed to just generically joining a group. So what's important to know about IGMP version 3 is that we are able to be very, very granular in how we join groups and what traffic we want to receive compared to kind of IGMP version 2, which is a bit more broad. I can join a group and anybody else who's a member of that group who's sitting to that group I will receive traffic from. Whereas with IGMP version 3, I can be very, very specific. This does require typically a different IP stack or a different implementation at the host. The host has to be IGMP version 3 aware. It has to know, hey, I need to speak IGMP version 3. I'm going to be responding and joining these very, very specific streams. And they use this new IP Multicast Listen API to do that. So certainly something to keep in mind when you look at deploying your multicast network in your environment. You might or might not need to upgrade some of your devices to be able to support IGMP version 3. It is relatively new if you look at it from a big picture standpoint. And certainly the applications are also needing to be rewritten. So you'll see this again in financial trading and in video environments where they're taking advantage of IGMP version 3 for some of the reasons that we'll go through in the SSM section. So we've got a new membership reporting address, so we don't overlap with the membership reporting address that we utilize for IGMP version 2. This is what allows our interfaces to be able to participate in both version 2 and version 3 environments simultaneously, right? So it's not an all or nothing proposition for customers. They can deploy multicast applications that utilize IGMP version 3 on the same devices and the same networks that they also have devices that utilize IGMP version 2. So it gives a good migration path for customers to be able to maintain that. And the idea is that all of our hosts are going to send their reports to this particular address that instead of the target group address like they did in version 2. And then all of our routers obviously will listen to that address as well to see who's interested in receiving traffic for that particular group. There is no report suppression, so all of the devices will respond to the reports, right? As we saw in IGMP version 2, one person was elected the querier, right? And will respond back to those reports. In IGMP version 3, everybody does because we're much more granular. We need to make sure we don't miss something important. And then you can certainly tune and nerd knob your response time and interval. So in the case of IGMP version 3, when I join a group, again, RFC 3376, and more fun reading. This is our first instance where we actually see the S, G or star, G notation. You'll see this a lot when you start looking at multicast networks. S, G is shorthand for source and group membership, right? So this is part of what comprises multicast state. So that's what the decoder ring, if you will, for S, G is. S is the source, and then comma, and then the G being the group. And you'll see that when you start looking at some of the CLI outputs a little bit later on. Again, we'll have the IGMP device, right? In this case, a receiver sending a report to the multicast address, and then it's sent out to everybody else on the wire. So in this case, we've got a source up here, 10.100.1.1, sending to 224.1.1.1. And then we only want to receive for the host down here at the bottom, only wants to receive traffic from the one receiver. So we can see up here on the topology, both of our sources in the upper left and right-hand corners are sending to the same group. Now, I mentioned earlier in the lessons that if we have multiple sources sending to the same group, the host needs to either be able to sort that out or filter out which one they really wanted. With IGMP version 3, we're now able to say, you know what, I only want to see traffic that's sent to this group from this particular source. So in this case, we're going to add the include to say I want to receive traffic from 10.100.1.1, which means that I won't receive traffic from 10.200.2.2. Right? So now our host, our receiver, is more intelligent about how and when and where he joins multicast groups and what traffic they can receive. This is the benefit of IGMP version 3 in a nutshell right here in this very simple example. Two sources sending the same group, the receiver is able to sort it out and say, you know what, tell the router, don't send me any of the traffic that's sent to that group from source 10.200.2.2. Very cool capability in IGMP version 3. So when I join a group, again, we go back to our sample topology that we'll use throughout the IGMP lessons. We'll see that the host will send a report to the multicast group and it says, I want to join group 224.1.1.1. My exclude list is empty, which means anybody who sends to that group, I'll receive their traffic. No big deal. So there's not anything magical or mystical about that. Now, in the case of an IGMP version 3 request, I actually tell it I want to include 10.0.0.1. So only send me traffic that's into this group from this particular source from the network, right? So anything else that might be on the 224.1.1.1 network, I'll ignore. Or actually, I won't ignore. The network won't send it to me to begin with. The router says, hey, he didn't ask for that traffic. We're not going to go ahead and replicate it out to him. That's part of the intelligence of IGMP version 3. So then only our included sources are joined, and we're more meticulous about what we receive. We also can likewise include and exclude. So in our join request, we can say, you know what, ignore this source, but send me everybody else, right? So I can reverse the logic. It's not just include, but I can also exclude who I need to receive the traffic from. So I've got options. And this is all configured on the host, right? So this is part of the application and stack that are on the individual host. So whether that's a Windows box or a Mac or a Unix client or something else, this is part of their configuration for their IGMP of their multicast application to be able to say, I want to receive traffic from this particular source. This doesn't just happen randomly. You know, the user doesn't say, you know, I don't want to receive traffic from this particular source today. It's usually something that you, the network administrator or the system administrator or the application owner, sets up. And then the host follows your instructions. A lot of times this is a web portal, right? They'll click on it, click to join this link. The user has no clue that they're using IGMP version 3 and source-specific multicast. As far as they're concerned, it's just normal networking magic 101, right? Our job is make the impossible look easy, and you get to do that with IGMP version 3. So we will continue to maintain state, much like we do with IGMP version 2. We'll send a periodic query. As we mentioned earlier, all of our devices that participate in the IGMP group will respond. Compare and contrast this to IGMP version 2 earlier, right? They elected one of them to say, you're the reporter, and the rest of us will not bother. This changes in IGMP version 3.
So we'll connect to our router core 1, which we've done over here. And if we look at interface gigabit Ethernet 0/6, we can see that there's no specific IGMP configuration. This is just a gigabit Ethernet interface configured in layer 3 mode connected directly to a server. And I can also verify this by doing a show IP IGMP interface gig 0/6. And what we will find is that the interface defaults to IGMP version 2, as expected, and this is a default, so it doesn't show up in the running configuration, but it is there on the interface. What we're going to do is configure the interface for IGMP version 3, but before we do that, we're going to start a multicast stream from our directly connected server, and we should see an IGMP join group 239.1.1.1. So we'll start the stream, And now if I do a show IP IGMP group, what we will see is that we do have a server or a source sending on 239.1.1.1 connected to gigabit Ethernet 0/6, and that it just started. Its uptime is only 6 seconds. And now what we will do is configure our interface for IGMP version 3. So we'll go into config mode, interface gig 0/6, do the command IP IGMP version 3, get out of configuration mode. And now if we review the interface config, we can do a show run interface gig 0/6. Then we can see that the command has been accepted. And then we now show IGMP version 3 on the interface. And we can also verify this by doing a show IP IGMP interface gig 0/6. And we'll see that our IGMP version has been updated to reflect that it is now version 3. Now for our host that's been transmitting traffic, if we do a show IP IGMP groups, what we'll see is that it's still connected, right? We have not disrupted the stream. It's still transmitting on the same group address, the same interface, and its uptime is a little over a minute now. And this is a non-disruptive change. With IGMP version 3, we're able to support backwards compatibility to IGMP version 2 hosts as well. So it makes it for a very straightforward transition for customers who are looking to migrate from IGMP version 2 to IGMP version 3, or for customers who need to support both protocols at the same time on the same interface. We're going to configure IGMP version 3 on an iOS XE device. In this case, in our diagram, we're going to connect to Edge 02, which is in the upper right-hand corner, and we've got a server directly connected to Gigabit Ethernet 4. We can see in the configuration that there is no IP IGMP configuration at all. We're in a default state, which we'll be able to review and see here that our IP IGMP interface gig 4 is defaulting to IGMP version 2. So very consistent with what we see in iOS configurations. Now we're going to start our traffic from our directly connected server, which will start to build some state in the network, and we'll see an IGMP group being joined. So today, or right now, if we look at our IP IGMP groups, we'll see that the default group for AutoRP is joined, but we do not have any other groups joined on this particular device. So we'll start our traffic source, and now what we can see is that we have an IGMP or a multicast stream joining 239.200.200.200 on Gigabit Ethernet 4. And its uptime is 4 seconds. This is very, very similar to what we saw in the iOS configuration for the iOS platforms. So there's a lot of consistency between iOS and iOS XE from a lot of the CLI output perspective. So what we will do now is we will configure our interface to be an IGMP version 3 interface. So we'll go into configuration mode, interface gig 4, and we'll use the same syntax, IP IGMP version 3. Get out of configuration mode. We can review the configuration was accepted by doing a show run interface gig 4. And we see now we have IP IGMP version 3 configured. And we also can do a show IP IGMP interface gig 4 and see that the version has been updated from version 2 to version 3. Now, equally important, we'll be able to verify that the group state was not lost. This was a non-disruptive change. So if we do a show IP IGMP groups, we'll see that we still are sending traffic on 239.200.200 on Gigabit Ethernet 4, the interface we just changed, and that our uptime is around 1 minute 16 seconds. So this did not force a leave of the group and cause the host to rejoin, but rather the traffic continued to send and was non-disruptive. This provides, again, that easy migration path for customers to go from version 2 to version 3 and support both simultaneously. So very nice capability. And now you've configured IGMP version 3 on an iOS XE device. We'll configure IGMP version 3 on an NXOS device. So we'll connect to Data Center AG 01, a Nexus 7000 in the lower left corner of our screen. And we can take a look at the configuration of the interface where our directly connected server, which will be our source, is connected. And that interface is Ethernet 2/3. And we can see that there's no IGMP configuration configured on this interface. It's in its default state. And to verify what that default state is, we can do a show IP IGMP interface E2/3, and we'll see that it is version 2. Now, what's interesting to note is that some of the CLI here is different than what we see in a traditional iOS or iOS XE device. We do still see the same data that our IGMP version is configured for version 2, and our various queries and timers and things of that nature that are configured. We also see some interesting statistics. We can see the number of different queries from different versions, and most notably, that's specific to NXOS speaking devices, is that we have configuration for virtual port channel information. So in this case, we're not using VPC, virtual port channel, on the NXOS devices, but know that there are some considerations to be taken into account when using different modes of PIM, Protocol Independent Multicast, on a virtual port channel device. That'll be configured in the appropriate section for that topic, but something that I wanted to call out and make sure that everybody was aware of. But we are configured for IGMP version 2. We can also see that if we do a show IP IGMP groups, that there are no groups that are joined. By default, NXOS doesn't join a default group the way iOS or XE does when you enable multicast routing, so we don't have that state for the auto RP configuration. Now, what we will do is we'll start our traffic from our server, and we'll see a join on 225.100.100.100, and we can verify that it joined by doing a show IP IGMP groups, and there we can see our traffic. It's coming on Ethernet 2/3. It was dynamically learned, so there are some different flags that you'll see within NXOS, and the decoder is at the top as far as what those flags indicate. This is a dynamically learned one, which means we learned it through IGMP, and our uptime is only 5 seconds. So this is the traffic that we just now started. But to configure it for IGMP version 3, what we'll do is we'll go into configuration mode, and notice that we don't have to use config T. We can just use straight config as the command to get into configuration mode. Interface Ethernet 2/3, but we will use the same syntax, IP IGMP version 3. We can get out of configuration mode. Oh, and now when we look at our interface config, gig 2/3, I'm sorry, E2/3, we'll see that we now have an entry for our IGMP version. And this can also be verified inside of the show output from show IP IGMP interface E2/3, and we can see that our IGMP version is now 3. Much like on the iOS and the iOS XE devices, what we'll see though is that our traffic and our change was non-disruptive to move from version 2 to version 3. So IP IG groups, and we can see that we're still sending on 225.100.100.100 on Ethernet 2/3. Our uptime is now 1 minute 40 seconds. So again, this was a non-disruptive change. Our traffic wasn't disrupted while we made this configuration, and this allows backwards compatibility between version 2 and version 3 devices. And with that, you've configured IGMP version 3 on an NXOS device.
In summary, for IGMP, certainly it's a critical component in controlling multicast traffic at layer 2, right? And that's something important to keep in mind when you're troubleshooting your multicast environment. Am I dealing with layer 2, layer 3, or an application layer? Certainly IGMP being layer 2 centric. It definitely helps. Snooping helps in a switched environment. As I mentioned, this is on by default. So it's on by default because it is a goodness and light feature that should be turned on in all networks all the time type of deal, because it helps preserve CPU and resources inside of the switch, which is a finite commodity. Certainly IGMP version 2 is the most common when we look at customer environments across the world. IGMP version 2 is by and far the leading multicast IGMP version that's out there. Certainly version 3 is becoming more prevalent, and specifically in financial applications, we see a lot of IGMP version 3, where they're running out of multicast addresses or they have so many streams they want to be able to reuse the same multicast group address, but have different sources sending the different types of data to different receivers. So your application does need to support IGMP version 3 or source-specific multicast to be able to really take advantage of that capability, but that's becoming more and more common over time. So let's talk about multicast protocol fundamentals and where this kind of fits into the table. Again, two types of distribution trees. Shortest path, also known as the source tree. We touched on these earlier in lesson 1. Certainly the idea is being able to build a path from the receivers to the sources. And really, the shortest path tree is the optimal path, the optimal unicast path through the network, right? But the penalty you pay for having the shortest path tree is that it utilizes more resources and state in the network. So depending on what your considerations are, shortest path tree might not be your best bet if you have a lot of multicast and a very complex topology and you don't want all that state distributed out across multiple parts of your environment. The shared tree certainly takes less memory and resources in the network itself, but it could also have the possibility of suboptimal pathing and additional delay. So again, it's back to understanding your requirements and your application to know which technology do I use. And really where that kind of rubber hits the road is when we talk about the different types of PIM as to which type of tree we're going to get, right? So it's going to be a matter of understanding your requirements and then picking the right technology to meet those requirements and make it a reality. That's kind of network engineering 101. So when we look back again to the example of the shortest path tree, we have source 1 talking to receiver 1 and 2 down at the bottom, connected to router A, C, and E. We see that the shortest path tree is the path from source 1 through router A, southbound to router C, eastbound to router E, and then southbound to our 2 receivers. Pretty straightforward in this topology, right? If we look at the shared tree, now we're utilizing the rendezvous point concept, and we'll talk about rendezvous points quite a bit in this lesson and in the next to go into more detail. But we'll see that how this changes the flow of traffic to utilize a shared tree. Right, we've got 2 different sources, source 1 and source 2, both sending data to the rendezvous point at router D. They're converging there at router D, then being sent southbound through the shared tree down to our receivers. But we can see that the pathing is different, especially for our traffic from source 1 to receiver 1 and 2. They're not utilizing that direct link, that shortest link between router A and router C, but rather they're traversing over to router D and then southbound. That's a good example of the trade-offs that you make between shared tree versus shortest path tree. This localizes our state into those different routers that are on that path, as opposed to if everybody did the shortest path tree, we'd have state showing traffic going down router A to C as well. So again, it's trade-off. When we look at multicast forwarding, how do I actually get traffic across the multicast domain? We mentioned it's backwards to unicast routing, and this is where a lot of the confusion comes into play for people that aren't familiar with multicast and trying to operationalize it. They apply unicast routing logic to multicast, which doesn't always necessarily map out one for them. So certainly unicast is concerned about where the packet is going, whereas multicast is more concerned about where the packet came from. Where was the source? How do I get back to the source? Because I need to go talk to him to get my data. And we utilize that reverse path forwarding that we discussed earlier as well to be able to mitigate loops and packet duplication in the network. So for that reverse path forwarding, what is RPF? It's the check that is done for every multicast packet that traverses a network to make sure that it's received on the upstream interface from the source, right? So that it's following the distribution tree. And this is important, right? We don't want to have traffic going the wrong direction or being sent from a potential rogue source or someplace else, but rather, is this the logical way we expect to see the traffic? And if the answer is no, we drop it. The RPF check fails, which is our loop mitigation. We drew a bit of analogy to spanning tree earlier to talk about that. The RPF check itself is what does that checking to make sure that it did come from the source address, the upstream address towards the source, So if that fails, the packet's dropped. If it succeeds, then it's passed the RPF check and life is good. And it goes on its merry way. And again, if the RPF check fails, it's dropped. Obviously, depending on the topology, that might or might not be a normal thing to see. So again, back to the comments I've made earlier with regards to understanding what normal looks like in your network. It might be normal to see the RPF check fail on this one particular interface because of the way your topology is designed. You need to know that ahead of time, as opposed to when somebody's breathing over your shoulder saying, when's the network coming back up? Is it up? Is it up? Can you give us a status? We got 30 people on a bridge. Can you give me a status? I'd like to get an update. CEO wants to know, right? Hopefully you've heard of other people that have been there and haven't had to experience that yourself. That's not a whole lot of fun. But certainly preparing yourself to be able to troubleshoot and operationalize your environment is important. So when we look at RPF, we mentioned it's forwarded. It's typically silently discarded, although you won't see a log message. Usually it'll just show up as an increment in a counter, right? So it's not like it's something that you'll see a bunch of warning signs or anything else. And then the datagram, when the datagram is forward, it's sent out to each interfaces in what's called the outgoing interface list, the OIL. And when you start to look at multicast from a CLI standpoint, you'll see outgoing interface list, or OIL as the abbreviation for it, in a lot of the CLI. It's in there showing these are all the different interfaces that will send this multicast traffic out. So you can start to visualize a little bit in your network where multicast traffic is going. You know the upstream interface towards the source, and you'll see the outgoing interface list where there are either receivers that want to receive the traffic or other routers that are part of the distribution tree that will receive that traffic as well. And the key point of the RPF is that it's never forwarded back out the reverse path forwarding interface, right? We're not going to send it back the way it came. We already received it. Why are we sending it back? That would be a loop or a problem. So you don't want to do that. So now if we focus on lesson 3.2 PIM Overview, let's dig into some of the details on Protocol Independent Multicast, what it is and how it builds these distribution trees. So we mentioned earlier that there's a couple different flavors of them. Certainly the earliest flavor of PIM is dense mode. And the idea with dense mode is that it uses what's called a push model. It will send traffic everywhere all the time until it either times out or until somebody tells it to stop. But the problem with dense mode is that it will do that again and again and again and again. So that means that the traffic is flooded throughout the network. And just by the using of the word flood, that's probably not a good thing, right? In most cases, people aren't really enjoying floods. If my basement floods, am I happy about it? Probably not. If multicast traffic is flooding my network, am I happy about it? Probably not, right? So keep that in mind. It'll prune back where it's unwanted, but the flood and prune behavior happens again and again and again, roughly every 3 minutes. So what you see is that traffic gets flooded. If somebody prunes it back and says, I'm not interested in this at all, go away, it'll prune back, but then it comes back 3 minutes later. Oh, hey, did you want this traffic now? No, man, I already told you earlier I didn't want it. And that process repeats itself again and again and again. Now, it sounds horrible, but why do we have dense mode? If you look at really the early history of multicast and kind of where it came from and the networks it was used in relatively smaller environments where this was no big deal, right? If it's all being flooded underneath that segment and it comes and goes, who cares? But the reality now, we look at large global networks and mission critical applications and things of that nature, we want to do things a little bit more intelligently. So that's where sparse mode comes into play. Sparse mode uses a pool model, which means I won't send you the traffic unless you specifically request it. That's the IGMP that we talked about earlier, right? That's some of the requirements for IGMP version 2 is that I want to subscribe to that channel. Please send me that information. Please send me that data, as opposed to, I didn't ask for this, why are you sending it to me, right? Why are you flooding it? Why are you pushing it out to me? And so that's definitely a much more intelligent way to handle traffic in your network. And that's where we see sparse mode as being, in general, the predominantly deployed protocol independent multicast technology that's out there. So let's dig into the details of the fun that is PIM Dense Mode. We mentioned it uses a flood and prune model and that it will flood the traffic across the network whether you wanted it or not, right? So that's definitely a downside of PIM. We do have forwarding state that's created by the data arrival, which could also be a detriment in my environment, right? If I have a network that I'm flooding multicast traffic to that's not interested in, I'm creating state in my network. I'm creating those S, G mappings that we talked about earlier that take up CPU and memory and impact my convergence numbers and those types of things. And then if I have it pruned off, then it's creating this constant churn of state and multicast traffic in my environment. So all these things are typically something you don't want to have happen in a stable network topology. The idea with convergence is once it's converged, it's converged. I expect to see very long uptimes in my routing table. Right? I don't expect to see minutes, seconds in my routing updates. I expect to see, hey, this OSPF route has been up for 36 days. Hey, my router's been up for 36 days. That's probably a good thing. If I see a route constantly flapping and churning, that's usually a sign of bad things happening. Same approach to multicast, right? If I see that multicast route flapping and churning about, that's typically a sign of bad things, or it's a sign of dense mode. So we try to avoid that. Certainly that can lead to black holes and route loops, which are obviously things we want to avoid. So the idea with dense mode is that when I start to flood, if I have a source over here on the left-hand side that's sending to a receiver down at the bottom, because of the flooding behavior, the routers that are on the top receive the traffic. Did they ask for it? No. They don't want it. Well, maybe they do. If a receiver joins, that absolutely wants it. But in this particular scenario, they don't want it, yet they're receiving it. They're storing state. They're seeing that, hey, there's this multicast stream and here's the traffic and let's flood it out across my network. And devices that are connected to those routers see that multicast traffic. So routers that are connected to or devices that are connected to that network see that multicast traffic because it's being flooded across the domain. Obviously, not an optimal way of doing things. So what will happen? They send prune messages back. Hey man, I don't want that. Quit sending me the stream. Great. The source receives it and says, you're right. I shouldn't send you those streams until 3 minutes later. Then my timer pops. Maybe you want the streams now. I'm going to send them to you again. So that's not a very efficient way of doing networking, right? So in this case, now we've got our perfectly routed tree. We've got a nice path down to the receiver, and life is good. Our state still exists because it probably hasn't timed out in the tables, but it's still out there consuming state, even though now we're not replicating packets. But this process will repeat itself again in 3 minutes. Definitely, something you want to think of quite a bit before you deploy a dense mode network in a kind of a modern environment today. It's something that most people are not doing. Yes?
Is the 3 minutes a requirement to the protocol, or is that a parameter that's set and is typically 3 minutes?
So the question is it a parameter of the protocol? And the answer is yes, it's a parameter of the protocol. So that's one of the kind of inflexibilities of dense mode is that it's 3 minutes, whether you wanted it to be 3 minutes or 30 minutes or 3 hours, right? It's a fixed value. So it's definitely not something that we see customers deploying in the primary use case, and this is being very generous in my opinion. The primary use case maybe in a lab, if you want to see dense mode flooding and realize, wow, this is horrible, you certainly can. The option is there. Performance testing, unless you're another router vendor or somebody else that's doing some sort of competitive bake-off, that might or might not be important to you. In general, certainly easy to configure. Do I have to do any configuration work for it? Very, very little. So if I'm totally cool with this behavior, it's definitely the choose your own adventure path. Do I want to go into the dark cave where there might be a dragon, or do I want to go out into the nice pasture where I can ride a unicorn? Probably going to choose a unicorn over the dragon, right? But you got to know what you're doing. Certainly, the potential issues, having additional state, the flooding and the pruning constantly going on in my network failing to converge nicely, et cetera, are all reasons why dense mode isn't being deployed. So one of the things that I keep in mind, probably, over 15 years ago, I went to Cisco Live in Vancouver, British Columbia. And at the time it was called Networkers. So that kind of dates myself a little bit. They've totally renamed the entire program to where a lot of people don't even know it was called Networkers. But the idea was that we were attending a Cisco Live type function. And I got to sit in a class where Bo Williams was teaching, and his whole spiel on dense mode was very simple. It's like, I want to boil it down to caveman logic for you. Sparse mode good, dense mode bad. That's really all you need to know. But certainly now you know the details behind why is dense mode bad. It's bad because it does the flooding and the pruning and creates all this state. But certainly it's something that stuck with me 15 years later. I don't really remember the rest of Bo's topic and conversation other than it was multicast, but I remember sparse mode good, dense mode bad. So maybe that'll stick with you as well, and you can propagate this story.
We'll configure Protocol Independent Multicast in dense mode on iOS devices. To begin, we'll connect to our Core 1 router, which is an iOS device, and if we do a show IP PIM interfaces, we'll see that we don't have PIM configured anywhere. So let's go ahead and apply the configuration commands to enable PIM. We'll paste them in, and we'll see that our first command that we need to enter is IP Multicast routing. This is going to be required in iOS devices to start the processing for multicast, and then we'll begin to configure PIM on our various interfaces. So we've configured PIM in dense mode on all of our IP enabled interfaces, and it's always important to remember this is one of the most common misconfiguration items for any IP multicast deployment, is that people will tend to forget to add protocol independent multicast configuration to an interface that ends up being part of the RPF path, the reverse path forwarding path, back to the source, which then means that the RPF fails and because it's not PIM enabled, and then the traffic doesn't work. So that's a common misconfiguration. So one of the things you'll get used to doing is doing a show IP PIM interface, and now we can see that we've got multiple PIM neighbors. The rest of our network is already configured for PIM, and it is in dense mode, and we can see that that's also reflected. So specifically, we're going to be worried about our connection on gig 0/1, which is our peer iOS device. We can see that that's in dense mode as well. And we can also do some additional details, show IP PIM interface gig 0/1 detail, and we can see quite a bit of information, right? We can see that PIM is now enabled. It's in version 2, that it's in dense mode. So let's remember that we talked about in the lecture, with dense mode, there's a lot of dense mode flooding, right? So that's not desirable behavior, but we'll see how this plays out as we look at some of our other output. So, and there's a lot of other statistics here. Some of it's relevant to dense mode, some of it's not. A lot of it's just generic iOS stuff for various types of interfaces, MBMA interfaces for frame relay, for example, or ATM multipoint. So we won't cover all those because that's not part of our topology. But if we do a show IP mroute, and this is our first time doing this command, this is to view the multicast routing table. And what we'll see is that we've got a number of flags. There's a lot of detail that's reflected in the multicast routing table. We can see that there's a flag for dense mode, for sparse mode, BiDir, SSM, etc. Right? These are our different types of modes of PIM that we talked about earlier, and then a lot of other specific attributes, whether it's for BGP or for VXLAN configurations, etc. There's a lot of detail here that can be shown in the multicast routing table. So let's take a look at the output that we have now. This table was empty because we weren't doing any PIM or multicast processing prior to configuring PIM on the interface. But now we can see that we're starting to participate in multicast groups. This is the one for AutoRP. We talked about that during the lecture as well, and we'll talk about it in more detail in the Rendezvous Point chapter. But we can see that we're starting to get some additional state in the network. And that was just by virtue of enabling PIM and configuring it on some interfaces. So we've got a second iOS router that we'll connect into, and we can do a show IP mroute, and we'll see that we've got some additional state. These are star comma Gs from a server that's connected to this router core 2, and we can see that we've just got some sources that are transmitting. What we'll do is we'll start a client interface on our server and configure it to join the 239.1.1.2 group.
So now we've started that traffic, and on this router, which it's directly connected to the source and the receiver, they actually are both the same box. What we'll see is we have a new entry in our routing table specifically for the client. 10.0.0.14 is explicitly joined 239.1.1.2, and we can see that it's in dense mode. And then again, our flags and various attributes. We can see that it's coming in on Gigabit Ethernet 0/6, and this is the outgoing interface list, the OIL list. And we talk about OIL throughout some of the lecture as well as part of the topology that we have there and that we build for where the multicast traffic goes. So this is very, very helpful when you're troubleshooting various issues. Now, if we go back to our Core 1 router, because this is in dense mode, what we will see is that our state table should have increased. So there's a star comma G for 239.1.1.2, and there's the actual S comma G, the state for that particular source and receiver. And what's interesting to note, because it is in PIM dense mode, this router is not in part of the path between server 4, which is doing both the client and the receiver components, yet the state is being flooded over to the second router. And if we watch this long enough, what we would see is once the 3-minute timer comes up, that the PIM dense mode would prune it, and then it would flood it again, right? So this would be a constant churn of our dense mode state, or our multicast routing state, and this is part of a big reason why dense mode is undesirable. This router is not in the path, it's not part of the communications, yet we're receiving state about this particular source and destination pair, which is just unnecessary. So, but from a configuration standpoint, the config for dense mode is very, very easy. There is no concept of a rendezvous point, and it just floods and prunes throughout the network topology, which is obviously undesirable. So if we do a quick show run include PIM, what we'll see is we really haven't added a lot of configuration. It was really just the PIM dense mode command on the various interfaces that are all that's required for it, plus the IP multicast routing configuration. So you can see it's very straightforward to configure PIM in dense mode on an iOS device. We'll configure iOS XE with PIM Protocol Independent Multicast dense mode. To begin, we'll connect to our Edge 1 router, which is an ASR in the upper left-hand corner of the topology. And we can do a couple quick show commands and see that there is no PIM configured on here. We don't have any multicast routing table. So this is a platform that's ready to be configured for Protocol Independent Multicast. So we'll go ahead and paste in the commands. And we'll see that one of the differences with iOS XE and iOS native is that we still use the IP multicast routing command, but we also use the distributed keyword, and that takes advantage of some of the hardware attributes that are present in the ASR platforms and inside of XE to be able to take advantage of all the hardware and CPU resources that are available to us. We'll then also configure Protocol Independent Multicast on our IP interfaces using the exact same syntax, IP PIM Dense Mode. So now we can take a quick look at our PIM neighbor list and see that we are starting to form PIM adjacencies with other devices. We can also take a look at some specific interfaces, Gig 2 for example, and look at the detail on it. And we'll see that much like we saw in iOS, we have some additional configuration detail that is enabled when we configure Protocol Independent Multicast. We see that PIM is now enabled and that it's in dense mode. And as we discussed in the lecture, dense mode leverages a flooding and pruning mechanism, which is not very desirable in a modern IP multicast network. So we'll see some examples of how this behavior works here in just a moment, but we can see that we still have some of the same configuration or output information that was supplied in iOS, like MBMA mode for frame relay or ATM multipoint. So very, very similar to what we saw within inside of an iOS platform. If we do a show IP mroute, what we'll see is that we have again joined the AutoRP group, even though
in dense mode, we don't utilize RPs. Auto RP does leverage dense mode flooding for RP discovery. So we join this group by default when we enable multicast routing. And that will help us later when we configure our configuration for auto RP. Now, similar to what we did in the previous lesson for iOS, if we enable some multicast traffic on our server over connected to Edge 2, so let's connect to Edge 2 and take a look at the state that's present in that router. If we do a show IP IGMP groups, we'll see that we've got a source coming in on gigabit Ethernet 4 that is sending traffic into two multicast groups, 239.200.200.222 and 239.200 across the board. And we can also take a look at the mroute table and see that we have star comma G's for all of those that are in dense mode. And much like we saw earlier in iOS, we can also see that when we configure multicast routing, that we end up with a multicast routing table that again has multiple flags, and specifically the ones we'll focus on are dense mode, sparse mode, BiDir, and SSM. And we can see that that detail is present as well in iOS XE. Now, let's start our multicast traffic from our source, which is also connected to Edge 02. So we'll have the client join the group. And now if we do a show IP mroute, what we'll see is that we should have an entry now for that server joining that multicast group on 239.200.200.222. And this is what we refer to as state. And I don't want to belabor the point, but it's a very, very important concept in multicast. This is all an example of state. So when people talk about multicast state and how that impacts the scale of their environment, this is what they're talking about. The multicast routing table, the IGMP table, things that the network needs to track to be able to tell where multicast is going. So we can see that we've got an incoming interface list on gigabit Ethernet 4, and that we're flooding it out gigabit Ethernet 2/3. And what this ripple effect has on the network because of dense mode, we can do a show IPM route, and we'll see that we have state for these devices. We've got state for our 239.200.200.222, as well as for the actual the star comma G, as well as the S comma G for the host. Now, this particular host, this particular router, Edge 01, is not part of the path between the server that's connected to Gig 4 and the receiver that's also connected to gigabit Ethernet 4, yet we're flooding this state throughout the topology. So this will continue again and again as it floods and prunes across our multicast environment, which is why multicast dense mode is not a desirable technology for a modern IP network. If we refer back to the lecture, the real key takeaway for sparse or for dense mode multicast networking is sparse mode good, dense mode bad. So let's take one last look at our configuration. Show IP run, include PIM, and we can see that the configuration is very, very simple. IP PIM Dense Dash Mode, and that was all it took to configure Protocol Independent Multicast in dense mode on iOS XE. We're going to configure IP PIM Dense Mode on NXOS devices. So let's begin. First, within NXOS, we don't actually support dense mode, so the configuration is very, very quick and easy because there isn't any. But what we do support in NXOS is the ability to be able to still form PIM neighbor adjacencies with devices that do run in dense mode. And the reason for this primarily is for backwards compatibility for auto RP. If we recall, or as we dig further into the RP rendezvous point technology configuration sections, we'll see that auto RP leverages dense mode flooding for neighbor discovery, which means that we'll want to have our NXOS devices participate in auto RP. However, we do not have a full dense mode implementation. So let's begin just to see the configuration example. So if we start off on our data center AG2 switch, which is an NXOS device, we can do a show IP PIM neighbors. And what's interesting is that in NXOS, the CLI for various features doesn't show up in the command line until you actually enable it from a feature perspective. So we can see that doing a show IP PIM neighbors returns nothing because it's not a valid command syntax, because PIM as a process has not been started inside of NXOS. So let's begin with that, and we'll start off with feature PIM. Then we get a warning about our license will expire in 111 days. That's no problem. It's still a full-featured functionality. So we can do a show IP PIM neighbors now, and we'll see that the process isn't running because there's no interfaces that are configured to take advantage of it. So let's go ahead and configure Ethernet 2/1 and 2 at the same time for IP PIM Sparse Mode. We can see from the CLI syntax standpoint, there is no dense mode command, right? We do DE try to get context sensitive help for dense mode. It returns nothing. So sparse mode is our friend, and the only configuration option available to us in the interfaces for a PIM process. So now we can get out of here and get out of the configuration altogether and do a show IP PIM neighbors. And what we'll see is that we have PIM neighbor adjacencies with Core 1 and Core 2. And those platforms are both running iOS still in dense mode. So we do provide that backwards compatibility for AutoRP, but we don't have a true dense mode stack. So what's interesting to note too is that if I go up to Core Router 1 and take a look, I can see that I've got a PIM neighbor that just came up on Gigabit Ethernet 5, who is the NXOS platform, and we can do a show IP PIM interface gig 0/5 and see that we've got a dense mode configuration and that the neighbor appears as a dense mode device. But again, this is only for AutoRP backwards compatibility. So this is, misrepresenting the scenario. It's going to be important for you to understand that in general, dense mode is bad because of the flooding behavior that we've discussed quite a bit. And to that point, we didn't enable it inside of NXOS because really not too many customers are using dense mode, if any at all, in a modern IP multicast network. But certainly we wanted to show it from an illustration perspective that there is some support for dense mode, but it's very, very tactical for configurations specifically for AutoRP. So configuration of IP Protocol Independent Multicast dense mode on NXOS is very simple because it doesn't really exist.
Okay, so now let's talk about PIM Sparse Mode in Lesson 3.4 and why it's more advantageous than PIM Dense Mode that we just discussed. So certainly it supports both the source and a shared tree model, which we talked about earlier with regards to distribution trees, so that gives a lot of flexibility. And then we start to introduce a new concept called a rendezvous point, an RP, and we'll see this throughout the rest of the live lesson with regards to RP engineering and RP considerations, placement and things of that nature. So some of the key differences is that all of the senders and receivers rendezvous at the RP, right? That becomes the place to go. If you've ever been on a cruise, right, you have a rally point or a muster station, kind of same approach, right? When something happens, where do you go? You go to this one spot. Same approach for multicast traffic. Where do I need to go to find other multicast people? I go to the rendezvous point. Right, it's not very creatively named, but yeah. But certainly all of the senders register with the RP and they join the tree, say, hey, I'm a sender. I've got this particular multicast group that I can send out to our various receivers as they request it. The receivers all join a shared tree that's routed to the RP from their local designated router from whoever is the DR for their particular subnet. So back to a 2 subnet topology, or a 2 router in a subnet topology, one of them will be the designated router, the DR, right? And that will be responsible for sending the PIM joins and prunes northbound to the rendezvous point, so the RP isn't confused by having all this traffic coming from multiple different routers that end up being for the same source or same receiver. Definitely, sparse mode is used for wide-scale deployments. It's the most predominant protocol out there. It's really been kind of designed to be able to help provide this scale and efficiency mechanisms that customers are looking for to deploy multicast at scale. And definitely the optimal choice for production networks. If I had to choose between sparse mode, dense mode, back to sparse mode good, dense mode bad. Yeah, what does K-man logic tell me? Sparse mode is the way to go. So if we look at the same topology that we had earlier with regards to our traffic, right? We've got our receiver down at the bottom. The difference is now we have the concept of a rendezvous point there in the middle of the network, right? You can see the RP there in the center of the screen. Our receiver will signal northbound to the RP. I like to join this particular stream. And the RP can send a register towards the source, which is a unicast. This is kind of an important detail, right? We've been talking about multicast and how traffic flows, but in this, there are some unicast control plane components to multicast. This is one of those components. I need to send a join to the source to say, you know what, I've got somebody who wants to receive this traffic, hook them up. That's a register, right? That's done via unicast. So when we start to build access control lists, or if there's a firewall in the path, you need to keep that in mind too, right? Because the addressing changes for unicast versus multicast. So we send our join westbound over to the source. And then if we decide to leave the group, we would send a register stop back to the first hop router. And then likewise for our source to register, we can see that we've got the traffic that's following the shortest path tree to the rendezvous point, right? So in this case, it's going from the router on the west through the northbound router down to the RP because that is the best path. That's 2 hops away as opposed to 3 hops if I were to go to the south router, right? So now I've registered from there. And then from the rendezvous point, it flows down the shared tree to the receivers. And the reason we go through this level of detail is because, again, it's going to be important if you're troubleshooting to know where do I expect to see this traffic in my network? How do I get to the rendezvous point? Where's my source? Where's my receiver? And who's in the middle? And what kind of distribution tree am I using? Right? Where do I expect to see the traffic? Now, one of the things that can happen with sparse mode is we will do a shortest path tree switchover. So do I have to send all my traffic through the rendezvous point all the time? The answer is no. And that's a good answer. Right? We don't want to have all this traffic hairpinning through an RP just because we have to, but rather we have the ability to be able to say, you know what, I'm going to switch from the shared tree to the shortest path tree because the shortest path tree is the more optimal path to get there, and we can signal that to the network, and now our traffic is switched along that southbound path straight to the receiver, no longer traversing the rendezvous point. So once they've hooked up, they don't have to go through the rendezvous point all the time, every time, which means I don't have to scale my rendezvous point to handle every multicast packet in my network. I can layer some intelligence in the environment and say, you know what, my RP is there to do kind of the initial meetup and figuring out who is where and what and when and how. But that when it makes sense, I can switch over to the shortest path tree and have my traffic circumvent the rendezvous point if it need be. Now, depending on how I do my rendezvous point placement, it might be in the path by default anyway. It just depends on how your network topology is laid out. Typical core aggregation access type of model in a data center, if I have multicast in that space, typically I'm going to traverse that path all the time, anytime, because that's the way I get out of the data center, right? But when I look at it from a larger, wide area network, I have probably more options in how my network is laid out as to where my RP is and where that shortest path tree switchover could happen. So we'll talk about this in the rendezvous point engineering section as well. So to signal that shortest path tree switchover, we can see that by default the traffic would go through the rendezvous point, but we will signal that that we need to prune the traffic off of the shared tree and send it via the shortest path tree. So we have to tell the rendezvous point, hey, we're not going through you anymore. We're switching over to the shortest path tree. So he knows that, hey, they didn't just disappear and these guys are gone, never to be seen from again, but rather they're still there. They're just using the shortest path tree to get from point A to point B. The good news is this all happens without you having to really configure anything, right? This is part of the protocol and how it behaves on its own. So you don't have to sit there and say, okay, so how do I tell it to signal that shortest path tree switchover? It happens, right? And again, we send prune messages from the rendezvous point back to its upstream device saying we're no longer sending traffic through the rendezvous point. and we can prune that traffic off. So we're not wasting bandwidth and resources forwarding traffic that doesn't need to be forwarded anymore, right? Because it's all switching down that southbound path to the receiver. And in this case, now we've got our kind of perfectly optimal environment. Our traffic is going straight from the source down the source path tree to the receiver. So life is good. So certainly sparse mode is very, very effective for a larger topology and network. It has additional controls and capabilities to be able to scale and enhance the environment, especially over dense mode. Because we're able to send traffic down joined branches, we're able to be more intelligent about where we send the traffic. It's not flooded everywhere all the time. The network learns where the traffic needs to go and only sends it down the paths that it needs to, as opposed to sending it everywhere all the time. And we can do this all dynamically. So it's not a configuration matter where I need to go in and manually tell it to switch over. It happens by default. We are unicast routing protocol independent, and this is where the PIM part comes into play, right? I mentioned this earlier. It's kind of a concept that took a little bit of time to kind of get my head around as far as protocol independent multicast. It is its own protocol, right? We see it's got its own timers and behaviors and configuration that are unique to just PIM, but the protocol independent part of it really refers to its unicast requirements. It doesn't care if you're running OSPF or EIGRP or RIP or static routes. Doesn't matter. There's no hooks or ties between the multicast routing table and the underlying unicast table, other than the fact that your unicast has to work for a multicast to work, but there's nothing specific that says this is multicast for OSPF or EIGRP or RIP or static routes. So that's the protocol independence from that standpoint. And then certainly it provides the basis for multi-domain or inter-domain multicast routing, things like multi-protocol BGP and MSDP. We'll touch on MSDP a little bit later today. In all fairness, multi-protocol BGP is what I would consider to be more of an advanced topic, so it would be not covered in this lesson.
We'll configure iOS with Protocol Independent Multicast Sparse Mode. So to begin, we'll connect to router number 1, and we can see that there is no existing PIM configuration. By doing a show IP PIM neighbors, we'll see we have no neighbors adjacent to us. If we do a show run pipe include PIM, we've got a default configuration. So to get things started, the first thing we'll do is apply our Protocol Independent Multicast Sparse Mode configuration to the router. And as we saw with our dense mode configuration, we'll begin with IP multicast routing to start the process on iOS. And then we'll configure PIM on all of our individual IP enabled interfaces. And this will help us with our reverse path forwarding later on when we look at troubleshooting and how communications flow in a multicast domain. And we've enabled them on all of our interfaces. So now if we do a show IP PIM neighbors, we'll see that we are starting to form neighbor adjacencies with some of the other routers in our topology. Specifically, we'll focus on Gigabit Ethernet 0/1. That is our other iOS neighbor that's already configured for sparse mode. So what we can also take a look at is show IP mroute, and we'll see that we don't have much of a routing table right now. There's not much traffic going on. The traffic that is going on is dense mode, but doesn't come to us because we're in sparse mode only. We see we still have the same flags and table across the top and the output, just like we saw earlier. This is very, very helpful when looking at the configuration and seeing what's actually happening on the router at any given point in time. So because we're in sparse mode, we still have our traffic sending over on the core router 2 connected server. And what we'll see is a big difference to what we saw with our dense mode configuration. So if we do a show IPM route, all we'll see are the star comma G's, the group memberships for the multicast groups, right? So these are the 2 groups that are available to be joined, and they're sitting out there. But if we recall from the lecture, sparse mode does require a rendezvous point to be configured. Now we haven't configured rendezvous points. That'll be done in a later lesson. But know that just by enabling sparse mode, we stop the dense mode flooding that was happening. We no longer have state for the dense mode topology that was flooding through our environment earlier today, and we can verify that over on core 1, our multicast routing table is very, very small. It's just for auto RP, right? That's the only group that's being joined. Because we don't have a rendezvous point to share information or any configuration to share information on those other groups that are being advertised on core 2, core 1 knows nothing about them. So this helps illustrate the importance of rendezvous point configuration and why that's a key difference between sparse mode and dense mode that makes it so compelling. We're not learning state about things that we don't care about, and or with a partial configuration the way we have it right now, we actually aren't learning anything at all except for what might be local to us. So very, very clean and scalable routing protocol. And with that, we've configured sparse mode on the iOS devices. We can also do a show IP PIM interface gig 0/1 detail. As we saw in the dense mode configuration, we can see that we get a lot of additional details. So we can start to see things like PIM is enabled, but the difference now is that our mode is in sparse mode. And some of these other counters will become more relevant as we start looking at building our topology, controlling things, and working with it. So additionally, we can see that sparse mode is enabled, and that's probably the key component for this part of the lesson right now. And with that, we've configured iOS with a very simple and basic sparse mode configuration. We'll configure iOS XE for Protocol Independent Multicast Sparse Mode. So to begin, we'll connect to our Edge 1 router in the upper left-hand corner of our topology, and we can see that we do not have any PIM neighbors or multicast routes. So this is a vanilla box that has not had multicast configured on it just yet. So we'll begin by applying our configuration. And as we saw with the dense mode exercise, our first command will be IP Multicast Routing Distributed. Much like in iOS, it's IP Multicast Routing to enable multicast processing, and then we add the distributed keyword to take advantage of the hardware capabilities that the ASR router platforms bring to the table. We then configure IP PIM Sparse Mode on all of our IP-enabled interfaces, and this is again important for reverse path forwarding checks, that even if you don't expect traffic to go down an interface, an IP-enabled interface, you'll still want to configure Protocol Independent Multicast on it, because it's important in failure scenarios to have all of your interfaces enabled. Otherwise, things might not work the way you expect them to. So now we can do a show IP mroute, and we see we have our same flags available at the top of the table, and we can see dense, sparse, BiDir, SSM, etc., much like we saw earlier. And we can see that we've automatically joined the auto RP group as well. So that's enabled by default. What we don't see is any state from our dense mode flooding that we saw earlier. We still have a source sending and receiving connected to Edge 02. And if we take a look at Edge 02, what we can see is we do a show IPM route, and we see we have some multicast state here, right? We have a sender and a receiver. We have a sender on 239.200.200.222 and a receiver on 10.0.0.18 that are connected and receiving traffic. So in a dense mode topology, that would be flooded to our adjacent neighbors, all of our dense mode neighbors. In a PIM topology, that doesn't happen. In a sparse mode topology, that doesn't happen. So this is a much cleaner implementation for multicast, and it was why sparse mode is so much more desirable than dense mode over when choosing between the multicast routing topologies. We can also take a look at some additional output and verify that we are running in sparse mode. If we do a show IP PIM interface or IP PIM neighbor, we can see that we now have some Protocol Independent Multicast neighbors, and we can also do a show IP PIM interface gig 2, and we'll see that our mode has changed from a D for dense mode to S for sparse mode, like we saw in the earlier example. So that's a good thing. And then we can also do a detail and see that our configuration still reflects that PIM is enabled and that we are indeed in sparse mode on this interface. So that's a good double checking of all of your configuration to make sure that the change was accepted and applied, and some different ways you can validate that are reflected here in the CLI. So, but as we saw earlier, there still is no state in our mroute table for the receiver and sources over on the other side, and that's goes back to our conversation in the lecture with regards to the necessary requirement for a rendezvous point in a sparse mode network. So we do have kind of an incomplete configuration here because we've only enabled sparse mode very specifically on the router's interfaces, but we have not completed the rest of the topology requirements by configuring a rendezvous point. We'll do that in one of the upcoming lessons, but we wanted to show you what would happen as you build the topology incrementally bit by bit by bit. And with that, you've configured sparse mode on an iOS XE device. We'll configure Protocol Independent Multicast in sparse mode on an NXOS device. So to begin, we'll connect to switch DCAG01 in the lower left-hand side of our topology, and we can do some quick verifications to see that PIM is not running on the platform and that we do not have any multicast route state because of that. So this is a box that has not yet been configured for any multicast configuration. So let's go ahead and apply our configuration. We'll enter configuration mode and we'll apply our config. We'll enable feature PIM because, as we mentioned earlier, NXOS doesn't do any multicast routing or load the CLI for any of the multicast routing commands until the feature itself is enabled, and all of those commands are housed under the feature PIM package. So we'll enable feature PIM, and then we have access to our IP PIM Sparse Mode commands, much like we configured on an iOS platform. What we will now be able to see is that if we do a show IP PIM neighbors, we're forming neighbor adjacencies between our core routers and our other NXOS device on Ethernet 2/4. So if we do a show IP PIM neighbor Ethernet 2/4, we can see some additional information on it that shows that we have a neighbor adjacency, the uptime and DR priority, etc. We also can do a show IP PIM interface Ethernet 2/4 detail, or without the detail keyword, and see that we see a lot more information than we saw in a traditional iOS or iOS XE platform. We see that we don't need to have the detail keyword, that all of that is included in the output for an IP PIM interface. We can see a designated router. We can see our neighbor count. In this case, it's a point-to-point link, so there is only the one neighbor. We can see a lot of additional configuration information that is either different from what we saw in iOS and XE, or like here, VPC, SVI, things that are specific to NXOS platforms. Virtual port channel is a feature that's only available on Nexus platforms, so there are some additional considerations that need to be taken into account with that. And we can also see some error counters, which is nice for troubleshooting, to be able to see some of the additional PIM error registers that might happen in a misconfiguration, or if there's a problem on your network. So there's a lot of detail that can be found here. And because we are running sparse mode, when we do a show IP mroute, we'll see that by default there is no automatic join for auto RP like we saw earlier. So we're not going to automatically join or advertise a dense mode group. We are in sparse mode only, and all of our neighbors are also in sparse mode, so we don't have to join auto RP. We do have a default group for the source specific multicast configuration. We'll talk about that in the source specific multicast environment. But what we can see that's different from what we saw in a traditional dense mode topology is that if we connect to data center AG02 and do a show IP route, we see that we have a source that's joined on two different groups, 225, 200, 200, 200, and 200.222. That's connected to Ethernet 2/3. We also have a receiver also connected to Ethernet 2/3. So we have some multicast state again in our table that we can take a look at. But because it's not in dense mode, which is not supported in NXOS, it's not being flooded. That state information is not being flooded over to the router 01, the DC Ag 01 platform. So once we configure our rendezvous point, which we'll do in a later lesson, we'll see that this becomes a more complete configuration and we start to share some additional state between the platforms. But this is a key difference between dense mode and sparse mode. That's an important concept to understand and think about while you're building and deploying your multicast topology. One of the other things that's interesting to note too, from a show IP mroute command standpoint, we have quite a few different options. One of the ones that has been helpful in the past is to do a summary, to get a quick breakdown of the amount of traffic that's being sent on the multicast groups and some packets per second and bit rate. This is also very helpful to kind of help gauge how much traffic is being sent. So this is not just unique to NXOS, but it's also something that's available in XC and in native iOS. So we'll see those as we continue through the additional lessons. And then we can also do a show IP mroute detail and get a lot more detail on the specific attributes. And these specific attributes are going to be different on each of the platforms. But again, you get a byte counter and things of that nature that are helpful to troubleshoot and isolate. So it's not just a show IP mroute, but we can do a show IP mroute summary or detail to see what's happening. So there's a lot of good detail that can be found just from looking at the routing table. And if one last review of the mroute table that's different from iOS and iOS XE, we don't have our table of flags that we saw earlier in the in iOS and iOS XE, and XOS doesn't use the same flags. So you don't have that same table at the top that has all of the different types of configuration modes and attributes. What you'll see is that it's some of that information is reflected later on down in the configuration or in the output. So we can see that this is coming from the IP Multicast routing information base and learned in PIM. This is being learned from IGMP. So there's some additional output and detail that you'll want to understand if you're leveraging NXOS in your environment to be able to kind of get the same information that you saw in a traditional iOS platform. But with that, you've configured a simple sparse mode configuration on NXOS.
So now let's take a look at source-specific multicast and talk about how it compares and contrasts to dense mode and sparse mode that we just talked about in the previous lessons. So the idea with source-specific multicast is that it uses source trees only. So there is no shared tree in source-specific multicast. So that's a huge difference right there. It's still a sparse mode-like technology, but we do eliminate the need for rendezvous points and shared trees, as well as MSDP, when we look at MSDP a little bit later for RP redundancy. So it helps simplify the network, but the cool thing that SSM does is it assumes a one-to-many model, and it really allows us to be able to take full advantage of IGMP version 3. So if you think back to the earlier lesson on IGMP, we talked about IGMP version 3 and how hosts can signal specific groups to join, and from specific sources that they want to receive the traffic from, if there are multiple sources in that particular group. SSM is the PIM component of IGMP version 3, if you will. All right, they go together. So the idea is that our hosts are now responsible for source discovery, and this can be through the application or a web page or a content server. People say, you know what, I want to receive traffic from this particular source, but not that source. And this is a very efficient model that we see customers looking at for large-scale video distribution. So much like we talked about earlier with regards to IGMP version 3, hosts signal the requirement to join a specific group, right? And all of our content or all of our state in the network will be represented as a S, G as opposed to a star, G. We mentioned earlier that that star, G, S, G notation refers to source and group put together. For sparse mode networks, typically you'll see star, Gs. You'll see a receiver a source register with a group, and you'll see a star comma G state propagated across the network. And you'll see this in the rendezvous point, and you might see it in some of the intermediate routers. With SSM, we eliminate that concept. And the idea with the star being is that it's an asterisk, a splat, whatever nomenclature you use for it, it can be anything. It's a wild card. Whereas with source-specific multicast, we're not just randomly joining groups. We are joining very, very specific groups. I want to receive traffic from this particular source on this particular group, and that's it. So it's much more prescriptive as to what traffic I want to see. So you'll see S comma G state as opposed to star comma G state in an SSM environment. So the last hop router will send the S comma G to the source directly as opposed to a star comma G northbound to the rendezvous point. So it's a cleaner model from that standpoint. And then, as we mentioned earlier, there is no shared tree, right? It's all specifically source path tree to the receiver, because now we know exactly who we want to talk to. We're not talking to the rendezvous point and trying to sort all this stuff out and to do a switch over, but rather, let's just go talk to the man, right? Tell me who to go talk to. I'm going to go talk to him. Life is good. And then only that specific flow is delivered to the host. And it also simplifies our address allocation, right? So now, we mentioned earlier that if you have two different sources sending to the same group, but sending different content, that can be confusing for your host, right? So customers will typically allocate one particular address for this particular content, one particular address for this content. If you draw the analogy to TV channels, channel 1 is multicast address 1, channel 2 is 2, and so on, right, down the list. SSM allows us to be able to say, you know what, I can have everybody join channel 1 on dot 1, but then have the intelligence say, only send me the content for channel 1 from this particular host, from this particular source. So I can be much, much more granular. Allows me to be able to be very conservative with my address allocations. I don't have to allocate 100 addresses to have 100 different channels of content out there. Not going to have one address with 100 different channels of content and utilize SSM to be very granular as to what's inside. And that requires the intelligence both on the network as well as on the receiver side to say, I only want that particular content. So, pretty cool capability. So as we mentioned, it does use the source trees only, and that the hosts are responsible for all of the source and group discovery. This is typically done in the application, right? So it's not like your user has to manually say, I want to join this group on this particular subset to receive the content. Usually it's a matter of clicking a page, clicking a link, and having it join that particular group. So very, very specific from that standpoint. And it definitely solves multicast address allocation problems, although not too many customers scale to the extent where they run out of multicast addresses. /16 is pretty big, so you can do that. But then it can also help prevent certain different types of denial of service attacks. You don't have to worry about somebody injecting bogus traffic into your network, right? So you can be very, very specific about which source as opposed to just somebody randomly joining a group and pumping out the wrong information, but rather being able to say, this is a particular trusted source that I can utilize.
We're going to configure IP Protocol Independent Multicast source-specific multicast mode on a Cisco IOS device. So to begin, we'll connect to our core iOS router, core 01, and we already have enabled sparse mode on this particular platform in the earlier lessons. And we can do a quick show of the configuration and see that we do have some multicast groups that are being sent. And we can see that we've joined the default group for AutoRP. We're seeing a group on 239.1.1.1 that's being advertised as well. And we can do a show IP mroute and see that we have state for this. We see just the star comma G. Nobody else has joined this group. It's just being sent by the source. And we also, because we were talking about configuring source-specific multicast, we want to look at the IGMP configuration. We mentioned in the lecture that IGMP version 3 is required for a source-specific multicast configuration. And our default configuration on all of the platforms is IGMP version 2. So if we do a show IP IGMP interface gig 0/6, we'll see that we are indeed configured for IGMP version 2 and that it's enabled on the interface. So this is going to behave in traditional IGMP version 2 mode, although that configuration will soon change as we enable source-specific multicast. And part of that prerequisite for an SSM topology is that we'll want to enable IGMP version 3 as well. And that's done so that we can support the very specific attributes that we talked about in the lecture with regards to how a host requests a very specific group to join from a very specific source, hence the name source-specific multicast. So let's go ahead and apply our configuration. And what we're going to do is walk through this. So we entered configuration mode. We configured IP PIM SSM default. This just defines the default range of addresses that are used for source-specific multicast. And out of the box, that is the SSM group, right? So typically that's not something that is used by ASM. And then we see on our gig 0/6, we've enabled version 3 of IGMP. And because we don't have a version 3 compliant source or receiver, what we're actually going to do is have the router join the source-specific multicast group so that we can see this type of state that's built with an IGMP version 3 and source-specific multicast receiver. So let's start off by taking a look at the show IP IGMP interface gig 0/6, where we can see that our interface has indeed been configured to version 3, and also some new output. We have explicitly told our group to join, our interface to join 232.1.1.1. So if we now look at the output of show IP mroute, what we'll see are some new details. We see that 10.0.0.6 has indeed joined 232.1.1.1, and what's new that we want to point out is the lowercase s, right? So if we refer back to our flags up here, we can see that indicates a source-specific multicast group. So this is a quick tell or indicator that this is an SSM configuration. If we also do a show IP mroute, we can see that there's an option to just display the source-specific multicast configuration. So we can see the route table for just SSM by doing a show IP route SSM. So that's a pretty nice command when you start looking at a mixed configuration environment where you might have source-specific multicast for some platforms and traditional ASM, any source multicast for the other devices in your network. It's nice to be able to easily parse that information out from the route table. And as we mentioned earlier, we can do a show IP mroute summary and see some additional configuration information, and similar to what we saw in XOS. And we can also do a show IP mroute verbose and see some additional details here, right? So we can see some additional information for the multicast routing table. So with that, it's a pretty straightforward configuration, and now we've configured source-specific multicast on an iOS device. We'll configure Protocol Independent Multicast in source-specific multicast SSM mode on a Cisco IOS XE device. So first we'll begin by connecting to our edge router, the upper left router in our topology, and we can see that we already have the router configured for PIM. We can do a show IP PIM neighbors, and we'll see that we have some adjacencies. We can also do a show IP IGMP groups, and we can see that we have some traffic that's being sent or being sourced from a host on Gigabit Ethernet 4, advertising on group 239.100.100.100. And we also see some state in our mroute table. Now, because we're going to start to use source-specific multicast, one of the things that we'll need to do is configure interfaces for IGMP version 3. And if we look at our existing configuration for our interface that we'll work with, Gigabit Ethernet 4, we can see that our interface is configured in version 2 mode right now. We can see that that's our current version, and we're going to go ahead and modify that configuration to reflect version 3 to allow IGMP version 3 joins to happen, which will get us our source-specific multicast configuration. So we can apply our configuration now, and we can see that we've configured IP PIM SSM default which tells the source-specific multicast configuration to use the default IP range for a source-specific multicast. And then we've changed our configuration for interface Gigabit Ethernet 4 to be a version 3 interface for IGMP. And we can see that that change has been applied by doing a show IP IGMP interface Gig 4. And we can see that now we are in version 3. Now, one of the other things we've done is we've also configured the interface to join a group 232.2.2.2 with a source of 10.0.0.6. And this is a source-specific multicast group. So now what we can see in our MRoute table is that we've got some new state, and the new state that's in there is specific to our source-specific multicast config that we just entered for joining a specific group. And we can see that we have a flag with a lowercase s over here that indicates that it is a SSM group. So we have specifically joined that group from that source, and we can also do some MRoute commands to only show us the source-specific multicast MRoute tables. So this is convenient when you have multiple multicast topologies. Maybe you're running ASM and are adding SSM to the configuration. You can differentiate the multicast routes pretty quickly by using the show IP route SSM to be able to just see the SSM specific routes. And like we saw on iOS native, we can also do a show IP MRoute summary and see some additional detail here, and then also show IP MRoute count and get some statistics. So some pretty interesting things that are helpful to know for troubleshooting, to be able to review very, very specific configurations. Also, one last point of note that's good to know for the show IP MRoute count is that it also shows us how much memory is being used. And we can see that this grows as we add state to the topology, which again is a consideration we discussed in the lecture with regards to how much state you have in your topology and how that impacts convergence and resources on the router. So, but with this, we've configured a very simple source-specific multicast config in a Cisco IOS XC device. We'll configure NXOS to support a Protocol Independent Multicast source-specific multicast environment, SSM. So we'll begin by connecting to our data center AG01 switch in the lower left-hand corner of our topology. And this switch is already configured for Protocol Independent Multicast Sparse Mode, PIM Sparse Mode. So if we do a show IP PIM neighbors, we can see that we've got our multicast topology with PIM neighbors northbound, our two core routers, and then laterally to our data center AG02 device. We also have some IGMP state in the network from a version 2 source that's connected to the switch as well on Ethernet 2/3. So we can see that we're transmitting on 225.100.100 and also 101. You can also take a look at the MRoute table and see that we've got some multicast data in here as well, star comma G's specifically for those particular groups. So now we're going to go ahead and configure our device to support SSM, and to do that, one of the things we'll need to do is configure the interface to support IGMP version 3. As we mentioned earlier, IGMP version 3 is a prerequisite to support source-specific multicast environments, so that the receiver can specifically request a specific stream from a specific source and transmit that to the network and have the network join it to the appropriate group. Now, this is a bit of an impartial config because we don't have a real IGMP version 3 source, so we're going to force the router to join a SSM group, but the effect remains the same. So let's go ahead and first take a look at our interface, and we'll see that if we do a show IP IGMP interface Ethernet 2/3, that we are configured for IGMP version 2, which is the default on the NXOS platforms, and all of our various statistics and things that we saw earlier when we were reviewing the configuration, VPC configuration or VPC specific information as well for NXOS platforms. So now we'll go ahead and apply our configuration to Ethernet 2/3. Well, we see when we review the configuration that's applied, we have a default line in here for IP PIM SSM range 232.0.0.0/8. This just defines a specific range that we want the NXOS platform to handle for source-specific multicast. This is the industry standard for the multicast SSM range, so nothing terribly surprising or shocking by this configuration command. What we do add to the configuration under Ethernet 2/3 is IGMP version 3, and then we also, this is forcing the router to join a specific multicast SSM group. So we'll go ahead and apply that configuration. And now if we take a look at our IGMP interface Ethernet 2/3, we can see that we're now in version 3 mode. And also, if we do a show IP IGMP groups, we'll see that we still have our IGMP version 2 groups that are operating. We also have now a new one, 232.333. This is the interface that we specifically told, or the group that we specifically told the interface to join. Therefore, it's designated as a local in the state table on Ethernet 2/3. And what's interesting to see is that it shows us both the group address as well as the source. So the SSM table shows us very, very specific details here. And we can also see this reflected in the mroute table by doing a show IP mroute. We can see that now we've got some additional state in here as well, specific to this particular interface. We see 10.0.0.30 and joining 232.3.3.3. So we know that we've got a successful join here. And we can see that that it was learned via IGMP, and that it is it's now in the state table. Additionally, like we saw on iOS and iOS XE, we can do a show IP mroute summary, and we can see statistics and counters for the different groups that are transmitting and the different sources. And then also we have the option to be able to do detail to see some additional information regarding each of the entries in our state table. So we can see the total number of routes, the number of specific S, G entries in the table. So there's a lot of detail that's reflected here that can be useful when you're troubleshooting your network or trying to figure out what normal looks like. And then we can see here's our new state that was just created for our SSM demonstration. So with this, you now see how you can configure SSM on a Cisco NXOS device, and that it's not very difficult to do.
Okay, so now let's talk about Protocol Independent Multicast Bidirectional mode, or BiDir mode, BiDir. Some of the concepts for BiDir are drawn from what we already know from typical rendezvous point and sparse mode deployments, right? So we're utilizing the same source tree for traffic towards RP to the receivers, and the benefit being that I don't have to build S, G state. So we see BiDir being used in large-scale networks where I either am scale constrained, where I don't want to have all this different state floating about my network. I want to just have star, Gs through my environment, so less state to track, faster convergence, things of that nature. And we will follow a shared tree all the time. So now I've got a very finite path to troubleshoot and operationalize my network, right? Because I no longer have a shortest path tree switchover, so I don't have traffic that's veering away from the rendezvous point and going down a different path. Everything is stuck to the same path. And again, this is one of those decisions where you have to understand your application requirements as to whether or not BiDir makes sense for you to use, right? So certainly the benefits of having less state for a lot of our customers is a key benefit. And we're starting to see more adoption of bidirectional PIM in networks across the world. So because we are utilizing the same shared tree, we certainly can violate our STAR, G RPF rules, which kind of violates what we talked about earlier, but bidirectional PIM is one of those exceptions to the rule. There's always an exception to the rule, isn't there? Anybody who has kids knows that there's always exceptions to every rule, depending on the various scenario. But the idea is that we can still accept traffic on outgoing interfaces. So you have to be very, very careful to not interject a loop in your network. And this is where I guess you kind of get to earn your keep as a network administrator, knowing the topology, knowing the application, knowing the requirements, and being able to engineer a solution that meets the requirements without cratering the network and causing a huge outage. So we do have a new role called a designated forwarder, who is responsible for forwarding traffic up the shared tree. And these are typically roles that are defined in the routers at the edge, right, of the topology, and then are going to be able to accept data on all of their interfaces and their outgoing interface list, the OIL, that we'll see in the CLI, and then send it out to all of the other interfaces, including the designated forwarder, which is the perfect example of the violation of the RPF check rules, right? Typically, we wouldn't do that with RPF. Some of the benefits that BiDir brings to the table, though, is that we're utilizing shared tree only. So again, it mitigates the amount of state, or minimizes the amount of state that I utilize in my network, which is typically an important consideration for a multicast deployment. All of our source traffic flows up and down the shared tree, so we have a very good understanding of where multicast traffic goes in our network as a whole. And certainly the fact that it eliminates all that state can help from a convergence standpoint as well. All right, I mentioned earlier, I used to work for a large global financial. Some of our multicast state in our routers was upwards of thousands of star, G and S, G entries, which for our requirements was spot on normal. That was what we expected. The challenge that we frequently saw was that if there was a failure in our network, the unicast routing would converge very, very quickly, right? We had all kinds of cool technologies to leverage, whether it was bidirectional forwarding detection and aggressive timers and all these other neat things that we could do. Our multicast was always the last thing to converge. And part of that was because it relied on the underlying unicast infrastructure to converge, but also that amount of state took time to propagate, CPU cycles and data-driven events to create the state for the multicast topology to converge as a whole. So certainly the concept of introducing something like BiDir can be very, very attractive to an organization that needs to minimize that state in their environment, and being able to eliminate all the star or S, Gs and just move to a star, G driven environment. So food for thought, something to keep in mind. Definitely allows many to any applications to scale. And really, you could have virtually an unlimited number of sources, because as long as they join the group, who cares, right? It's pretty good to go. I had a manufacturing customer who had a penchant for using multicast for their applications, and really their application teams, of course this never happens to you guys, but their application teams didn't talk to the network teams at all. Yeah, that never happens, right? Not in your environment. It's all one big team, group hugs, and all that kind of fun stuff. But the reality was that they didn't realize that the application teams were using this much multicast until they turned on multicast on their switches, and all of a sudden they had all this state that just started populating and flooding the environment, and they were just astounded, right? So definitely for that many to any applications, that was exactly what they were using. They were using their manufacturing application and just setting up multicast left and right, and it worked great in the data center. But when they turned on multicast as part of a broader project, they found all these Easter eggs and hidden gems, if you will, in their network. So definitely every time I say that, many to any, that's exactly the scenario I think of as the moment they turn on IP multicast routing and what's all this? It was pretty cool.
We'll configure a Cisco IOS device to support Protocol Independent Multicast in a bidirectional mode, or BiDir. To begin, we can see that our existing router, core router 2, in the middle of the right-hand side of our topology diagram already has some basic configuration for PIM. We have PIM Sparse Mode configured, and we are defaulting on our IGMP configurations. So we'll be able to see here that we have sparse mode on all of our interfaces. We can do a show IP PIM neighbors. See we have various neighbors connected to the router platform, and that we do have some state in our table right now. We've got a multicast source connected to Gigabit Ethernet 0/6 who is joining two different groups, and we see the star comma G state for that. Now, in this specific configuration, we're just going to enable support for bidirectional PIM, and what we will see is really not a lot of change to the multicast routing topology right now because we don't have any RPs configured. We'll configure rendezvous points in lesson 4, but what we would see if we did have rendezvous points, and we'll see this later, is that our state will change from star comma Gs or S comma Gs to star comma Gs. So we will get rid of the specific multicast state that we track in traditional sparse mode topologies for every source and receiver in our network, and just move to a star comma G specific state. That's one of the big advantages of bidirectional PIM, is the reduction of state in the network topology. So let's begin with a simple configuration, and we'll see that to enable bidirectional PIM is simply just a one-line command: IP PIM BiDir-enable. We can get out of configuration mode. Then if we do a show IP mroute, we'll see really nothing has changed because we don't have any specific S comma G state in our network that we need to that would have been converted. We'll see that as we go through the rendezvous point configuration section, but it's a very, very simple configuration to enable BiDir in your network. As we mentioned in the lecture, though, it's important to understand what your requirements are, because there are some considerations with bidirectional PIM. So it's not just the easy button to minimize state in the network, but it does require some thought and planning to make sure that you are aware of the considerations for enabling bidirectional PIM. But with this single command, you've enabled bidirectional PIM support in your Cisco IOS device. We'll configure a Cisco IOS XC device to support Protocol Independent Multicast in a bidirectional configuration mode, or PIM BiDir mode. So we'll begin by connecting to Edge Router 02, which is our router in the upper right-hand corner of our topology. And we can see that this router is already configured for PIM. We can do a show IP PIM neighbors. And so we have PIM adjacencies. We can do a show IP mroute, and we'll see some multicast state in this environment, in this box. And we can also do a show IP IGMP groups and see that we've got some multicast sources that are directly connected to this particular platform. Much like we saw in iOS, the enablement of bidirectional mode of PIM BiDir mode, is very, very straightforward. So we'll go ahead and apply that configuration. And we can see that it's just a matter of the same syntax: IP PIM BiDir-enable. And what we will see is really not a lot of change right now, because we don't have any rendezvous points configured, and we'll configure rendezvous points in lesson 4. But what we will see when that happens is a reduction in multicast state of S comma G's, state like this, in the router. Now this one is still reflected because it is local. So because it is local, it's learned on the router. But in a rendezvous point configuration, normally this state would also be out at the rendezvous point. What we'll see with bidirectional PIM is that state would not leave this box, but rather we would just be following the star comma G multicast topology to get from the source to the receiver. So with that, we've got a pretty straightforward configuration for PIM bidirectional. Now what we can see that is kind of a good indicator of the bidirectional capabilities in our network is if we do a show IP PIM neighbors, we'll see that some of them are starting to advertise that they are bidirectional capable, right? So now we see that our neighbor on Gigabit Ethernet 2, which happens to be our iOS device, that we just configured a little bit ago is now advertising that it's bidirectional capable. So that's an important consideration with PIM, is that we do advertise these capabilities amongst the devices so that they know how to behave with the either conversion from shortest path tree to shortest tree, or the source tree, or how they deal with multicast state in their platform. But we can see just the simple single one-line command IP PIM BiDir-enable was all it took to enable BiDir mode in iOS XE. We'll configure a Cisco NXOS device to support Protocol Independent Multicast in bidirectional mode, or PIM BiDir mode. Now within XOS, one thing that's interesting to note is that it does configure a little differently than a traditional iOS or iOS XE device. So specifically, when we say that we want to configure bidirectional PIM, there is no command like IP PIM BiDir-enable like we saw on an iOS and iOS XE device, but rather the configuration is actually applied to the rendezvous point configuration. So we won't actually see any configuration commands in here, because we'll do all of that when we get to the rendezvous point configuration section. But I did want to show that there is no support for the PIM BiDir-enable command. What we'll see is that we do have a BiDir RP limit, which limits the maximum number of bidirectional PIM RPs for a VRF, but there is no IP PIM BiDir-enable. So the syntax all falls at the end of our rendezvous point configuration. So not to be a tease, but we'll see that in the next lesson 4, where we talk about rendezvous points. But I wanted to show for completeness that there is no specific configuration for BiDir inside of NXOS the way that there is for a iOS or iOS XE device.
So in summary, with regards to PIM, there are a couple of different flavors. Certainly sparse mode, good; dense mode, bad. I think we hammered that home earlier pretty darn well, and you get the benefits of that. Certainly dense mode, flood and prune, might work in most environments, but it's typically suboptimal behavior that we want to try to avoid. Sparse mode is our most commonly seen flavor of PIM that's out there, and then followed by SSM, which does require client support on the senders and receivers, as well as the intermediate network. Typically utilizes SSM in the network. And then BiDir, where we get rid of all of our S, G state in the network and pin everything to shared trees. And certainly an important note, and I mentioned this a little bit earlier when we were looking at IGMP, but there are some specific platform considerations that you'll want to take in mind. If you have devices that are specifically running NXOS in your environment, you'll want to understand the considerations with regards to SSM and BiDir specifically in a VPC configuration. All right, so that we couldn't really include those in the entire lesson, because then we'd have to get into an entire dissertation on VPC and what it is. But certainly know that you'll want to understand the considerations for SSM and BiDir in a VPC domain. So we'll begin with lesson 4.1, rendezvous points. And when we talk about rendezvous points, certainly they are the focus point in a sparse mode or BiDir network for network devices to be the root of a multicast group. They are where the traffic will flow through into in those types of domains. It can be common amongst all groups or unique per group. And this is important, especially when we talk about rendezvous point engineering. It might be advantageous for me to have a rendezvous point be in one of my core nodes for a specific group, but then shift and have a rendezvous point for a different set of groups someplace else in my network. So now I have options to how I can place my rendezvous points in my environment depending on my requirements. So we have that flexibility to be able to define different RPs. So it can be a global RP for everybody, or an RP just for a specific group. Certainly it's required for PIM Sparse Mode and bidirectional PIM, so we'll definitely have rendezvous points in those topologies. And really, depending on the deployment, it may or may not be critical in the success. Certainly it's going to be important for initial setup, but then after that, we'll see how they play out. So when we talk about placement, There are certainly some considerations for placing a sparse mode rendezvous point. Certainly the first few seconds when the streams are starting and when devices are joining the multicast group, the rendezvous point is very, very important, right? Because traffic is going through it. We saw the PIM registers and the PIM joins earlier in the previous lesson that talked about how traffic flowed through the rendezvous point before they switch over to the shortest path tree. So for those specific cases, RPs are very, very important to the flow of traffic in the network. If we're using a shared tree, like we do in PIM BiDir, bidirectional PIM, then certainly the rendezvous placement is very, very important, right? Certainly from a BiDir standpoint. When we talk about bidirectional PIM specifically, some of the considerations is going to be key because it's always having the data flow through it. It becomes part of that data path. So now it becomes, if you look at it from a failure domain standpoint or a change domain standpoint, being able to have the rendezvous point be highly available as well as resilient is going to be important, because if the rendezvous point fails, multicast traffic will fail as well. So when we talk about the different ways we can discover rendezvous points, there are options we have available to us. Certainly static RPs is probably one of the most commonly deployed, and we'll see in the CLI section how static RPs are configured, but know that just from its name, it's implying that you are configuring static RPs on each individual device in your network. If I only have 5 devices, it might not be that big of a deal, right? Static RPs, there's nothing wrong with them. If I have hundreds or thousands of devices, static RPs can be a challenge. How do I manage and maintain that? How do I make sure my configurations are consistent and that my data is flowing properly across my network? Auto RP is a technology that can be used for RP discovery. We mentioned Auto RP just briefly earlier in the IGMP section when we talked about one of the default groups that we saw register. We'll get into much more detail on Auto RP in the upcoming slides, but know that that is indeed a good option for rendezvous point discovery. Another one is Bootstrap Router, BSR. Those are considerations as well for being able to, or different methods to be able to learn about various rendezvous points in our network. So let's start off with static RPs and talk about those. So certainly from the name itself, it's manual configuration. It is the most common, right? Most of our customers don't have massive monster networks. Most networks are relatively finite in scale and usually under a single group's control. Maybe it's just you, right? You're the network administrator. You get to be the ones typing in all the commands and CLI at dark 30 in the morning when your maintenance window is. Typically a static RP is seen in that kind of environment, right? Where it's easy to maintain that configuration consistency across our entire network. Every PIM-enabled device on the network has to be configured with an RP. And that's going to be important, right? So imagine I'm a PIM router, I receive a PIM join, I don't have an RP, I don't know where to send it. So I have to have that. In a static environment, you're configuring that static RP. One of the things to keep in mind with static RPs though is that there is no RP failover unless you use Anycast RP. And we'll talk about Anycast coming up when we talk about RP redundancy, but know that that's a consideration. If I have statically configured something in my network and it's on all of my devices, all of my network devices, and that device fails, how does my network fail over? Am I just scrambling to restore service to the failed device that was the RP? Or do I want to have some intelligence in my network to either find the information it's looking for someplace else, which is the Anycast model, or I just wait until I restore service? If I had to choose, I'd probably go with a bit more dynamic because I don't want to get that phone call at 3 o'clock in the morning, because that thing's never failed during the day, right? They always fail in the middle of the night when you're asleep. So I want to be able to have my network be a little bit more self-healing and be able to route around a particular node failure without causing a major challenge for my organization. One of the options for RP discovery is Auto RP. And when we look at Auto RP, all the routers will learn the RP address automatically. Pretty creative name, Auto RP. They learn it automatically. Let's talk about how they do that though, because this is where it gets a little interesting based on what we talked about earlier. There are 2 IANA assigned groups specifically designed for AutoRP. We mentioned those in lesson 1, but we'll certainly review them now. The first one being 224.01.39. This is the Cisco Announce group. So AutoRP is a Cisco specific technology. Cisco certainly spends a lot of money having super smart people doing R&D and developing innovations in the networking industry. EIGRP, HSRP, et cetera, are probably common examples that most people are familiar with from a standards or a Cisco proprietary protocol that has become either more public or is out there a lot more. AutoRP is another one that doesn't get a lot of press, but it's certainly an example of a Cisco proprietary technology. So 1.39 is the Cisco Announce. 1.40 is Cisco Discovery. So what will happen is that all the routers will join that .40 group to learn the mapping agents. And we'll talk about mapping agents and what their role is, but they're part of AutoRP. So if I'm a router in a multicast network, and I'm either configured for AutoRP or it's enabled by default, as we saw in the iOS CLI example earlier, then I'm going to automatically join this group and I will be able to learn the mapping agents. That's part of how AutoRP works. So the idea is that within any multicast domain, there is only one mapping agent, right? Kind of the master router who's in charge of the AutoRP configuration. Certainly we can configure backup RPs so that there is some sort of failover if the mapping agent fails, but in general, the mapping agent is a role that's done and performed on one router or switch. And I use router, but it can mean a layer 3 switch as well, right? So don't get too caught up in thinking it's a 2501 or something else. It could be an Nexus 7000, it could be a Cat 6500. To me, that's a router, right? So certainly those devices can be configured for backup RPs. And then all the routers in the domain receive the RP mapping for where the RP is, right? So the candidate RP mapping, that's the CRP, as candidate mapping. So, and then the router with the best match will become the auto RP, will become the RP for that particular group. So this is a process that's done automatically by all the routers. They've got an election process. They've got a process to determine who's going to be in charge once it's all said and done. Certainly you can configure it, right? You can influence it, much like anything else. There's always plenty of nerd knobs to either hang yourself or configure your network to the optimal state. You get to choose which way you go. We see plenty of customers doing both. So get these frantic calls, hey, it's not working the way I wanted it to. Typed in the wrong commands, right? So, but then you're also able to utilize AutoRP with administrative scoping. So as a technique to allow me to control where my multicast traffic goes in a broadly distributed domain, if I follow a plan to deploy my RPs and understand my multicast layout and topology, I can also tie that into AutoRP. So I can have AutoRP for this part of my network or that part of my network and have them be different. So I have flexibility and options. The mapping agent is there is only one that's active in the IP multicast domain. If anybody's watched Highlander, there can be only one. This is the only one mapping agent for a particular multicast domain. And again, we can have all those routers be administratively scoped. So when we look at the way a AutoRP domain would work in dense mode, certainly the RP announcements are all flooded to the 224.01.39 group, right? So we've got our candidate mapping agents and our RPs, candidate RP 1.1.1.1 on the left, RP 2.2.2 on the right, and then we have mapping agents up at the top, 3.3.3, 4.4.4. Hopefully these aren't addresses you're using in your network unless you own the address space. Just use it with caution. But the idea is that all of the routers will join those announce groups and those discovery groups to be able to determine who is the appropriate mapping agent and where our candidate RPs are, and then determine who is the RP, who is the one, right? So in this case, that's flooded across the network, and that's where there's some requirements for having some dense mode activity, even in a sparse mode domain with AutoRP. Right? Sometimes you'll hear that referred to as dense mode fallback. AutoRP will still flood this traffic amongst the routers, but it's specific to these groups. So it doesn't necessarily have the same adverse bad behavior as it would if you're talking about just a generic multicast group, because it's designed and specifically for the protocol that we're using, in this case AutoRP. It's not so bad. So something to keep in mind as well. But then one of our mapping agents is elected as or candidate mapping agents is elected as the mapping agent, and then he's the one who will pick the RP. When we compare and contrast this to BSR, Bootstrap Router, this is another RP discovery technique. This one's industry standard, right? So it's not just a Cisco thing. We can have multiple candidate BSRs, again, to provide backup and have our candidate RPs send their announcements to the BSR. And then all of the RP announcements are configured in the RP set, right? And then that's distributed to all of the routers that are part of the BSR domain. So they'll send the entire RP set and IP addresses through BSR, and they're flooded on a hop-by-hop basis across the network. So again, similar to kind of that dense mode model, we have to have a way to force this information out or spread it, disseminate it, whether they wanted it or not. They participate in the multicast groups, so they get it. And then all routers will select the RP from the RP set, and they all use the same algorithm, right? So you can influence that certainly through the CLI as to which ones you want to be the RP. But something to keep in mind too is that BSR can't be used with admin scoping, so you lose a bit of flexibility from that standpoint, which is one of the reasons why AutoRP was kind of invented, was to provide that additional flexibility and control, especially in a large multicast domain. Those are some discovery techniques. Certainly, by and far, the most common, as I mentioned, is static RPs, and then followed by AutoRP, and then BSR. I haven't seen a lot of. You got a question?
Yeah. How can you guarantee that the same selection algorithm is used in all routers? I mean, your influence of certain routers, but your entire network may not be your own in a let's say a video distribution environment.
Yep, so the question is, how can you ensure that they're using the same algorithm? That's part of the BSR protocol. Okay. So if they're using BSR, they have the same algorithm. It doesn't get updated or changed with releases. Okay. So it's very simple. Yes?
Are there multiple mapping domains? I mean, for example, if one, it seems like that might be a point of failure. If you had, like, for example, you got failover for the RP, you've got one mapping agent, or you have multiple mapping agents.
Yeah, so the question is, can I have multiple mapping agents? Right now, there is only one mapping agent, but you can have multiple candidate MAs, which would be eligible to take over if the primary mapping agent dies. And that's part of the BSR protocol, is to communicate that, hey, this guy's dead, he's timed out, he's no longer advertising the RP sets, somebody else needs to become the new mapping agent. So it can be self-healing from that standpoint, yeah. So now let's shift our focus a little bit and talk about rendezvous point engineering and RP redundancy specifically. How can I make my RPs redundant? A couple different ways. Probably the most common way is to utilize RFC 3446 Anycast to be able to provide that RP redundancy. And the idea with an Anycast is that I'm going to have more than one RP for the same group. Right? I need to have more than one to be redundant so that if one fails, I've got somebody to take over. The cool thing is, and this is where it kind of can mess with your mind a little bit, is that they both have the same IP address. So then my routing protocol will tell me which one is the closest one, right? Based on the IGP metrics, whether it's OSPF or EIGRP or whatever, I will naturally flow to the closest Anycast RP device. The idea is that they'll utilize the interior gateway protocol, the IGP, to figure out which one is closer. And then I utilize another protocol, MSDP, Multicast Source Discovery Protocol, to be able to share mappings between the two RPs, so the two Anycast RP members. So as one Anycast RP device learns of a source, he will send that over to the other one, so that they both have the same table, if you will, of who has which auto or any of the various mappings for the multicast domain. Certainly, the biggest advantage with Anycast, and this is why most customers typically deploy Anycast for their RP redundancy, is because it has very fast RP failover. I'm following my interior gateway protocol. Nothing has to change on my end devices, right? I still configure a static configuration saying my default RP is 10.0.0.1. There just happens to be 2 or 3 different people that are 10.0.0.1 on my network. So now my routing protocol just says, oh, hey, this one's gone. Let's go talk to the other one and another device. Very, very fast failover. So seconds of a failover as opposed to much longer. And we also don't have any dense mode fallback because our RP address is statically assigned. I mentioned earlier that with auto RP and BSR, there is still that dense mode fallback that happens to be able to have our routers join the Cisco announce and the Cisco discovery groups. That goes away with Anycast because it's a static RP mapping that's been enhanced, if you will, with auto RP. So I'll have one command line entry for Anycast and then have Anycast configured on my 2 Anycast devices and have them share that state with MSDP. Very, very slick stuff. From a disadvantages, there's always pros and cons, and you as a network administrator get to choose your own adventure as to how you want this to proceed. But certainly there is more configuration, right? Because you are typing in additional commands inside of the Anycast device. You're also configuring MSDP, so there might be some configuration there. And you are putting a static RP definition on every router. So with auto RP, you don't have to, right? You don't touch the other routers. You let auto RP do its thing. Whereas with Anycast, you have to configure them on each one. But in my opinion, the pros certainly outweigh the cons, and that's a big part of why Anycast is the most widely deployed RP redundancy protocol that we see out there. Now, we mentioned MSDP, and we haven't really talked about it a whole lot, but the idea with MSDP is yet another RFC to lull your kids to sleep at night, RFC 3618, and really the impetus behind MSDP was to provide a way for multicast routes to be learned between different routing domains. So start to think about like internet type stuff, multiple BGP administrative domains. I have my particular AS and I need to talk to another AS. I configure a protocol between the two of them, BGP, to exchange routes. MSDP is like BGP for multicast. Kind of a loose analogy, so keep that in mind. Don't get too far down the rabbit hole of I got a 12-step process to determine routes and weights and communities and metrics and all the fun things that BGP brings to the table. MSDP is designed to be pretty simple, lightweight technology for customers to use. But that was originally what it was designed to do. Now we start to leverage MSDP in a Anycast domain to be able to share multicast source and group mappings between the different Anycast routers. That's how they share the state, so that way there's a fast failover. If one fails, the state's already over here. He knows where those groups are and who's a member of them. It doesn't have to have a data-driven event to learn where those sources are. So my convergence is very, very fast. Certainly commonly used with Anycast RP. I mean, that's the only time I've seen people do it. I haven't seen customers utilize MSDP with an internet-facing connection, although I'm sure there are. I haven't talked to every customer in the world, right? So, but this is a very powerful and common combination of technologies. Anycast plus MSDP make for a great combination for RP redundancy. Now that said, I've waved the flag for this is my favorite, RP redundancy. Let's talk about some of the considerations that you have to keep in mind because, as always, there's pros and cons, right? So one of the common things that we recommend customers to do is to utilize a new loopback or a unique loopback just for the Anycast ID. So you'll see on the 2 Anycast routers, typically you'll see loopback 1 or loopback 10 or something else that's not normally used. Most customers will utilize loopback 0 for router IDs and SSH, TACACS, source IP addresses and things of that nature to make their life easier. Most customers don't have more than one loopback. With exception, right? But certainly the idea was that you want to have a separate one, a separate loopback just for Anycast. Makes troubleshooting much, much easier at ODark 30 so that you don't have to say, okay, so wait, is this the loopback 0 or is this a different loopback? And wait, that's my router ID. Well, no, it's not my router ID. It becomes very confusing. This makes it very easy. Loopback 10 is always my Anycast ID. If I see a router with loopback 10, he's probably talking Anycast. Probably also has MSDP in there as well, right? So now I know that it's different. Certainly, some of the things to worry about with router ID, some of these are a little dated, but if you think about from a standpoint of utilizing the one with the lowest IP address for the Anycast, we'll minimize it being used for the router ID. Or you can use a secondary address. Personally, I'm not a fan of secondaries because most people don't look for them and expect to find them in a network. So the recommendation I make is to utilize the bottom command, utilize the router ID commands that are available in your routing protocol to specify the router ID. Is it a little bit more work up front? Yes. Is it worth it when it's all hitting the fan and things aren't working the way they want to? Yes. So in my opinion, you're trying to set yourself up for maximum success when things don't work the way they're supposed to. By specifying the router ID, I always know that that is my router ID and it's not my Anycast ID. So pretty straightforward from that standpoint. Also, just one quick tip. You might have network management tools that don't like the idea that there's two devices on my network that have the same IP address. That's an IP address conflict. You can't possibly have that. You can with Anycast. So you might need to either mute your network configuration tool or network management platform that's not a real alarm. We had this experience when I was a customer. So something to keep in mind as well, right? But for the most part, most devices anymore are used to seeing Anycast, so shouldn't be that uncommon. And then finally, we talked about Anycast RP using PIM, Protocol Independent Multicast. The idea is that now with RFC 4610, we have incorporated the Anycast functionality into PIM natively. So now I don't have to configure MSDP to exchange my groups. I can just utilize Anycast configurations. So it's a platform-specific capability. For example, NXOS supports this version of Anycast PIM. I'm sure iOS and XE devices will pick up the support for it if they haven't already. So it's kind of a check the release notes and check your details in your environment as to whether or not you can utilize this. It's becoming more popular, certainly as more platforms support it. And the reason it's becoming popular is because I don't have to have MSDP there now. So I eliminated an entire control plane protocol, which if I'm a network architect, I want a simple, fast, easy to operationalize network. Right? I want network nirvana. But as I add more and more technologies to my environment, I start to add routing protocols and first hop redundancy protocols and BFD for bidirectional forwarding detection and all these other things. My network becomes more and more complex. If I can reduce that complexity by minimizing or eliminating a protocol, I'm all in, right? That's what I want to do. So that's why customers are starting to kind of make that transition to Anycast RP where they can.
In this video, we'll configure static rendezvous points on Cisco IOS devices. So let's start by connecting to our core router 1, which is in the middle of our diagram on the left-hand side. And we can do a quick show IP PIM RP and see that there's no rendezvous point configured on this platform yet. So we'll go ahead and apply our configuration, which is a very simple config. We'll walk through it. First thing we'll do is we'll configure PIM Sparse Mode on our loopback interface. And the reason we do this is because we are going to have our rendezvous point address be a resilient interface on the router. We typically don't want to assign a rendezvous point address to a physical interface so that if that interface were to go down for whatever reason, the network could converge and still connect to it. We want to make sure that we pick an address like a loopback and use that as our rendezvous point. And to that end, we are going to configure IP PIM RP address 192.168.0.4, which is the loopback 0 on this particular router. Now, there seems to be a bit of a
question or kind of comments in the community as to whether or not we should configure PIM Sparse Mode on our loopback interface, and the answer is a definitive yes, because when we're using our loopback interface for a rendezvous point, it becomes part of the reverse path forwarding check. So we want to make sure that that interface is PIM enabled, otherwise your RPF fails and things don't work properly. So some versions of code this used to work without it, but it's definitely best practice and definitely required to make it work in current models of code. So all that being said, now we can do a show IP PIM RP. And what we'll see is that we're starting to receive multicast traffic from other sources that have already been, or from other routers that have already been configured to use us for a rendezvous point. So we see the 239.1.1.200 and 1.1.2 groups that are now in our table because we know of them from another router who's pointing to us to be the rendezvous point. And we can also do a show IP mroute, and we'll see that we've got star comma G state for those interfaces as well. So let's look at the other router and see how the output compares when we look at a device that's not the rendezvous point. So this router's already been configured for using 192.168.0.4 as our rendezvous point, and we can verify that by doing a show run pipe include PIM, and we'll see the command for IP PIM RP address 192.168.0.4. So now if we do a show IP PIM RP, what we'll see is that we are registering these groups to that rendezvous point, right? So 239.1.1.200 and .2 are configured or are sending traffic and are registering with the rendezvous point 192.168.0.4. It's been up for 7 minutes 49 seconds, and the expiration is right now is never, right? So it's not going to expire on us because it's a statically configured one. It's not a dynamically learned one that has a possible limited life cycle. So we can do a show IPM route. We'll see star comma G state in this particular platform as well for those individual sources. And we do a show IP PIM RP dash map, RP map, not dash map. We can see that we've configured this particular platform to use that 192.168.0.4 for every potential group. And we'll see in the controlling multicast traffic section that we can now start to carve that out and have flexibility for different groups to use different rendezvous points. But in this very simple example, it's going to be configured to 192.168.0.4. Now, if we go back to our core 1 router and do a show IP PIM RP map, we'll see it's the same configuration, right? Nothing has changed from a configuration standpoint. It's still 192.168.0.4. We didn't specify an access list or anything else, but it's the exact same output. And with this, you've now configured a static rendezvous point on a Cisco IOS device. We're going to configure a Cisco IOS device to support Anycast rendezvous point with Multicast Source Discovery Protocol MSDP configured to another iOS device for rendezvous point redundancy and state sharing information. So as we mentioned in the lecture, with Anycast RP, the concept is we want to have multiple devices on the network that are advertising the same IP address. And typically that's not something you have in an environment. It's unique to an Anycast concept. And then what will happen is that the routing protocols use their various metrics to determine which rendezvous point is closest and which IP address for the rendezvous point is closest, and then we'll use that as the rendezvous point. So we're going to apply the configuration, and before we can start, we can do a quick show IP PIM RP, and we'll see that we don't have any rendezvous point configured on this platform at this point in time. What we're going to do is create a new loopback 10 interface and assign it an IP address of 192.168.0.10, which is already configured on another platform in the environment. So if we do a show IP route 192.168.0.10, we'll see that it's already there, which is a little different to what we're normally used to seeing in a network. But again, this is for Anycast, so things are going to be a little bit different than what you might be normally used to. So we'll go ahead and apply our configuration. And we're going to go ahead and configure loopback 10, which we've done here. We're going to give it an IP address, 192.168.0.10, which is exactly the same as the address that's already being advertised on our network that we saw earlier in our route table, configure PIM Sparse Mode for all the reasons we mentioned earlier in the static RP configuration lessons, where we talked about the need for having the loopback interface that's our rendezvous point participate in the reverse path forwarding check and to be able to have PIM enabled on it. So, and then we'll enable it by doing a no shut. We'll add our new loopback to router OSPF1. So this, so far we haven't configured really anything that's multicast specific. Our next configuration will be where we apply the multicast config itself. We enable PIM RP for 192.168.0.10, and this is where we start to apply our MSDP configuration. So what we're going to do is configure IP MSDP peer. So we're forming a peering relationship to another device, in this case another iOS device, that has a loopback of 192.168.0.7. And we're going to tell it to use a connect source of loopback 0. So that way we know that who the connecting device will be on the other side when we look at some of the show output. And we'll see this as we walk through the configuration example. And then we'll get out of our configuration. So now if we do a show IP PIM RP, we'll see that we've got state on our network, right? We're starting to see some star comma G state based on what we're seeing so far. And we can do a show IP mroute and validate that. We see that we've got star comma G state here now, and no actual S comma G state at this point in time. Some of the new commands that we've got available to us to look at MSDP, we can do a show MSDP peer, and we can see that we have a connection to 192.168.0.7, who is our remote peer. Our connection state is up, which is good. It's only been up for a minute and a half. And we can see that there's also filtering options and things of that nature. We're going to do a very basic MSDP configuration, but know that you can filter and be very granular with how you apply your MSDP configuration as to who advertises which source active addresses and state to the other MSDP peer. So you have a lot of flexibility. And then some various timers and things of that nature. We also can do a show IP MSDP SA, and we do see one source active. So our neighbor, 192.168.0.7, has told us that it knows about an active source for 10.0.0.18. Right, so we see that here, connecting to 239.200.200.200, and that our rendezvous point is 10. And MSDP, for those who aren't familiar with it, its initial origins were for multi-domain routing, so being able to share multicast routes across the global internet. So it's got a lot of BGP configuration, but it's important to note that you don't actually have to have BGP enabled, which is being reflected in our configuration. We don't have BGP, and it just says BGP Autonomous System 0. And then we can see some additional information here as far as the connect time and how long we've known about this particular source. So we can do a show IP MSDP SA, and you can see that there are some other commands here we can do, show IP MSDP summary. So depending on what you're looking for, you'll be able to kind of see what your different options are. Something maybe as simple as, well, how many routes am I learning, or how much state am I learning from my peer? In this case, we can see we're learning 1. So now if we connect back over to our second device, which is already configured for MSDP, this is our MSDP peer. If I do a show IP MSDP SA, we'll see that I'm not learning anything from the other router at this point in time. And that's because all of the state that was on core 01 is all star comma G. So there is no actual source and destination on this traffic at this point in time. Nobody has joined those groups as far as core 01 knows. Now, if somebody were to join, you would see the state to start to show up and be populated here. So this is not alarming at all. And we do show IP MSDP peer. We can see again our connection status, who we're talking to, 192.168.0.4. Our connection state is up, and then just some other information as far as filter options that are available to us, messages that are sent and received, and things of that nature. So there's a lot of options again with MSDP. This is just a very basic configuration, but what we've done with MSDP is allowed it so that we can have any source in group that's active on one device be shared with the other one, in this case core 01, so that we have a consistent table, so that if core 02 were to fail, that Core 01 would already know about those sources and be able to recover very, very quickly for a rendezvous point redundancy perspective. So if we take a look at the show IP PIM RP here, we can see we've got multiple groups and multiple state. So this guy's obviously talking on the network and sees multiple different types of traffic flowing through it. And with that, we've configured a very, very basic MSDP and Anycast RP configuration on a Cisco iOS device. We'll see how you can configure RFC 4610 PIM Anycast RP on Cisco iOS devices. And we'll begin by connecting to Core 02, the core router in the middle of the diagram on the right-hand side of the screen. And not to be misleading, but I wanted to illustrate the point that really you can't. It's not there in code as of the time of the creation of this video series. So we can see that there is no show IP PIM Anycast commands that are available to us. So unfortunately, that's a feature that's not available on iOS at this point in time, the way it is on NXOS. And if you want to see how it's configured on NXOS, we do have a lesson specific to Anycast RP configuration on NXOS here in the video series. So just wanted to show this as a point that Cisco iOS doesn't support it as of right now within our environment, but certainly it's something that you will want to keep an eye for to see if it shows up on the roadmap of any iOS platforms that you might have in your environment. In this video, we'll configure a Cisco IOS XE device with a static rendezvous point. So to begin, we'll connect to our edge router, number 1, which is in the upper left-hand corner of our topology diagram. And we can do a show IP PIM RP and see that there is not a rendezvous point configured at this point in time. We'll go ahead and apply our configuration. And much like we did with a Cisco iOS device, we're going to go ahead and configure IP PIM Sparse Mode on our loopback interface. And as we mentioned, this is important for cases where reverse path forwarding checks, for them to pass. It's going to be important since we are configuring our loopback as the rendezvous point. And in the lecture, we mentioned that it was important to use the rendezvous point or a loopback interface or another virtual interface for our rendezvous points, because we want to have an interface on the box that is configured to be the RP that is always available. As long as the box is up, a loopback interface will be up. So it's a great choice and most commonly deployed. And then we go ahead and apply the exact same syntax for the command IP PIM RP address. In this case, we're using 192.168.0.2, which is our loopback interface on this particular platform. So now we can do a show IP PIM RP, and we'll see that we're starting to have devices register with us, right? We're starting to see some multicast groups come in. We can see our 239 1.1.200 and 1.2 that we saw in the previous example, as well as some new groups 239 200 200.222 and .200 are registering. These are sources that are connected to Edge 02. So it doesn't take long for this state to build. And we can also verify that we're seeing some state come up by doing a show IPM route. And we can see that we're starting to see some state here. We've happened to catch one in the middle of a registration process. So that's kind of neat to see, right? That's part of the process. We can see from the flags F and T, if we scroll up, we'll see that it is a register flag and that the shortest path bit is set. Shortest path tree bit is set. So pretty cool from that standpoint, as part of the normal registration process for a host. So if we go over to our Edge 02 router, we can do pretty much the same commands, right? Show IP PIM RP, and this is system's already configured to use the RP. It shows that the RP has been up for 1 week and 0 days, and that it has a 0 timer for expiring. So this is something that's relatively new in iOS and iOS XE, and now showing how long the connection has been up to the rendezvous point. So that's a pretty neat capability in my opinion. And then also we can do a show IPM route, and we'll see some of the state in here as well. So here's another example of a local source connecting to a locally generated multicast group. So that's being pruned.
That's what the P bit is indicating, is that we're pruning this off, because really it's the same server acting as a multicast client and the server at the same time, and the source. So it's really just kind of looping in this gigabit Ethernet 4 interface and coming back out. So kind of a unique configuration to this topology. But we can see the multicast state here. Now, if we go back over to Edge 01 and do a show IP PIM RP map, we'll see that much like we saw on iOS, we are configuring it at this point in time to have all of our multicast groups, the entire 224.0.0.0.4 range, configured to use this particular system, RP 192.168.0.2, as a rendezvous point. And for those who might be wondering, the question mark just means that we haven't been able to do a DNS recursive lookup for the name of this platform. So if you have DNS configured on your iOS and iOS XE devices, the host name would show up here where the question mark is next to the rendezvous point. So, but that's how simple it is to configure a static rendezvous point on a Cisco IOS XE device. We'll configure IP PIM Anycast RFC 4610 and a Cisco IOS XE device. So to begin, we'll connect to our Edge 02 router, which is our router in the upper right-hand corner of our network topology. And not to be misleading, but what I wanted to illustrate was that we are not able to configure PIM Anycast RP. There's no commands for it. The feature hasn't yet been implemented in iOS XE. So you can see that an IP PIM A command doesn't have any other configuration for Anycast in the topology at this point in time. So certainly we illustrate this configuration in Cisco NX-OS in a later lesson. So if you want to see how it's configured on NX-OS, you can see it in that environment, but it's not available on the XE platforms as of the time of the publication of this particular video series. So certainly something you'll want to keep an eye out for on the release notes and see if and when it shows up on any of your platforms that run XE. But it's not available at this point in time on any platforms other than Cisco NX-OS from a Cisco perspective. So with that, we've demonstrated that you unfortunately cannot configure IP PIM Anycast RP and RFC 4610 mode on iOS XE devices. In this video, we'll configure a Cisco NX-OS device with static rendezvous points. So first we'll connect to our data center aggregation 01 switch, which is in the lower left-hand corner of our network topology diagram. And we can do a show IP PIM RP, and we'll see that nothing is configured. Now notice that the output that is displayed is a little bit different than the output that we see on a traditional iOS or iOS XE device. We see a very different format, right? We start to see that we've got BSR disabled, auto RP disabled, BSR rendezvous point candidate, and our policy auto RP, etc. So there's a little bit different information that's displayed, and we'll see that this change in information display also carries over to when we actually configure the rendezvous point and what we'll see after that. So let's go ahead and apply our configuration. And much like we've done on the other platforms, we're going to utilize loopback 0, which on this particular system is 192.168.0.3, and we're going to enable PIM Sparse Mode on it. And for the exact same reasons we do it in iOS and iOS XE, because we are choosing a virtual interface as our rendezvous point so that the box has additional resiliency and our rendezvous point can be reachable if a single interface goes down after the network converges, we do the exact same thing in NX-OS. So IP PIM Sparse Mode is applied, and then the format and syntax is exactly the same, IP PIM RP address 192.168.0.3, and then we've applied the configuration. So now if we do a show IP PIM RP, we'll see that the information at the top stays the same. This is pretty much a table that would only modify if any of these conditions were met. But we'll now see that we have got a rendezvous point 192.168.0.3, and the uptime for it 46 seconds when we just configured it, that it doesn't expire. And then we see which groups it is servicing under the group ranges, right? So group ranges 224.0.0.0.4, so the entire multicast group capability. And we can do a quick show IP MRoute. And what we'll see is that we're starting to build state. So devices on the network are configured to register with this as our rendezvous point, and we can see that we're learning them via Protocol Independent Multicast and via IP for some of the remote ones. Some of the local ones, the 225/100 sources are directly connected locally. We learn those via IGMP. So this is a little different in the way that the MRoute table is displayed in an iOS or iOS XE device. We show probably what I would consider to be more information in NXOS to be able to have a consolidated view. But it's important to know that the view will look a little different depending on where you are in your network and the different OSs that you utilize. And then we see some additional state here for some of our sources and the receivers and how those are being learned. So now if we connect over to our second switch, data center switch 02, this one's already configured to use this one as a 192.168.0.3 is the rendezvous point. So if we do a show IP PIM, we can see PIM RP. We can see the exact same configuration. Now, one thing that's different, and I wanted to connect to this one to point this out. Notice we don't have an asterisk here, right? Now, if we connect back over to 192.168.0.3 just for completeness, and do a show IP PIM RP, we can see we have an asterisk next to the rendezvous point address, right? So we can see it here that we've got 192.168.0.3 with a little asterisk nest to it. The asterisk indicates that that's the box you're on. That is you. That's where you are in the network right now. So if we jump back over to data center 02 and take a look at it, we don't have the asterisk. That's not us, right? 0.3 is a loopback of the other device. But we can do a show IP MRoute, and we'll see that we've got information that's specific to us, right? Some of the local sources that we have configured on the platform, but we don't have all the other state. And this is important to note because if you're the rendezvous point, you do track that additional state. So again, like we mentioned in the lectures, it's going to be a design consideration as to where you configure your rendezvous point, what platform you use, because it does require different resources. But with that, you have been able to configure a Cisco NXOS device to support a static rendezvous point. We will configure a Cisco NXOS device for Anycast from a rendezvous point configuration perspective, as well as MSDP, Multicast Source Discovery Protocol. So to begin, we'll connect to our Data Center AG01 device in the lower left-hand corner of our network topology. And if we do a show run PIM, we can see that we've got a rendezvous point configured and then just default configuration for our other PIM interfaces. And if we do a show IP PIM RP, we can see that that's configured as well. So what we're going to do, as with our other Anycast configurations, is we're going to configure a duplicate IP address on the network. In this case, we'll utilize loopback 10 and give it an IP address of 192.168.0.10. And we'll have two devices, our Data Center AG01 and Data Center AG02 switches, both advertise that network. And the impact of that will be that the other devices in our network will learn those routes for that particular loopback 10, and be able to leverage their routing protocol metrics to find the best path through the network. And this gives us some redundancy in that if one of these devices were to fail, the other device would be advertising the exact same IP address, 192.168.0.10, and would also, by virtue of MSDP, have learned various active sources on the network. So let's go ahead and apply the configuration, and we'll walk through it and explain it in a little bit more detail. So we will configure an interface loopback 10, give it an IP address, configure it to sparse mode. Now, because this is NXOS, we're going to configure IP router OSPF1 area 0 under the physical interface. It's not done in router OSPF1 config the way we do it typically in an iOS or an iOS XE device. We configure our rendezvous point address. And this is another interesting point of note with NXOS. We apply the same configuration command for MSDP, but it didn't take because it doesn't know what MSDP is. MSDP is a conditional feature within NXOS, which means that we need to enable it before we can utilize any of the configuration commands for it. So we'll go ahead and enable feature MSDP, and it's going to give us a bit of a warning about our licensing, and that's fine. We're in grace period licensing, so that's no problem. That it will work in a fully featured mode for 103 more days, and then it will automatically shut down. So we're not worried about it in this environment. We'll then reapply our MSDP configuration, and we'll see that it's now accepted. And this is because the MSDP process has been started within NXOS, and the CLI has been loaded so that it can parse the commands, and it knows what to do with MSDP. So now we can do a show IP MSDP SA like we did on our other platforms, and we'll start to see if we're seeing any other active sources in our environment. We can do a show IP MSDP peer, and we see that we have a established connection to 192.168.0.8. That is our partner MSDP node. Our connection state is established. It's only been up for 21 seconds. And then you can see that there are some additional counters and statistics that are available on this. Now, this is a little bit different from the CLI we saw in iOS XE, but the protocol in and of itself is still the same. So it's still MSDP. So we can also do a show IP MSDP summary. And we see that we are established and have a connection, which is good, and that we haven't received any S, Gs. So no real surprise. There's not a lot of state in this network at this point in time. So let's go over and connect to Data Center AG02, and we'll be able to see that this particular device has a corresponding connection back to us. It's now established to 0.3, which is us on Data Center AG01, and we can do a show IP MSDP SA. And had there been any active sources, we would see them listed here. So because there's not, we don't see anything. It's not a very exciting output at this point in time. But we also wanted to point out that if we do a show IP route 192.168.0.10, we can see that we've got two routes, one that's local and one that's direct, right? So we can these are two entries for the same route. Just different ways of kind of describing it with inside of NXOS's routing table. So they're both for loopback 10 that's local to us. So that's kind of interesting from that perspective. And we do show IP PIM RP. We'll also see that we are considered to be the local rendezvous point because we do have loopback 10. We're local. Now, if we flip over back to Data Center AG01 and do a show IP PIM RP, we'll see that he also has an asterisk, which means that he thinks he's local as well. This is exactly what Anycast is designed to do. We want to have two devices with the same IP address, advertising their ability across the network, and having the route table can help downstream or devices further out the network learn where these rendezvous points are and use a routing protocol metrics. So this gives us a ton of flexibility with how we can start to configure our network, and then we can change those IGP metrics or routing protocol metrics to influence which one we want to have be a rendezvous point at any given point in time. We'll take a quick look and see if any of our sources have come active, and they have not. So no big deal. So with this, we've been able to apply a very basic configuration. You can see that there are a couple of other options for MSDP that you can use to control traffic. You can get other statistics from it. So again, this is kind of the tip of the iceberg with MSDP, but this is a very common configuration with Anycast and MSDP for rendezvous point diversity and resiliency in customer networks. So with that, you've been able now to see how we configure Anycast and MSDP on Cisco NXOS devices. We will configure a Cisco NXOS device to support IP PIM Anycast rendezvous point via RFC 4610 configuration. So we'll begin by connecting to our Data Center AG01 router, which is on the lower left-hand corner of our network topology screen. And we can do a show IP PIM RP and see that we're configured for 192.168.0.10, which is a local source. We are the local rendezvous point. What we want to do is we want to add a Anycast configuration to this so that we have another device on the network that is configured for 192.168.0.10 as well, much like we did in the MSDP configuration. The difference being we're not going to configure MSDP at all. We'll leverage a feature that's unique to our PIM implementation that allows us to be able to have Anycast RP without MSDP. So the RPs will share state without having to rely on a second control plane protocol, MSDP, to advertise that for us. It's built into Protocol Independent Multicast. So we'll go ahead and apply our configuration and make that change happen. We'll configure loopback 10 and our IP address, advertise it in OSPF, much like we did earlier. And actually this part was already done, inactive on our router. And then we have our IPPIM RP address configured. What's new and exciting in this configuration are these two new commands, IPPIM Anycast RP, and then we give it the IP address of the Anycast address. So 192.168.0.10, and then these last two configurations here, 192.168.0.3 and 192.168.0.8, are the IP addresses of loopbacks on the two different devices on Data Center AG01 and Data Center AG02 that are participating in the Anycast RP configuration. So note that this is a little different syntax than we've used before. This is the first time we've used the Anycast-RP syntax in any of our configuration examples. So let's take a look at how that changes the output that we look at when we do a show IP PIM RP. We've got a new configuration or a new bit of detail here where we show our members of our Anycast RP group. So we see 192.168.0.3 and 0.8, and we can denote that we are on the local box, we are 0.3 by virtue of the asterisk that's listed there. So we can see that we've got a Anycast RP configuration. We're the local Anycast device. And if we switch over to AG02, we can do the same command, show IP PIM RP. The difference being that 0.8 is its local loopback 0, and that is the local entry. But we can see that we're joining the 192.168.0.10 group, and that the 0.10 is also local to us. So there's our Anycast configuration. All right, both of these devices have loopback 10 that are running Anycast RP from a PIM perspective as opposed to MSDP, and that's really about it for verification. There's no other commands to see routes that are exchanged. It just becomes part of the routing table. It's just part of PIM. So there's not a whole separate CLI complex the way there was with MSDP. So we have our traditional state that we've been generating in the network, our S, Gs and star, Gs. And if we look at this one, we can see some similar output, albeit with less state, because now each device is handling the traffic as an RP locally. A bit of a change in our routing tables, and this is what you would see with a traditional or typical Anycast RP configuration. Now both of them start behaving for rendezvous points depending on which one came active at any given point in time, and then IGP metrics or routing protocol metrics to get traffic to those particular devices with their PIM registers and joins. With that, you've seen how you configure an Anycast PIM configuration. We can do a show run PIM and see that all of the configuration that was added were these two lines here, IPPIM Anycast RP, and that was it. So very, very simple to configure PIM Anycast RP on Cisco and XOS devices.
Okay, so to wrap things up, to summarize, certainly RP placement may or may not be critical. Depends on the network topology and the environment that you're deploying it in. You have options, whether it's static configuration, auto RP, BSR. Certainly those are the most common forms, with static being the most predominantly deployed method, followed by auto RP. Anycast and MSDP make for a very, very powerful combination for RP redundancy in a larger domain. Allows my IGP to fail over and for my multicast traffic to follow it to the new rendezvous point. And then certainly Anycast RP becoming more prevalent as platform support is added. In Lesson 5.1, we'll talk about methods for controlling multicast traffic and how we can be successful with those. Certainly administrative scoping and an addressing design is paramount to be successful with multicast. It's typically not something you're just going to turn on and walk away and expect it to be great. You need to have a plan to be able to be successful, and ultimately that's what we want to do. Unless you're trying to torpedo your career for whatever reason, you want to have a game plan, right? You want to know what you're doing and have a method of the madness that can be supported by somebody else if you move on. So certainly starting with the end in mind is important. What are my goals? What are my application requirements? Why am I deploying multicast? Am I deploying multicast because I just watched a live lesson that was really awesome about multicast and I'm so excited to deploy it? That's always a possibility, right? But most customers deploy multicast because they have a specific use case, right? They need it for their application. They need it for their business to be successful, and you need to know what those are, right? Do I need to do administrative scoping in my environment? Am I worried about global address reach versus localized address reach within a campus or within a data center? Or do I just want multicast traffic to go wherever it needs to go? Certainly traffic control is going to be important. What about state control, right? We mentioned earlier with regards to configuring the different types of PIM is going to dictate where my state lives in my network and how much data I might have at any given point in time. If I'm doing just generic sparse mode, I'm going to have quite a bit of state, but it's going to fluctuate as it changes from the shared tree to the shortest path tree, right? So I'll need to be aware of that. Whereas if I'm using bidirectional PIM, I've got not as much state, but I've got state that flows through the shared tree, so I need to be aware of that. If I'm using SSM, I don't have the same RP concerns, but now I've got state that is just being built along the shortest path tree. So I need to be cognizant of that, and is that something I need to control, or maybe there's something else, right? And then ultimately from an administrative standpoint, the layer 9 stuff, I mentioned the OSI system model earlier, layer 8 being religion, layer 9 being management. Who owns the plan? Right? Is that you? Cool. You're in the driver's seat. You get to make all the choices. But who will own it moving forward? And equally important, does management support the idea of rolling out multicast? Right? And I think one of the things that's been interesting is that as I've talked with other customers about deploying multicast, almost all of them have some sort of horror story from 7 or 8 years ago where I turned on multicast and all of a sudden the network melted down until we turned it off. Okay. You need to think about what happened then and how you can mitigate that, right? And certainly management usually remembers that kind of stuff. They remember the big outages. They remember the bridging loop that spanning tree caused or whatever, right? So you need to get their support before you say, hey, I'm just going to turn on multicast for kicks and grins. They might say, no, time out. We've been there, done that. It melted down the network 7 years ago. Multicast is strictly forbidden on our network. Yeah. You have to navigate that within your own organization. So when we look at administrative scoping, the big question the customers ask is, okay, so cool idea, where do I start? Well, starting with a game plan is always number one, right? So RFC 2365 really lays out the strategy for most customers to deploy an administratively scoped environment, right? So again, we'll focus on that 239.0.0/8 address. And that is designed to be the private multicast address space, much like the RFC 1918 address space for unicast. So it's yours to slice and dice and deploy and allocate, and typically you won't see this on the global routing internet anywhere at any point in time. It should be dropped at all border edge routers. I'll put a little caveat, when configured properly, right? So there's always that devil in the details. But the idea is that within those administratively scoped zones, I'm able to subsequently break down that addressing space into smaller and smaller chunks. And that also limits the scope. How broad across my network can those addresses go, right? Do I want it to be enterprise-wide and say, you know what, 239.192/14 and above is a global scope that goes to everybody? Or, do I want to break it down into smaller chunks and say, this 239.255/16 is designed to be a local scope and only stays on this particular campus. I have the ability, and that RFC kind of lays out the typical progression that most customers go through to deploy it. It was well thought out, written by really smart people. So certainly, following their guidance is usually a pretty good place to start to ensure your success. And then the addressing expands downwards in the address range, and you may have other scopes that are equal, but they're typically not smaller. So typical subnetting rules still apply with regards to how I break down the division of subnets in my environment. But this is a great place to start, 2365, to kind of get that ball rolling and look at it from an enterprise-wide deployment. Some of the considerations is, do I want to map groups to specific RPs, right? That certainly gives me a lot of flexibility with my RP placement. Maybe I want to have a rendezvous point in my campus environment for my campus-based applications. I don't want them to have to go all the way back to the data center to find that their source and receiver are both present in the campus. Let's localize it. Let's think about the traffic flows. And based on what we now know about shortest path trees and shared trees, now that you're properly armed with lots of great multicast information, you can say, you know what, our RP placement should be there, and make that decision and that determination, right? So it gives you a lot of flexibility. And that's probably the most commonly used method of control. It also allows us to be able to control the state. Again, back to shared trees versus shortest path trees, we now know where state is created. That doesn't just happen magically and, oh my gosh, I wonder where all this multicast came from. That's amazing. The network just did it on its own. That's not the case. You as a network administrator are the ones who control and configure that based on your decisions as to which protocol I'm using in my RP placement. So if state is a concern, then again, choose wisely, right? So you have to be cognizant of that. Certainly the amount of state impacts your convergence. The more state you have, typically the slower your network converges. And in general, slow convergence isn't what customers are after. So ask your CEO if he'd rather have his network back up in seconds or minutes or hours. I bet I know what their answer will be. Certainly, I mentioned this earlier, multicast typically converges slower than unicast, and it's usually not like by a couple seconds. It's usually on the order of magnitude of minutes if you have a large multicast domain. That's not uncommon. That's not great either, which is why you want to have RP redundancy and utilize Anycast and things like that to help your network converge as fast as it possibly can. Multicast is frequently a breaking point for a lot of network devices. So if you want to really stress test a network device, throw a ton of multicast traffic at it. You'll bring it to its knees pretty quickly, or you'll learn a lot about multicast, if not both at the same time, right? So that's definitely one of the interesting things. But certainly multicast, the convergence is different, as are the forwarding parameters, right? Which we've covered some of. So something to keep in mind. When we look at controlling multicast at layer 2, certainly ACLs for IGMP is the most commonly deployed methodology, right? So maybe I want to limit the number of receivers from joining a group, or specific receivers from joining a group. Maybe the multicast traffic is sensitive in nature, and I don't want it to be able to be joined by anybody who randomly decides to join a group. I want it to be very specific. I can be prescriptive and say only these particular hosts can join this particular multicast group through IGMP. So blocking it down at the layer 2 level. Typically, the command would be something along the lines of IP IGMP access group, and then fill in the blank with an access list. If you're not familiar with access lists, you'll be very familiar with access lists by the time you're done deploying a comprehensive multicast design where you're controlling the traffic. You'll get very good at that. You also could prevent devices from snooping on a group, so tell a switch to not snoop on a particular group, and being able to restrict that as well, utilizing the access group command. So some options there as well. At layer 3, we have a lot more controls that we can exert on the traffic. At layer 2, kind of being at that lower layer of the OSI system model, you're somewhat limited in what you can control. Layer 3, a whole new world of possibilities opens up to you, right? Because you have layer 3 headers and layer 4 and beyond that you can deal with as well in your ACLs. A very common deployment is to utilize ACLs to define a multicast boundary. And the idea is that you would typically deploy a multicast boundary command, and that specifies the limit of a particular group. So if a packet with that source address tries to traverse the interface, it would be dropped. So it's a multicast ACL, right? Being able to decide what traffic can go where. Maybe you utilize this on slower IP links. Maybe they're backup links. Maybe they're a DSL backup to your primary internet connectivity or something else where you know your bandwidth constrained. If I'm on the backup, I probably just want the mission critical data to go through. Now, if multicast is your mission critical data, then certainly permit it. But in a lot of cases, if it's just video or extraneous company information, then maybe that's not important, right? You can control with the multicast boundary commands. You also can control who you form a PIM adjacency with. And in the PIM section, we saw that when we enabled PIM in the CLI, that we formed adjacencies with other PIM devices. Much like we do in OSPF or EIGRP, I form a PIM neighbor. I form a OSPF neighbor, EIGRP neighbor. Same approach with PIM. I define, or I can define who I want to be a neighbor with. That will also determine the path that allows traffic to go across, right? So I can do a neighbor filter, and I don't care about PIM updates from neighbor XYZ. Maybe I'm in a shared environment, and I want to be very granular where it's a co-location space. And I only want to form a PIM adjacency with my provider's upstream router, not other customers that are on the same IP subnet with me, right? So lots of options of how we can control PIM neighbors from being established and joining across our network as well. I can control PIMs, joins, and prunes. And this is something that right now is available in NXOS. It'll be coming to other platforms as the developers see opportunities to incorporate the feature functionality. But the idea is that I'm able to define a join and a prune policy, so I can control even where the state for joins and prunes would be from receivers to hosts. So maybe I need to get even more granular than my multicast boundary or a PIM adjacency or IGMP allows me to do. I can limit my joins and prunes within NXOS. So an additional control that's available to me, and the command is creatively named IP JP-policy. So join prune policy, define an ACL, and you're good to go. So pretty powerful methodologies. So we'll see all of these methodologies applied in the upcoming CLI.
In this video, we'll focus on configuring IP IGMP multicast controls in Cisco IOS. So if we recall from our lectures, IGMP is a layer 2 technology within multicast, and hosts join IGMP groups to indicate their interest in joining a multicast group so that we can start to receive the traffic on the device. So if we take a look at our configuration, we'll start off with our core O1 router in the middle of the diagram on the left-hand side, and we can take a look at the existing IGMP topology. We can do a quick show IP IGMP groups, and we'll see that we've got a couple of different groups. We've got 239.1.1.1 and 239.1.1.120. And in this scenario, let's assume that our network admin decided that we don't want to have somebody joining this 239.1.1.20 group that's connected to Gigabit Ethernet 0/6. Maybe that's an unauthorized stream, or that's a stream that we don't want that particular group to access for whatever reason. Maybe it's financial data, maybe it's sensitive data, or just something that they just don't need to have access to. So how would we control that? This is IGMP, so this is a layer 2 capability. So what we'll do is we're going to create an access list, and to be fair, all of these examples will be very simple access lists. Now, certainly iOS has a lot of options for configuring IP access lists, whether it's standard access lists, extended access lists, named access lists. The fun never stops with ACLs. But we're going to be very focused on how we start to use this for multicast. So we'll try to keep it very simple and straightforward. So in our environment, we want to prohibit anybody from joining this 239.1.1.2 group. So let's take a look and see. All right, so we still have it out there. We're going to apply basic config, and this configuration will create an access list that permits 239.1.1.1, and then it would deny anything else. Now, recall back to ACL kind of fundamentals, there's an implicit deny at the end of every access list. So we don't really need to specify access list 1 deny anything else. It's already there. And I chose to construct the access list as a permit in this
becomes very an important decision in your access list creation. This is very restrictive, right? In this scenario, we're only permitting hosts on that interface to join 239.1.1.1. They won't be able to join any other groups. Specifically, they won't be able to join the 239.1.1.20 group, which is our intended goal. But maybe the other approach that you could utilize would be to make this an access list 1 deny 239.1.1.20, and then they would be able to join anything else. But maybe I'm not a nice network administrator. I want to be very explicit as to what they're able to access, so I only give them access to the one particular group. So now if we do a show IP IGMP groups, it's still there. We've got we're going to have a minute and a half before this goes away because the state is there, and we're waiting for the timers to expire. So certainly that's what will happen is that this entry will go away in about a minute or so. So again, it's very important consideration as to how you construct your access list. Either very explicit as to what people can access, or more specific as to what people cannot access. And it's an important decision. It's comes down to a maintenance issue long term. How do I manage and maintain my network? How much do I want to touch it? Is this going to be something that I'm going to be doing on a regular basis, or is this a one-time only event? There's a lot of considerations, but we'll see here that the intended result will happen here in 42 seconds when we get some additional when the timer expires, and the access list will be triggered, and we can do a show access list right now and see that it's being matched for 239.1.1.1. We don't see the deny because, as I mentioned, the implicit deny is there. So because of that, we don't see any matches against it, and that's another consideration with the approach to your ACL. Do you want to be able to see all of the denies, or just know that only things that are permitted are being let through? So we've got about 9 seconds left before this timer will expire. And we'll see that this group should be gone here in the next refresh interval. So now 1 second, and now it's gone. So with that, we've applied a very basic IP ACL to deny access to that one IGMP group. So, and as I mentioned, there's a lot of different ways you can construct these ACLs. We're just kind of giving you the fundamentals and the tools to see that this is a possibility of what you can do inside of iOS. And with that, you've configured a IGMP access control list for Cisco iOS. We're going to configure an IP multicast boundary on a Cisco iOS device. So we'll start back on our core O1 router in the middle of our topology on the left-hand side. The idea behind a multicast boundary ACL is to define the scope of where a multicast address can go, which means we're going to dictate who can join particular groups and how far across our network can these different groups can go. And this dovetails into the administrative control session that we talked about as well, with regards to laying out your addressing scheme on your network and being able to have a lot of control over where traffic goes. This is where one of the easy commands to configure for multicast control. So we're going to start off by taking a look at our mRoute table, and we're going to see that we've got this particular source and destination 10006 on 239.1.1.1, that we have a subscriber upstream on Gigabit Ethernet 02 who has joined this group. So now let's, for use as an example, maybe that interface or devices connected to that interface shouldn't be allowed to join that group. In this case, it's our Edge 01 router. So let's assume that people behind it shouldn't be joining 239.1.1.1. So how do we control them or prevent them from joining that group, and do it relatively easily? And the approach we're going to take is with a multicast boundary ACL. So we're going to define a simple access control list and apply it using the multicast boundary config. So let's go ahead and apply that configuration and take a look at what we're doing. So we're going to create a simple access control list 5. We're going to tell it to deny 239.1.1.1, and then we're going to apply it on Gigabit Ethernet 02, which is our IP connection to Edge 01, and define an IP multicast boundary number 5. And now that 5 is a reference back to this access control list. So just real quick, so we can see the options that are available here. We do a multicast boundary
question mark, we can see we can use standard, extended, lots of access list options. So we're using a very, very simple example to illustrate the point, but the end result is still the same as far as what we'll be able to see. So if you recall back on our multicast route state, we had state showing that the traffic was going out that gigabit Ethernet 0/2. So now if we do a show IPM route, what we'll see is that our outgoing interface list is null. So this has already taken effect, right? So here's our group 10.0.0.6, 239.1.1.1. Specifically, we were trying to filter 239.1.1.1, and we wanted to make sure that we were not sending it out interface gigabit Ethernet 0/2. That's where we define our multicast boundary. Now the outgoing interface list, the OIL, is null. So our ACL has already taken effect, right? And if we do a show access list, we should see that we've got matches against it. So the host on the other side that's connected to Edge 01 is still trying to join that group, but we're denying it via that multicast boundary. So that's a really good example of how simple it is to start to control addresses. In this, we used a specific host address in this example, but this very well could have been an entire range of addresses. It could have been a big block of the 239 administrative scoped range that we said only the top 100 are permitted to go, or the bottom half of the group, or whatever combination makes sense in your particular topology. But the net effect remains the same, is that now nobody connected to that upstream router will be able to join 239.1.1.1, and we did it all with a single command. So again, pretty straightforward and pretty easy to implement, but also very, very powerful. Note, we didn't have to wait for a timer to expire like we did with IGMP. As soon as you apply the multicast boundary ACL, that change takes effect. So certainly something to keep in mind if you're working in your production environment. You want to be cognizant of the impact that this could have on your topology. And with that, you've configured a multicast boundary ACL in Cisco IOS. We're going to explore options for controlling protocol independent multicast neighbor relationships. Now, this might be something that could be helpful maybe in a shared tenancy environment, maybe in a co-location facility where you share a common subnet with multiple different devices that might be other customers that are in the same co-location facility, or just business partners or something else. Maybe it's just different parts of your organization that have different routers and devices under different management. But the idea is that we want to be able to configure a filter to allow us to be able to determine who we want to be a neighbor with. So if we go to our topology, we'll start with our core 01 router on the middle of the left-hand side of our topology diagram. And if we do a show IP PIM neighbors, we'll see we've got a couple of neighbors here, and we're going to go ahead and pick on gigabit Ethernet 0/2, the same guy, the Edge 01 router that we picked on earlier with our multicast boundary. We're going to say that we don't want to have him as a PIM neighbor anymore. Maybe it's a different part of a company that we're spinning off for mergers and acquisitions, or it's just somebody who's misbehaving or something else. So what we're going to do is we're going to define, again, a simple access control list to deny PIM relationships with this Edge 02 router. So let's go ahead and apply our configuration, and what we will do is walk through the config after it's applied, and we can see we've got access list 10, deny host 10.0.0.26. Now, the reason we picked this address is because this is the IP address of the neighbor, of the PIM neighbor. So we want to make sure that we're being explicit as to who we're denying. Certainly, again, this is something that can be done via different access control list methodologies. Maybe you need to have a range of addresses or a group of addresses. You can use all of the typical access control list gymnastics that you're used to using in this environment as well. But again, we're just using a very simple configuration to illustrate the point of the command and technology. So then we'll go into interface gigabit Ethernet 02, IP PIM neighbor dash filter 10, and the 10 specifies that we need to call access list 10 to see who we're allowed to, or who we're filtering. And now if we do a show IP PIM neighbors, what we'll see is that we no longer have a neighbor adjacency on gigabit Ethernet 2, right? So it goes from 01 to 03, and we've lost the neighbor adjacency on gig 02, which means we no longer learn any multicast state. We don't have any protocol independent multicasting capabilities between these devices. Maybe it would be easier to just remove PIM from the interface, but certainly a neighbor filter will do the trick as well, especially in a shared media environment, maybe a common Ethernet segment or a VLAN. Now, a bit of word of caution on this.
you'll have to take into account what the routing topology is from a unicast perspective, because if you start filtering your neighbor relationships and the best path, the reverse path, is across that interface, well, you no longer have a PIM adjacency on that interface, which means that it will be subject to RPF failing, which means you could be very disruptive to your multicast traffic. So this is definitely one of the options that you'll want to use with caution, but certainly understanding your topology and requirements are going to be key. As always with any access control list or any kind of multicast control, you want to know really what you're doing so that you don't impact your production traffic. But this is a good example of an option that you have to be able to provide that level of control and granularity in your multicast topology without impacting the underlying unicast traffic. So unicast traffic will flow across this all day, every day. So we're good from that perspective. With that, you've configured a PIM neighbor filter in Cisco IOS. In this video, we'll configure IGMP controls in Cisco IOS XE. So to begin, we'll connect to our Edge 01 router, which is in the upper left-hand corner of our topology diagram. And we can see that we have some IGMP groups already established for different flows of traffic. So we can see we've got just a handful, 239.100.100.100 and .110. Now, if we recall from the lecture, IGMP is a layer 2 technology and focuses on helping hosts join multicast groups to signal their desire to receive the traffic that's part of that multicast group. And that's part of how the network builds the state through the environment to make sure that the traffic reaches its intended recipients. So in this example, what we want to do is we want to filter out a particular group. So we're going to say that maybe 239.100.100.110 should not be allowed. And what we're going to do is construct a simple IP access control list inside of iOS XE to do this for us. Now, it's important to note that there are a lot of options inside of iOS XE for access control lists. We're just going to use a simple standard access control list, but certainly you could leverage an extended ACL, named ACLs, and get very, very granular with your desires. But what we're going to do is apply our configuration. And what we've done is we've defined an access list 1, and we're going to tell to only permit 239.100.100.100. Now, this is very, very granular in that we're going to reject everything else, because if you recall back to your access control list operations, there's an implicit deny at the end of each access control list. So we've got a specific group that we're permitting just the 239.100.100, and then we turn around and go to the Ethernet interface, in this case Gigabit Ethernet 4, and apply the access control list via IP IGMP access-group 1. The 1 refers to access list 1. That's how you link the two together. And then we'll get out of configuration mode. If we do a show IP IGMP groups, what we will see as soon as our timer expires at about a minute and 44 seconds is that this group will age out. So if you recall, IGMP is a timer-based protocol that will periodically refresh the group list and have different and have the recipients signal their intent to join a group. In this case, our timing for this example is a little off, and that we're going to have to wait a bit for this to age out. But it's certainly good to note that with access control lists, we've got a lot of different options, right? I mentioned standard IP ACLs, what we're using in this environment, and we've taken an approach of very restrictive. I'm explicitly calling out what I want to permit. I only want to permit 239.100.100.100 to be able to be joined on this particular interface. And the other approach would be to maybe make this a deny, and then just deny the rogue or the group that we don't want to be present. It just depends on your perspective and your life cycle and requirements for operationalizing your environment. Some customers choose to be very, very permissive, and others are a bit more locked down. I'm more in the lockdown group as opposed to permissive, because security, obviously, in this day and age is always an important topic and consideration.
So let's take a look at our groups and see in 17 seconds left on these timers. And this is a good refresher on our IGMP version 2 timers. It's 3 minutes. So we timed that right about in the middle of the timer refresh cycle. But what we'll see is that this group will disappear from the CLI here in just a few more moments. And there it is, it's gone. So with that, we've been able to be very explicit into what we're allowing. We're only allowing 239, 100, 100, 100, and we've filtered out all of the rest, including this 110. So with that, you've configured a IGMP access control list on Cisco IOS XE. We will configure an IP multicast boundary on Cisco IOS XE. So to begin, we'll connect to our Edge 01 router, and that is the upper left-hand corner of our network topology diagram. And if we take a look at our multicast routing table state, do a show IP route, we'll see that we already have some flows in our environment and in various state throughout the topology. So some star comma Gs, we've got an S comma G specifically here, and this is actually the guy we're going to pick on. We're going to say that in our particular topology, we want to make sure that nobody is able to successfully join that group, 239.1.1.1. And maybe that defines a boundary between our different administrative organizations, or just dovetails in with our administrative scoping that is so part of a solid multicast routing design, and being able to determine where traffic can go at any given point in time from a multicast perspective, and helping provide some control mechanisms, which is exactly what we're doing with this boundary capability. So we're going to define yet a simple access control list and apply it to our interface. And what is going to be important for us to note, the difference that we'll see in the CLI output here, is that this Gigabit Ethernet 2 interface will go away. The outgoing interface list will turn to null when we finish our exercise here. So we're going to define an access control list, access list 5, and we're going to deny 239.1.1.1, and then apply it on Gigabit Ethernet 2, which is our downstream link to our core 01 router. And then we define IP multicast boundary 5, and the 5 refers back to the access control list number here. That's how we link these two commands together. And then we get out of our configuration mode. So now if we do a show IP mroute, and specifically let's be granular and look at 239.1.1.1, so we don't have to sift through the rest of the CLI output, what we'll see is that our outgoing interface list is now null. So if you recall earlier, it's at Gigabit Ethernet 2, and that was where traffic was going. So one of the things that's important to note is that we will still have some of this state in here, partly because we are the rendezvous point. So the devices will register with us, but the ACL will prohibit any joins from happening, which means that we end up with some of this kind of this partial state, and this will eventually filter out or time out in the environment. But the multicast boundary is a very powerful option to be able to, again, control where traffic does or doesn't go in your network, and it was all done via one access control list command. So very, very elegant way to control traffic in your environment, and gives you, again, that capability to be very, very flexible to meet your application requirements and your company's requirements for where multicast traffic goes in your network. With that, you've been able to configure a multicast boundary in Cisco IOS XE. We will illustrate how to configure a Protocol Independent Multicast PIM neighbor adjacency filter in Cisco IOS XE. So to begin, we'll connect to our Edge 01 router in the upper left-hand corner of our network topology diagram. And let's take a look at our PIM neighbors. We can do a show IP PIM neighbors, and we'll see that we've got two neighbors. We've got a connection to core 1 and a connection to core 2. Typically, we only see customers deploying PIM neighbor filters on maybe edge devices, or in a shared facility or co-location facility, or maybe it's a business partner zone where you have multiple routers or devices that are under different administrative controls, and you want to be very specific as to who you form a PIM adjacency with. So in this case, we're going to say that we don't want to form a PIM adjacency with Gigabit Ethernet 2, which is our connection to core 01. So we're going to define a simple ACL and apply it, and we'll see the configuration and we'll walk through it as we go through. So we will define our access control list 10, and we're going to deny specific host 10.0.0.25. If you go back up here, you see that that is the IP address of our PIM neighbor. We're going to apply it to Gigabit Ethernet 2 via the IP PIM neighbor filter 10, and this 10 is a callback or reference to the access control list 10, and now the command is applied. So now if we do a show IP PIM neighbors, we'll see we only have a PIM adjacency on Gigabit Ethernet 3. So this command takes effect right away. Unlike the IGMP commands that wait for the timer to expire, this happens immediately as soon as you hit enter. So you'll want to be aware of that as you go through and do your configurations, what the possible impact of this could be to your active topology. But certainly it's a powerful tool. And one of the things that's a little interesting, I think, from a configuration perspective is we just took PIM off. Does that impact the way OSPF forms an adjacency, which also utilizes multicast? If we do a show IP OSPF neighbors, we can see we still have a neighbor adjacency on Gigabit Ethernet 2, right? So that's a good indicator of when you might want to use this PIM adjacency, as opposed to maybe doing a traditional ACL or a broader multicast ACL. We can be very granular and say, you know what, we want to have multicast traffic flow across this for OSPF, but we don't want to have it flow across for Protocol Independent Multicast. So that doesn't change the behavior here, and we're still able to maintain our OSPF adjacency, even though we have this PIM neighbor filter. And now we can still see that we don't have a neighbor on Gigabit Ethernet 2. So with that, you've now configured a PIM neighbor filter in Cisco IOS XE. In this lesson, we'll configure an IGMP filter in NXOS. So we'll begin by connecting to our data center aggregation 1 router in the lower left-hand corner of our network topology. And we can do a show IP IGMP groups and see that there are some existing groups already configured in the environment. What we want to do is apply an access list that will allow us to be able to prohibit the 225.100.100.110 group from being present. So maybe this would be useful in an environment where you want to restrict traffic, restrict who can send traffic, and maybe specify only a particular source or a group of sources. And the framework that we're going to use is very, very flexible. The access control list layout in NXOS is a little different than it is in iOS. So we'll see this as we go through the example and get some specific details. So we're going to apply our configuration. We'll go into config mode. We'll create a route map, which is different than normally just a traditional ACL. This gives us a lot of flexibility just by virtue of it being a route map. And we're going to specify the name IGMP filter. That's just a name we came up with. It could be whatever you wanted it to be. And then a permit sequence. And the permit sequence tells us to match IP multicast group 225.100.100.100/32. So we're saying that we only want to see this top group join, and we want to exclude anything else, including this 110. Maybe this is a rogue source of multicast data, and we don't want that out there. And then we're going to apply it to Ethernet 2/3, which is the source where this traffic is coming from, and we'll apply it as an IGMP access group, and then we specify the route map name. So somewhat similar to what we did within iOS, but different in that we leverage a route map. So as I mentioned, that gives us a lot of flexibility. We can get very, very specific in our sequencing and details as to how we want the route map to be configured. So if we do a show IP IGMP groups, so the timer hasn't been met yet, so we've got a little bit of time here before the 110 group will leave the table. But certainly this is a little different than the syntax that we see inside of iOS. Some additional information we can look at if we look at show IP IGMP interface Ethernet 2/3, we'll be able to see that we do have a policy on here. This is our report policy, IGMP filter. So you can verify that that filter has been applied there as well. And we'll see, and then our typical virtual port channel VPC information as well, which is unique to NXOS, is listed here as well. So there's a couple different places you can use to verify this. We can also just look at the interface Ethernet 2/3 and see that the filter has been applied here via the IP IGMP access group IGMP filter list. So if we do a show IP IGMP groups, let's see where we are with our timer, 136.
Okay, so now let's take a look at our group and see if our groups are gone now. And we can see that the 110 group has expired out of the group or out of the table, and it hasn't been permitted to get back in. So with that, you've been able to configure a simple IGMP filter in Cisco NX OS. In this example, we're going to configure the equivalent of IP Multicast boundary in Cisco NX OS. Now, NX OS does not support the boundary command directly. We end up with a sequence of commands to be able to configure PIM, as well as some data plane control lists to help us circumvent this lack of support for the multicast boundary configuration command. So we'll begin by defining some access control lists. So we'll get into configuration mode. Actually, we'll just apply the entire config and walk through it. So we enter configuration mode here. We apply, or we create an access list called no multicast data, or no MCAS data. And we define two sequences, permit IP 224.00024. And now if we think back to the very first lessons with regards to multicast IP addressing, 224.00024 is a local address scheme, or for local multicast. And it's typically used by protocols like PIM, OSPF, EIGRP, etc. So we want to make sure that while we're limiting our data plane access for multicast, this is just a normal IP ACL, we're just naming it no multicast data, we want to make sure that we don't impact our routing protocols. We still want to have OSPF adjacency, for example. So we'll specifically permit that local address, then we'll deny anything else that's in the multicast group. We're going to prohibit all multicast traffic going across this interface. And then we'll create a route map for the PIM policy. And the route map is very, very flexible, and that we can get granular and have multiple sequences of events happen and matching and permitting based on our requirements. So let's walk through this and see what we're doing. So we're creating the PIM policy in the first deny sequence. We're matching IP multicast group 239.111/32. So we want to prohibit that multicast group from coming into our network, and then from a join prune policy, and then we will then specify permit for everything else, right? So there's our permit statement for the rest of the entire multicast group. So this net effect is that we are denying just this one group and permitting all other multicast traffic. Then we go to our physical interface, Ethernet 2/1, which is our connection to our upstream core router. And we will apply these different ACLs. We'll apply our access list for multicast data to address our data plane requirements, and then we specify the IP PIM join prune policy and specify a PIM policy. So the PIM policy is the name that we just created for this particular route map. And the new command that we've got in here is IP PIM border. This is unique to NX OS in that it allows us to be able to tell NX OS to not forward or respond to AutoRP and BSR commands. So it kind of defines that PIM administrative boundary, but doesn't do the same as the multicast boundary that we saw in iOS and iOS XE. So now let's take a look at our PIM interface. So do a show IP PIM interface Ethernet 2/1. And what we'll see as we scroll down, we've got our join inbound and outbound policy is the same. You can specify different policies, one for inbound, one for outbound. We're doing a very simple configuration where it's the same policy for both. So we will match that PIM policy that we defined further up in the configuration. And then what's most interesting for us is we can see the join prunes that have been filtered by the inbound policy are 64. So we have sources that are upstream from this Nexus 7000 that are trying to join that particular group. And this is the rendezvous point. So state is coming in as they try to send their join messages to the rendezvous point to join the particular group, and we're filtering them. So we can see that this counter will continue to increment as traffic traverses the network, and we can see it's already gone up by 2 more. So it's a persistent little host out there trying to join that group, but we're filtering it from happening. Now, one thing that is an interesting point of note is if we do a show IP mroute, and let's just look at 239.1.1.1, because that's the one we're trying to filter to begin with. We see we still have some of the state that's in here. Now, the state is in here because this is the rendezvous point. So we'll still have the star comma G. We still have some S comma G state in here, but with no outgoing interface list. So it's pretty much a stopped process. And then we do still have some out here for Ethernet 2/1 that's coming in from a different source. That state is coming in on Ethernet 2/2. As is this, right? So that's a different interface than where we applied the PIM policy. So we can see that none of this is coming in on Ethernet 2/1, which is where we were. So if we really wanted to kill all of the sources for this traffic, we could simply go into config mode, interface Ethernet 2/2, and we could reapply our policies. And do a show IPM route 239.1.1.1, and eventually these will age out. So it's just a timing thing right now. But we in essence have turned this router into this rendezvous point to where it will deny traffic for 239.1.1.1. So it'll eventually time out and die across the environment because of these ACLs. So a little bit more steps than what we saw with a traditional configuration on iOS or iOS XE, but still very, very possible to do equivalent of an IP multicast boundary function within NXOS. We're going to configure Cisco NXOS to have a PIM Protocol Independent Multicast neighbor filter. So let's get a look at our topology. We're on our data center AG01 switch in the lower left-hand corner of our network diagram. If we do a show IP PIM neighbors, what we'll see is that we have 3 neighbors. We've got our core router 1, core router 2, and then our data center aggregation switch 02 that's over to the right side of us. We're going to focus on Ethernet 2/1. We want to say filter out this particular neighbor. Now let's be fair and use this command with caution, because typically in an enterprise network where it's all under a common administrative control, you would have all of your devices become PIM neighbors. So that if in various failure states, the network would be able to converge and you wouldn't have RPF checks failing. But maybe this is a business partner zone or a co-location facility or a shared segment with other entities that you don't want to have a PIM relationship with, then that is where you would use this type of command syntax. So what we're going to do is a little different than what we saw on iOS and iOS XE. We're going to start using prefix lists and route maps again to do it in NXOS. And this gives us, again, a lot of flexibility, but it also is just some extra steps and a little different than what you might be used to with a traditional iOS platform. So we're going to go ahead and apply our configuration, and we'll just step through it and speak to what we're doing. So our first step is to define a prefix list where we just call it deny-neighbor, and then we tell it to permit 10.0.0.33, which means I want to match 10.0.0.33, right? So we're specifying, hey, I want you to take a look at this packet and permit 10.0.0.33, which means that we match it. And then we feed it into a route map where we call, I named deny-neighbor. Again, I like to make it consistent across the environment so that when you're looking at it in ODark 30 during an outage, you can easily follow the path through the network. And we're going to, again, deny sequence 5. We're going to match IP address prefix list deny-neighbor. So we're going to call this prefix list deny-neighbor, and this prefix list will only send us 10.0.0.33 for inspection. So then we're going to match based on 10.0.0.33 and turn around and deny it. So a little different way of thinking about it, but that's pretty traditional route map communications. And then we'll go to our Ethernet interface, Ethernet 2/1, and we'll apply it via IP PIM neighbor policy, deny-neighbor. And this is where it actually is applied to the environment. So we can do a show run interface, Ethernet 2/1, and see that it is configured on there. IP PIM neighbor policy, deny-neighbor. And if we do a show IP PIM interface, Ethernet 2/1, we can also see on here that we've got a PIM neighbor policy called deny-neighbor. Now, if we do a show IP PIM neighbor,
Unfortunately, this is a bit of a feature, jokingly referring to a bug, in this particular version of the simulation tool that I'm using, where the neighbor filters don't work properly. So we still have our neighbor filter, and even when the timer expires, the neighbor will continue to refresh. So these filters aren't being applied properly internally in the software. But this is how you would do it on a physical box. So the command syntax that we showed you is the valid command syntax, and it is how you would do it in a real world environment. But due to some limitations with the simulator, it's not possible to display this properly within the NXOS simulator. So, but you get the point and what we can do. And again, this shows you how to configure a PIM neighbor inside of NXOS and how easy that is. But as I mentioned earlier, it's important to use caution with this command. It's not widely deployed, it's not widely used, because typically you want to have a cohesive unicast and multicast topology in your network. And I think there's even a note in the Cisco docs that say that this command should be used by experienced network administrators only, or words to that effect. So this is definitely a very powerful command, but also can be useful if the environment is appropriate for it. So with that, you've been able to configure a PIM neighbor filter on Cisco NXOS.
So in summary, to be able to control multicast traffic, really the best way to enable yourself to be successful is to start with a plan, right? You need to know your requirements. You need to know what the business wants you to be able to do, and also understand what your game plan is for administrative scoping. Am I using it in my environment? Do I need to? Maybe I don't. If it's a smaller network, typically we don't see administrative scoping in those kinds of environments. Administrative scoping is something that typically is deployed in a larger environment where I need to be very granular with my traffic flows. But certainly, I've got options for both IGMP and PIM to be able to control where my multicast traffic goes. And now I can use both to meet my specific needs. So when we look at SSM from a high level standpoint, it's all defined in RFC 3376. And the idea is that we are able to build upon the existing foundation and success that we have with IGMP version 2 and be able to add some additional capabilities to provide controls to allow customers to be more granular with how they did their multicast deployments with IGMP and IP. So certainly from a high-level standpoint, the idea with IGMP version 3 is it now allows hosts to listen to a specific subset of sources when they join a group. And this gives us quite a few benefits. We take advantage of a new API called IP Multicast Listen for the receivers to indicate who they want to listen to, so they don't have to just blindly accept all the traffic that's in a particular group. And they're able to be very, very specific. So with IGMP version 3, though, there is a requirement that the operating system typically has to support it, and also the application. So you'll see this in newer environments. You typically won't see this on an older OS or on an older application, but rather, because that intelligence has to be built into the environment, it's only in the newer technologies. With IGMP version 3, we do have some new membership report addresses. We start to utilize 224.0022, which is all IGMP version 3 routers, to be able to figure out who is a member of the group. And we also changed some things around as far as report suppression. So we mentioned in IGMP version 2 that only one device on a subnet will be a responder to the IGMP reports, right? On IGMP version 3, everybody responds back to any of the queries from the designated querier, right? So that's a bit of a change, and we'll see what that looks like on the wire. So when we look at how a host joins a IGMP version 3 group, we see we've got a host up here running an operating system that's capable of IGMP version 3 that sends a specific S-G IGMP join to the network, right? So it's telling the network, I want to join this specific source and this particular group through that S-G mapping. And we also have additional attributes to that Multicast Listen API. Allows us to be able to say, I don't want to hear from these specific sources within the group, and I'm able to map that out on the individual hosts. And again, there is no report suppression, so on the wire, it's a bit chattier. But in the example that we see here, we've got, again, two sources with different IP addresses, 10.100.1.1 and 10.200.2.2, that are both joining the same multicast group. In this case, 224.1.1.1. So as a receiver, if I were IGMP version 2, I would receive the traffic from both of those sources. And maybe that's a good thing, maybe that's a bad thing. In this case, we'll assume that it's a bad thing because we're trying to illustrate the value of IGMP version 3. I'm able to say, exactly. So we're going to say that the receiver specifies, I only want to include traffic from 10.100.1.1. Don't send me traffic telling the first hop router, don't send traffic from 10.200.2.2. Right? That's the benefit right there. Additionally, when the hosts join a group, they'll send the report out to 224.0.0.22, and everybody will respond. We can also specify specific sources. In this case, we want to include 10.0.0.1. Maybe this is a host that has particularly interesting information for us, but we're able to include that so that we can only see traffic from that particular source. And again, only the included sources are joined, which also means that the amount of state that's in my network is going to be very, very specific as well, right? It'll be just that S, G for that specific source and that specific group. And then also, we're going to see that the traffic will take the shortest path tree. And then for another option would be to exclude sources. So maybe there is only one device that's joining a particular group that you don't want to listen to, but you still want to receive traffic from multiple sources. Maybe this is a market data feed, and I want to see sources from, or traffic from sources that represent these two different markets, but not from this market over here. I can exclude that from my feed utilizing the exclude when I semi-join. So I send it out at 224.0.0.22. I'm telling you I want to join group 224.1.1.1, but I want to exclude 7.7.7.7. I'm not interested in what he has to say, for whatever reason. All right, so and these are all capabilities that would be built into the application, right? So it's not just going to be randomly stuff that your user picks. You had a question?
Yeah. Suppose that you want to exclude something from multicast, but based on content, not on the location. In other words, there may be a different kind of feed from one location at a certain time, but it's a different kind of feed from another time. And you want to make sure you get the later one, but not the earlier one.
So the question is, can I dig a little bit further into the packet and exclude it based on content? With SSM, because it's a layer 3 control, we're bound to layer 3 requirements. So it's either based on IP address or DNS name, which would result in an IP address. So it wouldn't be able to say, well, I want to receive it, but only if it's from this particular source based on a cookie or something higher up that I see in the stack. So you'd have to put them on different groups or different IPs. And then, so in this scenario, all of our sources are joined except for the excluded ones. And then from a maintaining state standpoint, the router still sends the periodic queries, right? Just like we do with IGMP version 2. Is anybody still interested in receiving this traffic? The difference being in IGMP version 2, what did we say happens earlier? Only one of them responds, right? They pick one to be the response. And in case of IGMP version 3, they all respond. So when we start looking at some of the other capabilities with SSM, we see that, again, we use source trees only. We don't use that shared tree, which gives us some benefits, right? Because now I don't have to worry about having a rendezvous point and having state that lives in a shared environment and then switches over to the shortest path tree. It becomes very, very clean. It's source tree only. So definitely when you look at it from a speeds and feeds perspective, this is a very streamlined protocol, but it does require the host support for IGMP version 3, as well as the network needs to support SSM from a capability standpoint too. So we turn that on inside of each of the different platforms, right? So we'll see that in the CLI. The hosts, again, are responsible for source discovery, and that's typically done via it says out-of-band mechanism. That out-of-band mechanism is kind of like the application, right? Somebody somewhere has programmed and said, let's make it the easy button so that users are clicking on this feed and they only get this particular information, and all the network magic is happening behind the scenes. This is our world, right, where we look at it from an SSM standpoint in IGMP version 3, that we're able to see this happening. But we try to make it easy for the users. So from a kind of a overview, certainly the host will join a specific source within a group, right? So they'll join the specific S, G as opposed to star, G. And the last hop router will send the S, G join toward the source. So instead of sending it to the rendezvous point, we send it straight to the source because we know who the source is. We've signaled that we know who the source is. We're using IGMP version 3. We're using the new fields, the new APIs, so the router knows that. And definitely helps eliminate the possibility of content jammers, right? Especially on the global internet where you have all kinds of interesting people out there doing interesting things day in and day out. It's kind of the Wild West. If there were an analogy to the Wild West in a modern world, it's the internet. It's truly, if you're a service provider, you're just providing connectivity, man. I'm not filtering content. I'm not doing all these other things. There's all kinds of interesting things out there. Certainly, the possibility for somebody to jam your content or to flood a particular multicast group with traffic that you didn't want them to send is not too tough to do, especially if they're professional hackers. And we know plenty of countries have professional hackers. So certainly, this is an additional security mechanism. And then again, it also solves some of the addressing challenges. So being able to minimize the amount of address space that's required, because now I can be very, very granular and have almost sub-channels within a given group that my receivers can join. Gives me a lot of flexibility. I don't need to have 100 addresses for 100 channels. I can have one address with 100 channels and be very granular with how I distributed it. So in summary, for SSM, we do utilize the source tree only. Certainly, again, the hosts are responsible for all of the source and discovery mapping, and this is typically the application owners, right? They're the ones who control it, not necessarily the network administrators. We're just providing the pathway for them and the mechanisms. Definitely solves multicast allocation problems because now we can differentiate between sources and groups and sources within a group so that I can be very discreet with my content allocations. And example being content providers can use the same group range but then have different feeds based on regions or something else like we mentioned earlier in the design session, right? I can have a very consistent configuration, but have it be sourced differently in different locations. Helps prevent denial of service attacks, which is becoming more and more important for customers who are internet facing, and being able to filter out bogus source traffic so that it's not received by the host application and consuming bandwidth. So let's look at how we configure SSM in these different platforms.
In this video, we're going to look at how we configure source-specific multicast, SSM, holistically on a Cisco IOS device. And when we say holistically, what I mean is we want to look at it from a perspective of not only the layer 2 aspects with IGMP version 3, but also from a PIM, Protocol Independent Multicast perspective as well. So we'll begin with a router, and the one we're going to utilize is our Core 2 router that is on the center of the diagram on the right hand side. If we do a show run pipe include PIM, we'll see we just have a very basic PIM configuration that is just PIM Sparse Mode on all of the interfaces. We don't have a rendezvous point because if we recall from the lecture, source specific multicast doesn't use the rendezvous point at all. It doesn't use the same mechanisms that a traditional ASM environment uses. So there's no need for rendezvous point config, which also simplifies your environment, and that I also don't need to have support for MSDP or PIM Anycast RP. This makes SSM a pretty good option for customers to consider, especially if their applications support it. And that's probably the biggest sticking point with source-specific multicast today, is that you do have to have apps that support it. All that said, let's go ahead and take a quick look at the route table, because this will be something interesting that will change as we go through. And we see we just got some generic star, G state in here, auto RP, and then we've got a source sending on 239.1.1.2, which is not an SSM range. That's just a normal ASM range. So let's go ahead and apply our configuration, and we'll walk through it as we get into the details. Okay, so if we look at it from a configuration standpoint,
very, very important command, IP PIM SSM default. This is a lesson from the School of Hard Knocks. I forgot to put this command in when I was building my configurations and getting ready for this, and I troubleshooting my SSM and it just wouldn't work, and I don't know why, and on and on and on, and I realized, oh, I've neglected to put this command in. So once I did, it all magically started working. So very, very important command, IP PIM SSM. And all this indicates is what range of addresses we're going to utilize for source specific multicast. The default is 232.0.0.0/8. So the entire 232 range for SSM. And then what we're going to do is utilize our loopback interface on one of the routers, because I don't have an SSM3 client or an IGMP version 3 client. We're going to make one of our routers be an IGMP version 3 client, and we'll use a loopback interface. So IP IGMP version 3 puts it into SSM capable mode, right? Supports version 2 and version 3 IGMP joins. And then we're going to give it an IGMP join-group 232.1.1.1 and source 192.168.0.4. Now, this command is what's going to force this router to join this particular group, 232.1.1.1, which happens to be an SSM group. And we're telling that the source is one of our other routers, core router 1 specifically, 192.168.0.4. So if we do a show IP mroute SSM, what we should see is that we do have some state now. So we've got a S comma G. Remember that with SSM, there is no real concept of a star comma G state. And note that one of our flags is now a lowercase s, which also indicates sparse mode. So that's good to see that that's already picked up that we're using sparse mode for this configuration. So now let's go over to our core 1 router and do a show IP mroute SSM. And we'll see that we've got the state over here as well. So we've got a successful connection between the two of them. We've got the joins that have all happened. We have our lowercase s to indicate sparse mode, and we're in good shape. Now, if we really want to verify this is carrying or capable of carrying data, because we're not using a real host, we're using a router, we can always do an extended ping. And this is a pretty cool trick to do as well. We can do a ping, specify the protocol as IP 232.1.1.1. Let's give it a repeat count of 5. We're not going to be too hard on it. And what we'll see is that the router will actually join that group and send data back. So we're seeing that the recipient is, or the destination is, responding back to these multicast pings. So that's pretty cool to be able to test that as well. And that'll also, sometimes if you're trying to troubleshoot an issue, that will help force state to be created. So it's a good kind of trick to have in your tool bag as well. So, and that's really about it. That's I think one of the things that a lot of people get wound up about with SSM is that it's different, and that means that it has to be complicated. And what we find when you start looking at SSM is really that it's quite simple. We've removed rendezvous points, we've removed MSDP, we've removed the need for anycast. You know, we've done a lot of removal of extraneous things, and we've given us the ability to be able to have a many to one ratio of multicast groups to recipients, and not being able to specify specific hosts that we want to have groups join. So it's very, very powerful from that standpoint as well. So and with that, really, that's all there is. You certainly can implement some of the same multicast controls that we talked about in the multicast control section of the lessons, but there's nothing that's specific to SSM other than the IP address. So all of those same controls, the PIM adjacency neighbors and IGMP filters and all those other good things apply to SSM, just with a different IP address. So with that, you've kind of got a quick holistic look at how to configure SSM on a Cisco IOS device. In this video, we'll configure IP multicast and source-specific multicast
SSM mode on Cisco iOS XE devices. And we're going to configure this in a holistic fashion, and then we'll talk about how to configure SSM, not only from an IGMP version 3 at layer 2 perspective, but also into the Protocol Independent Multicast, the PIM components of it as well, so that we see it all together in one place in one video. So we'll start with our Edge O2 router, which is our router in the upper right-hand corner of our topology. And if we do a show run pipe include PIM, we'll see that we've got a very, very basic config here. We don't have a rendezvous point because, as you recall, sparse source-specific multicast doesn't require a rendezvous point at all. We don't have any MSDP config or any other extraneous anycast configs. It's just IP PIM Sparse Mode on all of our IP-enabled interfaces. So a very, very simple config. And what we can look at from a mroute table state is we'll see we've got some star comma G state from some of our ASM environments. 239, 200, 200, 200 is an ASM group that is connected to Gigabit Ethernet 4, and then our auto RP group at 224.0.1.40. So we're going to apply our SSM config on the iOS XE device, and we'll step through it as we apply it. So we'll begin with this very, very important command, IP PIM SSM default. I mentioned this in the iOS one, but in case you didn't listen to it, this is an important command because if you don't have it, your SSM won't work. So I was configuring these environments and getting everything ready for the publication here, and was troubleshooting why my IGMP joins weren't happening and why I wasn't seeing the multicast state that I expected to see and everything. And I realized that I had forgotten to put this in global config. So, learn from my mistake and benefit from it. This is very important, and you'll want to make sure you take advantage of that and have that in your configuration. But what we do next is we go into our loopback 0 interface, and we're going to force it to do IGMP version 3 mode, which means that now it would support both IGMP version 2 and 3. But what's funny about this is that it's a loopback interface. So it's a virtual interface inside the router. And the reason we're doing this is so we can have a IGMP version 3 join issued to simulate SSM traffic. So the next command is IP IGMP join group, and we specify an SSM group, in this case 232.100.100.100, and our source is 192.168.0.2, which is a loopback interface over on our our Edge 1 router that's in the upper left-hand corner of our topology. So this configuration is applied now. We should be able to do a show IP mroute SSM and see some state, and we see that we have an S comma G. If we do just a generic show IP mroute, we'll see that we don't have a star comma G for 232, 100, 100, 100, and that's back to its SSM. So we don't utilize those star comma G groups anymore. And we also note that we've got lowercase s on our flags to indicate that we are in sparse mode. So that's a pretty nice indicator there to tell us that we're on the right path and things are working the way we want them to. So we've got our state here. We can go over to our core 2 router, and this isn't our destination, right? This isn't where the loopback resides. But what I want to show is that we do have the multicast state in this one. Now, that's important because if you think about it, this guy just happens to be in the path between Edge 2 and Edge 1. It could have been Core 01, but in this case, it's gone over to Core 02. And we are building state for this group in this transit router. And that's important as a consideration for source-specific multicast, because now I'm going to have almost an explosion of state, if you will, because now I have all these S comma Gs, and there's a CPU and memory performance penalty to be paid for that, and you need to understand that when you make your design decision and criteria. But nevertheless, it's a good thing from a simplification perspective. You're removing a lot of the other aspects of the topology from the environment. And then we'll go over to our Edge 01 router, and we can do a show IPM route here, SSM. We'll see that we've got some incoming state here for the device, but we don't have a complete connection. And check this out. So here's a great example of why it's important to have this. IP PIM SSM default. Watch what this does. give it a moment here, and we should see some state come over from the router now. That it will be able to complete its join into that particular group. So again, it's important to have that in your topology so that you can make sure that you have. There we go. So that you can have a true SSM environment. So that router saw it as a star comma G. That was a red flag for us, right? That we saw 232.100.100 as with a star instead of 192.168.0.2. That's indicative of a problem, and lo and behold, we had a problem. So that's a great example. And we can see that our sparse mode flag is set as well. So all good from this perspective. So we jump back to our Edge 02 router. We can see that we've got our state here, and things are working as expected. So pretty straightforward. And as we mentioned earlier, it's definitely good to consider SSM for your environment, assuming your applications support utilizing IGMP version 3. You get a lot of reduction in network protocol complexity, but the trade-off is that you have additional network state. So you have to make that decision for yourself as to which is the best approach for your particular requirements in your environment, but know that you've got choices, and that SSM, based on what we've just seen, is very, very straightforward and easy to configure, especially in Cisco IOS XE. In this video, we're going to configure Protocol Independent Multicast in source-specific multicast SSM mode on Cisco NX-OS devices. So to begin, we'll connect to our data center AG02 router, which is in the lower right-hand corner of our network topology. And we're going to look at this SSM configuration very holistically. We're going to look at it not only from the IGMP layer 2 perspective for IGMP version 3, but also from a Protocol Independent Multicast SSM specific configuration. And if we recall back to our lecture, the key difference with the SSM is that we don't require the use of rendezvous points anymore. There is no RP config in an SSM environment, and that's one of the benefits that it brings to the table. The trade-off is that it creates additional state for all of the different flows in the environment. So all of the S, Gs in your network start showing up in more places maybe than they used to when it was on a shortest path tree or a shared tree environment in ASM. But the trade-offs usually are worth it for many of our customers. So we'll begin to look at the configuration here and do a show run PIM, and we can see we've got a very, very basic configuration. Sparse mode on all of our interfaces, PIM is enabled. This command, this IP PIM SSM range, is in there by default. We don't configure that. That's there just out of the box. If you need to change the range of addresses you want to use for SSM, you need to change that statement there, as well as on any of the other platforms in your environment. So this is the default that's specified via the RFC. So most customers typically don't mess with that range of addresses at all. And we can see that we just have sparse mode on all of our configs. So what we're going to do is apply our configuration, and it's a very, very simple configuration in NX-OS. So we go into our loopback 0 interface, we specify IGMP version 3 to support version 3 as well as version 2 joins on this particular interface. And we are doing a bit of a pseudo interface or a pseudo config because the platform itself now, this data center AG02 switch, will be joining this IGMP group 232.200.200.200 as a client, which is typically not what routers do. They're traversing traffic that traverses them, but not necessarily do they participate in the traffic. In this case, we're going to do this so we can create the state that we need in the network. And we tell it the source is 192.168.0.3. That happens to be the loopback interface on data center AG01. So if I do a show IP route, what I'll see is that I have state. I've got an S, G for 192.168.0.3 to 232.200.200. And that we have this state in our environment. I can also do a show IP IGMP groups, and I'll see that we have this particular group that's being joined as well. And it also notes that it's a local interface or a local IGMP, which is typically different than what we see with a dynamic or a static environment. But certainly this is exactly what we wanted the platform to do. So we can do a show IP route and look at it from a source tree perspective and go into detail, and we can see some additional information, right? So we can see some statistics right now. Obviously there's no traffic going on because this is just the router joining that particular interface. But you know, and if this were a
environment where you were sending traffic, these counters would increment and you could get some additional input as to what's happening on the environment from that perspective. So pretty neat capability, but a very different display than what you saw in iOS or in iOS XE. So now if we go over to our data center AG01 router, we can do a show IP M route, and we can see previously we just had some star comma G state for our environment. We had a star comma G for the SSM environment, and now we have a specific S comma G for the other router joining the group. So we've got a successful connection between the two of them, and things are shaping up the way they want them to. So pretty easy to deploy source-specific multicast, and that's really one of the reasons why customers are starting to consider it, because they're looking to get away from the complexity that MSDP brings and having to have Anycast RP and all of those other kind of routing gymnastics that we did earlier to be able to have rendezvous point redundancy. What if I don't have rendezvous points? What if I have an environment that supports the amount of state that I have from a multicast perspective? I get a higher performance environment without having to have a lot of additional state and there's a lot of additional configuration in my environment from a control plane protocol perspective and things of that nature. So it's becoming much more popular with a lot of our customers. With that, you've been able to see how simple it is to configure SSM on a Cisco NX OS device. So in summary, for source-specific multicast, it definitely is an alternative for ASM, any source multicast, right? Which is all the other protocols we've talked about. So when you look at it from a big picture standpoint, ASM, SSM being kind of the two big groupings. ASM is everything else. SSM is what we just covered. It certainly is an alternative for those. It does require support on both the host and the last hop router, right, to be able to signal and understand IGMP version 3. So it may require a code upgrade in your environment to support IGMP, or as we showed in the CLI, in most cases you just have to turn it on. IGMP version 3, hit enter, and you're done. Some of the benefits is that it removes the need for rendezvous points and RP redundancy. So as we talked about in one of the previous sections with RP engineering, there can be a lot of considerations with regards to RP environments, whether I'm using static RPs, auto RP, BSR, or if I'm using Anycast and MSDP. Those are things that I have to configure, manage, and maintain in my environment. If I go to SSM, because my application support it, my host support it, my network supports it, I can remove those requirements from my network. So, and still, certainly, it's not as common as ASM, although I suspect that will change over time, right? As more and more people get comfortable with it and deploy it, we'll see it deployed more. Yes?
Will this also reduce the overhead?
Correct. So the question is, will this reduce the overhead? It certainly reduces the amount of state that's stored across the entire network, right? Because we now just have S comma Gs. S comma Gs everywhere, as opposed to star comma G, switching from the shared tree to the shortest path tree, and that kind of state fluctuation and churn. But if I have a lot of multicast senders and receivers, I'll still have S comma G mappings. So I don't get away from all of those, but it can reduce the amount of state that's there. Yeah. So in lesson 7.1, the IPv6 overview, we'll start to talk about the different address families that are part of IPv6. And it is truly an address family. It's not just an addressing scheme or an address layout the way we're sort of used to with IPv4, but rather we've got the concepts of multicast and unicast built into it, as well as Anycast day one. These aren't technologies that were added after the fact, but they were baked into it from the very beginning. And within them, we've got some well-known assigned multicast addresses, as well as solicited node addresses. And then inside of the unicast family, we've got unique local, link local, global, special, and embedded. So there's a whole new plethora of addressing schemes and technologies and considerations for us to keep in mind. So we'll focus primarily on multicast, but I wanted to provide a bit of a background for this so that we can understand the scope of what we're talking about. Certainly from an IPv6 standpoint, for those of you who aren't familiar with IPv6, they are 128 bits long. Compare and contrast that to IPv4. IPv4 being 32 bits long, IPv6 gives us some significantly larger address space, to the point now where people are saying we don't need to really worry about being logical or very conservative with our address allocations, we can just deploy it to everything because there's enough addresses to keep us busy for a long, long time. Although I have to suspect in 30 years, people are going to look back and be like, what were they thinking, just giving everything an IPv6 address? Then they know they need to conserve them. There's only so many. There's a finite number. Now we got to move to IPv10 or 8. So there's a career path for those of you who are younger. You can learn IPv6 and then roll that knowledge into V8 or V10 later on in life. Some of the changes, though, with IPv6 is that we do have hexadecimal values in our addresses. It's no longer just normal decimal values, right, 0 through 9, but now we can start to have hex characters appear as addresses. So it's a very different look and feel from a configuration standpoint. We also have some shorthand available to us to be able to distill addresses down, and we'll go through that as well. But we can see this is an example of an IPv6 address down across the bottom, the 2001 : etc. number is a V6 address, right? So compare that to 192.168.1.1, kind of rolls off your tongue. How does this roll off your tongue? It's a little bit different world, right? So the good news is that there are some shortcuts that we can take in expressing different types of addresses, and we'll see how that can distill down in just a moment. We mentioned that there are some predefined address families inside of IPv6, especially inside of the unicast space. Link local, much like we mentioned earlier for that TTL of 1 in a multicast domain, there are link local addresses that are used inside of IPv6. And they all begin with FE80. So get used to seeing these hexadecimal values in the addresses. It's not intuitive if you've been working with IPv4 for a long time. But we can see that those link local addresses are designed to only exist between two different devices, right? So there's a lot of them. Unique local can be defined as routable within an administrative domain, and we see these as FC00/7, and then we've got our global address space 2000/3. And that's a big chunk of addresses, right? So start thinking about Internet of Things and some of these emerging technologies where cars will have multiple IP addresses, or working with some of our military and DoD customers, the soldier of the future has potentially hundreds of IP addresses that are associated with different pieces of armor and equipment that they're carrying. So that opens up a whole new world of possibilities that the customers haven't typically been used to having, based on the virtue of just the volume of address space and the overall desire to connect everything to the internet. So when we start talking about shorthand for IPv6, this is where it gets a little bit simpler for some of us to utilize. So if I take the full address across the top, that's a bit of a mouthful to say and certainly to write. And if your typing skills are like mine, that's going to be at least 3 or 4 times of typing that in before you're going to get it right the first time, right? So what if we can abbreviate that a little bit easier? So we've got a couple different options. We can utilize :0s, like we've shown over here in the middle one, to be able to eliminate sequential patterns of zeros, right, that are together in a word in a group of 4. Or even the better shorthand for somebody with my typing skills would be a double colon, indicating that all of those spaces in between are indicative of zeros. So there's some pretty cool shorthand that we can use to make it easier and less typo prone for addressing. It's also a little bit easier to discuss if you have to talk about IP addressing with your colleagues. So when we look at IPv4 and v6 from a multicast standpoint, there are some differences. And this is a great side-by-side comparison chart. We see that obviously the addressing space is different, 32 bits versus 128 bits, but we also see from a routing perspective, there are some differences there as well. There's protocol independency with IGPs and BGP, also being able to utilize v6 SAFI in IPv6. From a forwarding paradigm perspective, we've got dense mode, which we already said earlier, dense mode bad, sparse mode good. We still remember that, right? So that's always important to keep in mind. There is no dense mode option for IPv6. That should give you a hint to how bad dense mode really is. They didn't even carry it forward into v6. They did carry forward sparse mode in just generically ASM, any source multicast, as well as SSM and BiDir. So those are still very relevant technologies, not only for v4, but v6. And you'll see that there are a lot of parallels as we move forward into the details. The concepts that you know for IPv4 will apply in a v6 multicast routing world. From a group management standpoint, we no longer have IGMP. We have what's called MLD version 1 and 2, multi-layer discovery. We also have the ability to be able to do domain control. We talked earlier in one of the lessons about multicast boundaries and being able to use ACLs to provide those boundaries. We've got a concept of a scope identifier inside of IPv6 multicast that allows us to be able to be granular in defining where that multicast traffic can go. So the good news is a lot of lessons learned from v4 of things that we could do, but maybe weren't necessarily easy to do. Let's try to make them easier in v6. So we certainly took that into account. And then also being able to utilize MSDP in v4 and shifting that into a single RP with globally shared domains. So now we can add additional or remove additional complexity from our environment by moving to IPv6. So let's look at the multicast addressing. So all of our addresses inside of IPv6 will begin, in a multicast domain, will begin with FF00. They all fall into this range. So it becomes easy to start to scope them out. Much like we talked about earlier, class A, B, C, D, E, we've got a specific prefix with a lot of addresses in it for v6. And we can see the breakdown as far as which flags are part of the different options available to us, as well as the scoping, whether it's node level, link level, subnet, etc. Right? You can see that these controls are built into the addressing inherent as well as the protocol. What's important to note, specifically in the 4 bits following the first 8 bits, is that we've got a feature called embedded RP. Embedded RP is a great capability that's built into IPv6 that allows us to be able to start to get away from Anycast and MSDP and all these other technologies, but rather use the embedded RP option. So we knew that there's a requirement for rendezvous points. How do we make sure that we have that built into the protocol day one so it doesn't have to create a whole new subset of technologies and protocols like we did in IPv4? So when we look at some of the well-known multicast addresses, FF02 is a permanent address and is definitely link local. And we can see some of the different common ones for OSPF version 3, right, to be able to route IPv6 subnets in an IP routing domain. We've got an address for designated routers, RIP-NG, which, believe it or not, RIP just will not die. It's one of those protocols where everybody loves to make fun of it, but it's still around, so it can't be that bad. But it's still not as preferential as a link state routing protocol from a convergence standpoint. But nevertheless, and then we also have EIGRP addresses for customers who utilize the EIGRP routing protocol. So these are all built into IPv6 kind of out of the box. From a multicast standpoint, remember we mentioned in v4 that we lose 5 of our bits mapping from that 32-bit address into 28 bits. So what do we do in IPv6? Well, the problem still exists. We lose 80 bits this time though, so it still hurts, right? So we still have our oversubscription ratio, but there's so much more address space that it doesn't hurt nearly as bad. So it's a little tough to see, but 1 in every 2 to the 80th power will conflict. Probably a pretty good chance that you're not going to have conflicting addresses unless you try really hard. So good news is there's plenty of address space with v6 that we don't have to worry about it a whole lot, but certainly it's still a consideration and something to be aware of. And if I were a test-taking kind of person, I would imagine that maybe some of these might show up on a test. So I know I would ask that question if I were writing a test on v6. So let's talk about v6 routing for multicast. What options do we have? Well, we still have our reverse path forwarding check based on reachability to the v6 source. That part doesn't change. I still want to be able to have that RPF, same as we had in v4 multicast. So our reverse path forwarding check is still protocol independent. It's not tied to OSPF or EIGRP or RIP-NG or anything else that's inside of v6. I still have my static routes or my static M routes, right? So I still can do all of the static routing that I want to my heart's desire with all the same pros and cons that you have in a v4 space. And you'll see a lot of these similarities and parallels to the v4 space from v6, right? So the same considerations. Static routes are great. There's not a whole lot of convergence with them, but the con would be that it's a static route. So if my network changes and the static route doesn't change, I either black hole traffic or I cause some additional configuration work to have to happen. I still have unicast routing protocols, whether it's BGP, ISIS, OSPF, EIGRP, all the favorites, right? Everything you know and love, you still have all of those available to you in IPv6. We also have multi-protocol BGP for inter-domain routing of multicast inside of the global internet, or for MPLS networks that are utilizing MPLS for tag switching. And then also support for v6 multicast sub-address family. So again, based on the addressing scheme, I can be very granular in how I lay out my addressing. So a whole new plethora of RFCs to read and love. So sparse mode defined in RFC 4601 for v6, so it's a little different than what we had for v4. We had to lay it out in a new RFC. We also have 3569 for SSM Overview. v6 SSM does require MLD version 2, much like we had IGMP version 3 for SSM in v4. Similar approach with v6. And then bidirectional PIM right now is in a draft state, so we'll see how that plays out over time. For our RP mapping options, a lot of these sound pretty familiar, right? Static RP, like we talked about earlier. BSR is certainly an option. Auto RP, no current plans. Auto RP was a Cisco proprietary implementation, right? Remember the Cisco announced the Cisco discovery groups that we would join. Those aren't there in IPv6, but we do have a new option, embedded RP. You know, you take the good with the bad. When we look at with the embedded RP, embedded RP is defined in RFC 3956, and the impetus being on that we're utilizing the RP addresses built into multicast, so we're able to specify in our multicast address as part of those flags that are in the header where the RP is or who the RP is. All right, so now I can be able to have network prefix specific RP addresses and being able to be granular with how I deploy this. So I get some of the same controls I had with all my other RP mechanisms previously, but now I can utilize some inherent capabilities in v6 to get those. So when we look at the each unicast prefix you own, because the RP is embedded into the addressing scheme, you have 16 RPs for each of the 16 multicast scopes with 2 to the 32nd power multicast groups assigned to each RP. So probably will meet most customers' needs for group management for a while, right? It's a lot of space. That's one of the things I think makes IPv6 so tough for a lot of people to get their head around, myself included, is that just the scope of it is so huge. You start thinking about 2 to the 32nd for multicast groups. Yeah, we get nervous when we see customers have groups that are in the thousands. Maybe anything above 10,000 is like, wow, you've got a really big multicast network. Here we're talking 2 to the 32. That's just almost a mind-boggling number. But what we can see is that when we start talking about multicast with embedded RP, we can see from the various flags and the network prefix what the resulting RP will be. So it becomes very, very deterministic, right? So it's easy to program into ASICs, it's easy to write in software, and it's easy to know what it will be at any given point in time based on my network. So here's the kind of the breakdown as to how that comes into play and how it results in the RP that's actually utilized for that particular domain. We mentioned MLD earlier with regards to IPv6 at layer 2. MLD, Multicast Listener Discovery, is very equivalent to IGMP and IPv4. So it's very similar from that perspective as far as its roles and responsibilities, signaling group membership and things of that nature. All of our MLD messages are transported over ICMP version 6. Certainly there can be some confusion numbers with their versions, right? Force of habit, just from a mnemonic standpoint, says that, well, MLD1 should correspond to IGMP version 1, but the reality is it corresponds to IGMP version 2, right? IGMP version 1 left a lot to be desired and is pretty quickly deprecated for favor of V2. Similar approach, right? In that we've got MLD version 1 is mapping more closely to IGMP version 2. And then MLD version 2 corresponds to IGMP version 3, where we get the SSM capabilities. So similar approach in IPv6. So don't fall into the trap of MLD version 1 maps to IGMP 1 and MLD version 2 maps to IGMP version 2. That's not the case. It's +1, if you will. Because if we can make it easy, we wouldn't want to do that. Hard is where we want to be. So if there's that little nuance or detail, that's always good to know. And then finally, there is a draft for MLD snooping for switches to be able to provide a similar benefit and functionality for multicast listener discovery that we have with IGMP snooping for switches, right? So we can eavesdrop on those conversations and make the appropriate IPv6 multicast forwarding decisions based on group membership and who's interested in what.
In this video, we're going to take a look at configuring IPv6 on Cisco IOS with a focus on multicast. So to begin, we'll start with our core 01 router, which is in the center of the topology on the left-hand side. And we do a quick review of the configuration. We can see that there are no IPv6 M routes in our table. We do have an IPv6 network configured, so we can do a show IPv6 OSPF neighbors, and we see that we do have an IPv6 environment, which in and of itself inherently does have some multicast functionality embedded in it, but we still need to configure multicast specific capabilities in the environment, much like we do with unicast. And what we'll see as we go through these exercises is that there are a lot of different options for configuring IPv6, but they're all very similar to the concepts that we use in a IPv4 unicast or multicast environment. So what we're going to focus on are things that are different or unique to IPv6. So we'll look at IPv6 MLD functionality initially, and then we'll shift our focus to the embedded RP functionality that's part of IPv6 as well. So that way we kind of compare and contrast some of the newer things that are present in v6 with what we already know from our v4 experiences. So let's go ahead and begin. We'll start by applying a configuration. And much like we did with a traditional iOS unicast routing environment, we'll do IPv6 multicast routing. And without this, we don't have any multicast functionality really for v6 embedded in the network other than what's present with just the generic out-of-the-box v6 implementation for link local addressing and things of that nature. So this is an important step to do. Otherwise, you run out. You don't have anything to really take a look at. So let's start off by taking a look at some v6 capabilities for MLD, and let's take a look at our interface gig 01, for example. And we can see that we do have MLD enabled on this particular interface, and that now it's configured for version 2. Now, if we recall back to the lecture, there are two versions of MLD, MLD version 1, MLD version 2, and the differences really come down to comparing and contrasting IGMP version 2 to IGMP version 3. And to make things more exciting for us in the networking space, MLD version 2 aligns closer to IGMP version 3 for source-specific multicast specifically, compared to MLD version 1, which more closely aligns with IGMP version 2. Now, much like in the IGMP space, MLD version 2 is backwards compatible with MLD version 1. So we can see the default on the iOS platform is to default to MLD version 2 because it will still work with other MLD version 1 capable devices. So let's take a look at what else we can see here. We can do a show IPv6 MLD groups, and much like IGMP, we can see that we've got some groups configured in this environment. Some of these are static groups that are configured just to create some CLI output for us to look at. But these are just local groups that are present on the environment that are being learned via MLD. And then we can do a show IPv6 MLD traffic. And this is useful for troubleshooting, being able to see the different types of MLD
traffic that's present in our environment, whether that's queries and reports and leaves and joins and things of that nature. So there's some good detail here that's available to us. But much like IGMP, MLD doesn't have a ton of options for us to do, other than the fact that it's there and it's important for it to work. We can always do some of our filtering and scoping, much like we did in the controlling multicast portion of the lessons. But because those functions or those processes are exactly the same to the v4, we won't really cover them in here, just because the only thing that's different is the IP address, is having it be a v6 address versus a v4 address. So same concepts apply though. Now, if we want to get a little bit more exciting, we can do a show IPv6 PIM neighbors, and we can see that much like we used Protocol Independent Multicast in a v4 environment, we utilize PIM in a v6 environment as well. And we can see that we've automatically formed some multicast neighbors, PIM neighbors with different devices on our environment, and that their the various interfaces and their IPv6 addresses are listed here as well. So similar to what we're used to seeing again. And then finally, we can do a show IPv6 M route and start taking a look at our routing table. And much like it does in a v4 unicast or a v4 multicast environment, we've got some additional detail here for the v6 environment. Now, this is a little funny in that one of the things that we talked about is that v6 from multicast standpoint doesn't support dense mode. So, you should never see a dense flag on any of your v6 multicast. If you do, something is really, really going wrong in your environment. But we still have the exact same output as far as what we can expect to see: sparse mode, BiDir groups, SSM, etc., albeit on a v6 address. So we can see some multicast route state here as well. Now, one of the things that we want to do from a rendezvous point standpoint is we talked in the lecture about the different options that we have available to us. Certainly we can go with Anycast RP, which is a pretty common deployment, or we can leverage static RPs as an example. One of the unique features of v6 is that it supports the concept of an embedded RP. And the embedded RP is a capability that allows us to be able to, by virtue of the addressing that we utilize, determine which RP is responsible for a group of addresses. So it becomes embedded into the environment and kind of inherent as to where my RP is. And we'll see how this works out for us as we go through the examples. It's a pretty nifty feature. So we'll start by saying, let's look at this particular group, and we want to see who the rendezvous point for this particular group is. And we can see that there's nothing, right? So we see that it's part of the entire range. It's a sparse mode that's default, and that there's nothing there. So this group doesn't have a rendezvous point defined at this juncture until we get done with our configuration. So now, if we look at it from a defining a static rendezvous point for this environment, what we'll do is we'll leverage the concept of embedded RP. So by virtue of our addressing scheme, and this is straight out of the RFC for embedded RP, so this isn't anything magical or mystical that I've done here, but by virtue of the RFC 3956, we're able to determine that this address can serve as a rendezvous point for this range of addresses, and the whole formula is worked out in the RFC, and so you can find it there if you're really interested in it. But know that that's how this is working. So what we're going to do is we're going to assign this IPv6 address to our loopback interface. So much like the same concept that we do in a v4 environment, let's use a virtual interface for our rendezvous point, so that as our network converges, we have a better likelihood of being able to connect to it. And then we're going to define a static RP address, and this looks very similar to what we did in the v4 environment. The difference being that it's IPv6 and we have an IPv6 address at the end. So same concept and same approach that we took earlier, just in a v6 flavor. The difference being that we're going, because of the address we're using for our rendezvous point, we're also able to have that be part of the embedded RP functionality. So if we go back to our previous command, show IPv6 PIM group dash map v6 address, and now take a look at it, we can see that we've got some additional detail, right? So now we see sparse mode. Our rendezvous point is this address, the 2001 DB8:1, and our RPF is DB8:1 as well, which is us, which means it's local. So that's not terribly surprising considering that we are on the particular box we just configured as the rendezvous point, and that the source info is static. So that's pretty neat, right? Because of the addressing, we were able to figure out where our rendezvous point was to this particular environment and provide that information. Now let's take this one step further though and take a look at it from a standpoint of another switch that doesn't have a rendezvous point configured on it. So we'll connect over to our Core 2 platform and let's do the same command. So look at the group, show IPv6 PIM group map and then the IPv6 address. And we'll see that this has been able to determine that the rendezvous point is 2001 DB8 and that it was learned by virtue of being an embedded address. So this is already there. This happened by default. I didn't have to configure any rendezvous point here. So let's do a show run pipe include RP. And we'll look for any hint that maybe we've entered, IPv6 rendezvous RP address. And what we'll see is that we don't. The only thing that we see is in our messages in our banner, right? That are part of the purposes, right? So the purposes is what's triggering the match here. So we haven't configured an RP, but because of the virtue of the addressing, we're able to find that RP as an embedded RP. And this is a pretty cool capability. Imagine what this does from a simplicity standpoint in your environment. By virtue of the addressing that you use, you don't have to configure the rendezvous point on every device in your environment anymore. That's a big change from IPv4. So that's a pretty cool capability. And as I mentioned, the rest of the v6 multicast capabilities are very similar to what we had in a v4 environment. The same concept of anycast, the same concept of auto RP and BSR, all of those capabilities are part of v6 as well, just not in an environment where we're going to configure them in this topology, just because we've already done most of that work in the other examples as well. I wanted to pull out what was unique to v6 and really focus in on that. So with that, you've configured some of the new unique v6 capabilities in Cisco IOS for multicast. In this video, we'll configure IPv6 multicast capabilities on Cisco IOS XE. So to begin, we'll connect to our edge router, which is in the upper left-hand corner of our topology, and we can do some basic show commands and see that we have a already established IPv6 environment. So we do a show IPv6 OSPF neighbors. We'll see we've got a neighbor. We can take a look at the IPv6 mroute though, and what we'll see is that we don't have any multicast routes yet. We haven't configured any v6 multicast routing other than what's already part of v6 inherently because of its multicast capabilities, which are mostly link local addresses and things of that nature. So much like in a unicast or a multicast v4 environment, we want to be able to configure multicast specific routing capabilities inside of IOS XE. And much like traditional v4 unit multicast environments where we have capabilities like auto RP or BSR or anycast, we're not going to configure those in this environment. We're going to focus on specific things that are new to v6. And one of those is the concept of MLD. And the idea that we want to reinforce with MLD in a v6 environment is that we are able to see that there are multiple different versions. And specifically with MLD, Multicast Listener Discovery, the idea is that we've got two different versions, version 1, version 2, and version 2 is backwards compatible with version 1. So we'll see the defaults when we go through this configuration right now. So if we do a show IPv6 MLD groups, we'll see we don't have any groups that we're learning. We do a show IPv6 MLD interface, and we'll see that MLD is disabled on all of our interfaces by default. So this is the default out of the box. So what we need to do is start to configure this. So let's begin by going into config mode. And we'll do an IPv6 multicast routing. And that process in and of itself will start to enable the v6 functionality in this environment. So now, just for the sake of information, let's go ahead and we are going to configure a join group, a static join group on one of our gig interfaces, just so we can get some state to take a look at. But if we do a show IPv6 MLD group, what we'll see now is that we're learning other MLD groups. These are being advertised throughout the network and are things that are coming into the environment all off of Gigabit Ethernet 3. And you can see specifically the 2999 is the one that we've configured, but the other two have been dynamically learned in this environment. So the 222 and the 6666 have been learned by virtue of MLD. So now we can take a look at some of the other capabilities in the environment and do a show IPv6 MLD traffic. Much like we saw in iOS, we're able to take a look at some of the statistics for MLD in a iOS XC environment and see what's happening from a queries and reports, and be able to help operationalize our environment, make it easier to troubleshoot if things aren't working the way we want them to. And then also we can do a show IPv6 MLD interface gig 3 and see some information on the interface. So we can see that the default in iOS XE without specifically configuring it is MLD version 2, which is good because, as I mentioned, MLD is backwards compatible from version 2 to version 1, and version 2 is the equivalent of IGMP version 3 in a v4 environment. So that gives us our source specific multicast capabilities and things of that nature, but then also being backwards compatible so that we if we don't have SSM, we can still support the traditional MLD version 1 clients and devices. So we have this in our environment now. So now if we do a show IPv6 mroute, we can see that we've got some additional route state as well. And much like in a traditional v4 multicast environment, v6 multicast state is equally important from a standpoint of being able to scale and converge the network. So much like we do in a v4 environment, we want to be cognizant of the choices we make from a design perspective as to which and how much state we have in our environment at any given point in time. So that being said, so let's get a little bit more exciting. Let's shift our focus to rendezvous points. So much like we do with a rendezvous point in a unicast environment, we can configure rendezvous points inside of a v6 environment. Now, what's exciting about this from a v6 standpoint is that IPv6 gives us the capability to leverage a feature called embedded rendezvous points. And the embedded rendezvous point, by virtue of the addressing that's utilized, will be able to dictate who the rendezvous point is without us having to configure it on all the different devices. So let's take a look at this example in real life and kind of help reinforce this. So we'll start off by saying we want to find out who the rendezvous point is for a particular group. So let's go ahead and paste in the command, show IPv6 PIM group-map, and then the IPv6 group. And we can see that the rendezvous point would be this particular host, and that's a static configuration, right? So this has already been configured on loopback 0. So if I do show run int loopback 0, we can see that we need to configure it on loopback 0. So let's go ahead and apply some configuration here. So now, when we do, one last piece of detail. Always important to have all of your CLI, not just portions of it. And then we'll configure a static IP address. So what we've done is we've configured an IPv6 address to be 2001 BD8:222/128 on our loopback, and then we've configured our v6 PIM RP address to be that same address. So now we're telling the v6 network that the loopback interface on Edge 01 is the RP address for this range of addresses. And the key part is for this range of addresses. Because we're using embedded RP, the addressing scheme dictated in RFC 3956 tells us what addressing scheme or what address we can use that will map to a range of addresses. So by virtue of the addressing choices we make in our environment, we're able to influence and dictate who the rendezvous point will be without having to configure it. So this is pretty slick. So we'll go ahead and now take a look at the syntax of this command, or the output that we get here for the show IPv6 PIM group-map IPv6 address. And now we can see that the rendezvous point, while it had derived it, now knows that it's reachable via RPF and that it's static. So that's pretty neat, right? But that's also kind of local to us. So how helpful is that? Well, let's go a little bit further away. Let's go to Edge 02, which is a different router. It's over on the right-hand side of our topology in the upper right-hand corner. And we can see, if I do the exact same command to look at the PIM group map on this platform, what we can see is that it was able to dynamically source this and realize that this is a sparse mode group, that the rendezvous point is this IP address, which is the IP address of the loopback on the other router, and it learned that by virtue of the embedded RP capability of v6. So imagine the capabilities that this brings to the table, where now you can start to have a v6 rollout in your environment without having to touch every platform and configure static RP on it, much like we did with a static RP configuration inside of iOS. Or with a v4 environment specifically. So this gives us a lot of new options and a lot of configuration minimization that allows us to be able to simplify the administration of our networks day in and day out. So as we mentioned, there are options to be able to support other rendezvous point redundancy technologies, whether that's Anycast. I guess Anycast is the primary RP redundancy capability, but then also Auto RP and BSR to support finding rendezvous points in the network. But we're not going to belabor those for v6 because from a capability standpoint, they are all part of configured more or less the same. The difference being that it's a v6 address as opposed to a v4 address. So we really wanted to focus in on the embedded RP capability and MLD, multicast listener discovery, to be able to provide that kind of laser focus that you're looking for on the v6 technologies to reinforce what we already learned for a v4 environment. So with that, you have now seen how easy it is to configure MLD as well as basic IPv6 unicast routing with embedded RP on a Cisco IOS XE device. In this video, we're going to configure IPv6 multicast functionality on a Cisco NXOS device. So to begin, we'll connect to our data center AG01 router, which is in the lower right-hand corner of our network topology diagram. And we're going to take a quick look around and see that there isn't any PIM or IPv6 capabilities other than the capabilities that we have for OSPF v3 for a generic IPv6 implementation. So if we do a show IPv6 OSPF neighbors, we can see that we've got some v6 neighbors established in this environment, and that we've got a generic v6 capability already turned on in the network. Now, certainly v6 has some embedded multicast capabilities in it, but we also need to configure some specific multicast capabilities to really get full multicast routing, because the embedded functionality, the inherent functionality of v6 still is primarily using multicast for kind of administrative purposes, right? So we want to use it for data plane functionality and be able to really turn on all of the features. So to do that, we need to enable PIM version 6. And what's unique to NXOS, and we saw this earlier with regards to configuring it in a unicast or in a v4 environment, is that we have to enable the feature. So that'll be our first step in our configuration, is that we will go ahead and enable the PIM feature. So let's walk through the configuration as we apply it. So we're going to configure, go into configuration mode, enable feature PIM 6. This turns on the Protocol Independent Multicast capabilities for IPv6. And in this case, it gives us a warning because we don't have a permanent license. That's no problem. Hopefully in your environment, if it's a production environment, you'll have a license, so that'll work for you. We also specify the v6 SSM range of FF30::/12. So that gives us that entire range of addresses for source-specific multicast, and that's per the RFC for IPv6. So nothing magical, mystical there. And then, much like we did for a v4 environment, we are going to enable PIM Sparse Mode on our
various interfaces, so for IPv6 specifically. Now, if you recall, in the iOS and iOS XE section, we didn't have to do this. This is unique to NXOS, and that we need to enable this PIM v6 functionality. But we can now start to take a look at some of our CLI output and see what's happening from a v6 standpoint. So if we do a show IPv6 PIM neighbors, we should see some neighbors. We've got neighbors on Ethernet 2.1, 2.2, and 2.4. These are the other routers in our topology, so nothing terribly surprising there. But you can see that as typical in XOS, it gives us some additional functionality and visibility that we didn't see in a traditional iOS environment. We've got BiDir capable, and we've got BFD state that's shown on this command. So it gives us just additional detail. And we can do a show IPv6 MLD groups. And we can see we're dynamically learning some groups via Ethernet 2/1, which is one of our upstreams to that core 1 router. So he's advertising some local MLD groups for multicast listener discovery. And we can also do a show IPv6 mroute. So we can see here some additional state, and much like we saw in a v4 configuration, the table output here looks a little different than it does in iOS. iOS has a nice table at the top that shows all the different flags and things. You can see those flags are not being used here. What we are showing is that we're learning this via PIM6, so it's being learned via PIM, and it's obviously IPv6. So, but not as detailed as some of the other options that are out there on iOS. And we can also do a summary to get traffic statistics off of it as well. If these were active sources, these counters would obviously increment. That's kind of a basic functionality that we've enabled here in NXOS. Now, one of the things that we mentioned in both the lecture as well as in the iOS and iOS XE capabilities was the function of being able to utilize embedded RP inside of a v6 addressing scheme. And that's very time-saving and conducive to a large-scale v6 rollout, because now I can allocate RP resources without having to create just additional interfaces, but rather utilize an existing loopback and have it be automatically discovered by virtue of the addressing scheme throughout the environment by embedding that as part of the multicast addressing per RFC 3956. Unfortunately, NXOS does not support that capability yet. This is not an RFC that NXOS supports, so hopefully that'll be coming in the future. Certainly something you'll want to check the release notes on and keep an eye out for, but unfortunately that capability is not implemented in NXOS today. But with regards to other rendezvous point capabilities, certainly we support static RP in NXOS, as well as the ability to be able to use Anycast RP. And those are configured just like they are in a v4 world, just with an IPv6 address. So there's not a lot to show from that standpoint, other than it's the exact same CLI that we used in a v4 world with a v6 address. And the unique capability of embedded RP, unfortunately, isn't there in NXOS today. So, but with that, you've been able to see how to configure basic IPv6 multicast functionality inside of Cisco NXOS.
So in summary, when we talk about IPv6 from a multicast standpoint, certainly IPv6 in and of itself has a massive address space. It's almost an impossible number to kind of really get your head around in totality. But IPv6 and multicast go hand in hand. V6 incorporates multicast as part of its key functionality for communications, and having technologies like embedded RP definitely make it very prevalent to be able to use multicast in a v6 domain. We still do have the same Ethernet mapping concern, although, as we discussed earlier, it's a bit more mitigated just because of the sheer volume of the address space. We don't have to worry about overlap as much as we do. It's not a 1:32 mapping anymore. It's a much larger mapping. And a lot of our same concepts that we're used to in a v4 world apply in a v6 world as well. So now we can start to see how MLD maps to IGMP, for example, and that we still have Anycast RP as an option, right? Or we can use embedded RP in v6. So the future is exciting for IPv6, and with its multicast capabilities built into it, it's got a good foundation. Yes.
Will IPv6 eliminate netting?
So the question is, will IPv6 eliminate natting? In general, the answer is yes, right? Because the amount of address space that's available, the need to conserve it isn't really there, which is kind of an interesting thing to think about because we've been conserving IPv4 address space for a long time using RFC 1918 and leveraging NAT to kind of obfuscate that from the global internet because there weren't enough addresses available for everything that needed to be connected. The converse is true that you can have, I'm trying to remember the stat, it was like 1 trillion IP addresses allocated to every person on the planet and still not run out of IPv6. I mean, it's a phenomenal number. So I guess the answer for now is no need to conserve it. Although, like I said, we'll see in 30 years if people are going, what were they thinking? That was crazy. We need it for everything. You had a question?
Yeah, isn't that in IP version 6? You still can do it if you want to do it for whatever reason.
Right. So there is, the question is, in there still NAT and V6, and there is, right? So V4 to V6 gateways and things of that nature, you still can do NAT, but I don't know that there's any practical NAT implementations in software out there just because you don't need to. So, and developers are much like network engineers, they're not going to write it unless you need it type of thing. So until somebody has a compelling case for it, I don't know that we'll actually see it in software.
Well, not in software, but as a firewall in terms of hiding your ports, that still exists, I presume.
So yeah, the comment is about if I wanted to use it as a security mechanism, is that a possibility? I mean, from a concept standpoint, sure. I don't know of any firewall vendor that's done a V6 NAT, although in all fairness, I haven't looked really hard either. So there very well could be one out there that I'm just not aware of.
I was a Linux firewall reseller, and that was a great point of debate. Some people see that approach to NAT as a security obscurity mechanism. I don't discount it, but that's one of the reasons why people aren't interested in that.
Yep.
Between MLD and IGMP, if you have version 3 and version 2, in general they roughly map to each other. But if you have to deploy something where you're going to be using multicasting on both networks, is there a way to get those two protocols to kind of share data with each other?
Got it.
Or do you have to kind of deploy them in parallel?
Yeah, so the question is really, from a layer 2 standpoint, if I've got V4 hosts and V6 hosts, I'm going to deploy IGMP version 2 or 3, and I'm also going to deploy MLD version 1 and 2. Can they share any data between the two of them? And the answer is no. They're separate. It's kind of ships in the night. Much like the routing tables. If you look at it from an IPv6 routing standpoint, I've got my OSPv3 routing tables or my RIP-NG routing tables, and they don't talk to the V4 routing tables unless I have a gateway of some kind to get between the two. So yeah, they're definitely ships in the night type of thing.
There's another mode in PIM, the Sparse Dense. Is there any application used for it nowadays?
Yeah, so in PIM, when you configure it in iOS specifically, you'll see that there's an option for IP PIM Dense Mode, IP PIM Sparse Mode, or IP PIM Sparse Dense Mode. And the idea with Sparse Dense Mode is for all like auto RP, where I still need to have that dense mode fallback for that flooding behavior for RP discovery, but I don't need it for anything else. So very rarely do you see an application other than auto RP where customers will deploy Sparse Dense Mode. For a long time, customers would deploy Sparse Dense Mode just because it was the fear factor. I don't know if I'm going to need it or not. I'd rather have it than break something in the future. But if you look at some of the newer OSs, NXOS is a great example, there is absolutely zero dense mode support in NXOS. No plans for it. There's no need for it, and so there's not even a sparse dense mode. It's just IP PIM sparse mode in NXOS. So that's kind of the direction that Cisco is taking the protocols. But so it would be few and far between that it would be an application other than auto RP that could use sparse dense mode. But you'll see that in a lot of iOS configs. IP PIM sparse dense mode. That's what we configured when we deployed our sparse mode network. But we were using our auto RP as well. So we're using auto RP with Anycast and MSDP. So let's turn on all the control plane protocols. Yes?
ISP standards question. If ISP is supporting IP6, are they likely then to be supporting multicasting toward their leg of the IP6?
So the question is, if a service provider is supporting IPv6, are they also equally likely to be supporting multicast? And I would say that's on a case-by-case basis. I've not seen too many ISPs that are supporting v6 multicast.
See, this is like it's great corporate technology, multicast, but it's like the promise for opening up the internet is just not there because the ISPs are shrugging their shoulders about it.
Yeah, and I think a lot of that has to do with the inability to be able to have an adequate number of address space, right? So I mean, even if you look at the global allocation for v4 multicast, it's a pretty small number compared to the global internet. So the challenge was, how do we allocate it out to different service providers? And they're always going to want more. The potential certainly exists that with v6, because of the glut of address space, that it might become much more prevalent.
Right, so what do you see as the stumbling block that they're not doing it with IP6?
Probably vendor support. I mean, when looking specifically at the product that I supported, which was Next 7000, v6 was on our list of things that we would prioritize and add stuff for, but it was never near the top of our priority list. It was always, if we have time, we'll add some v6 stuff too. Just because the customers themselves aren't necessarily deploying it. And the service providers, while they're huge, aren't necessarily big customers. They're not buying, tons and tons and tons and tons and tons of stuff all the time. So it's very much a coin-operated decision.
It'd be a great carrot to get people off of IP4 so they come on IP6.
Yeah, truly. And I think from a big picture standpoint, the news in the last couple of weeks about the v4 addresses running out is something that I think people in the IT industry have heard for a long time, right? It's almost like the
wolf.
Yeah. I was going to say the Pied Piper, but it's not the Pied Piper. It's the little boy who cried wolf. But you know what? Now the wolf is here, and I think it's kind of telling when people who are non-technical are like, hey, so what's up with this IP exhaustion thing? Is that a problem? And you say, oh yeah. Whoa, what are we going to do about it? I mean, how am I going to get it on my Facebook? That's horrible if I run out. So, that's their equation of what it means. But certainly it's got broader implications. But I'm hoping that, in general, we'll be able to kind of ride that wave. You need to have that compelling event to make it to where it becomes a priority. And even if you look at the government from a mandate standpoint, a lot of the v6 stuff that's out there was because the federal government said we only are buying devices from this point forward that are v6 capable and have some basic functionality. Great. So define basic functionality, that's what you get. As opposed to all the other things that v6 can do that take time to productize, develop, code, test, QA. We'll see how it plays out. It's definitely a watch this space. I'm kind of hoping that this last stuff will be the tipping point to where people say, you know what, we need to take it seriously and start doing something with it.
You need like a Meerkat application to drive it or something like that.
Yeah, exactly. Get one of these viral apps that drive it, and it'll be everywhere.
It's going to be a year 2K thing all over again. Oh, it's 2000 coming up. We got to do all this. Be ready for it.
Well, but that's what's so interesting about the SPs and people that different enterprises that I worked with in Asia Pac. For them, it was the only way they were going to go. Right? They were getting rid of NAT. The populations are such that the v4 space just doesn't scale. It's easy to see. I got however many billions of people in this country. Guess what? I don't have that many addresses. I'm going to go to v6. And certainly with some of the governments, it's easy to make a broad statement that thou shalt be v6 enabled by this date, come hell or high water, and you better be there. So
It's also probably because it's an emergency. They're emergent technologies, as opposed to being there for a long time.
Yeah, absolutely. When you have the legacy mindset, and truly, you look at some of the bigger, huge customers, talk about legacy mindset, they define legacy mindset, right? But they're also kind of the tail that wags the dog because they've got the purse. So
IoT is going to probably drive V6.
yeah, IoT is a great example of something that will help drive the need for V6. And certainly that's where some of the military applications I talked about earlier come into play too. If I've got thousands of soldiers on a battlefield, each of them has 1,000 IP addresses, I'm not doing that with V4. I have to do it with V6. So I can summarize that theater as a route as opposed to, you know, holy crap, how many subnets is that? That dude's wearing 2 subnets. You're not allowed to wear 2 subnets. So, yeah.
Call it IOHT, the Internet of Hackable Things.
Well, the Internet of Hackable Things is, yeah. Yeah, if you're in the security field, future's bright. There's plenty of work to be done, guaranteed. Hopefully you've learned a lot about IP Multicast, and I appreciate you taking the time. We started with an overview of IP Multicast before we moved into Layer 2 IGMP, and then followed up with Layer 3 Protocol Independent Multicast. We additionally covered Rendezvous Point engineering, controlling multicast traffic, source-specific multicast, and finally, IPv6 and multicast. Hopefully you learned a lot and feel more comfortable deploying IP Multicast in your network now.